Ready? Okay, so good morning, everyone. You can be a little louder. Good morning, everyone. Welcome to this first edition of the Zak World of Façades conference series. My name is Ahmed. I'm part of the organizing team here. I quickly want to introduce the Zak World of Façades conference series to you. We've been doing this event from the past 10 years. This is edition number 120. I'll just give you a quick brief of the event. Sam, there's some feedback on you. So we've been doing this event since 2012. We started it as a small networking event, and we've been able to grow this conference across the globe. 40 countries is where we are present. This is edition 120. Second one in Canada. We had one in May in Toronto last year, and we'll be having one in Montreal later this year. So the event spread out from New Zealand up until here in Canada. Every market is different. Every region has its own challenges. In some places it's about value engineering, in some places it's about embodied carbon, in some places it's about complex geometries, massive large-scale projects. So we've had the pleasure of hosting some great speakers throughout the globe talking on different topics. Been doing this in the last 10 years, same thing. Every time there's a different story. And I hope the storytelling by our speakers today would find you guys would find it interesting. I've tried to customize it as local as possible for the British Columbia to the Western Canada market. So hopefully you'll like it. So I'd like to start off by thanking our event partners. I'll just take 3-4 minutes. I would like to acknowledge all our partners before we get into the agenda. So our presenting partner for the event is Reyners Aluminium. Those who don't know Reyners is a Belgium company. They're one of the top 5 aluminium door, window, curtain wall system companies, one of the leading players in this segment. So they are the presenting partners for the event. AGC Interpaint is a German manufacturer of high-performance value-added glass products. American Fiber Cement Corporation, so they have fiber cement products for cladding. Beijing Wuhan Tiabo Glass, we call it WHTB, so they are a leading value-added glass processor out of China. Boston Valley Terracotta from Boston, some specialty terracotta stuff they do for cladding, for monuments, for other external applications on the facade and envelope. Cosentino, Spanish manufacturer, they have interesting cladding material called Decton. This is CSG, China Southern Glass, another large top 3 glass producers of the world. EOT, German manufacturer, they've got fixing systems, and now they've got rain screen cladding systems, which they'll be displaying on the show. Engineered Assemblies is a leading distributor of multifold cladding products based here in Canada. Equitone, manufacturer of cement board products, decorative, non-decorative. Guardian Glass, one of the larger coated glass manufacturers out of the US. HALIO is a dynamic glass company, the glass which tints on demand. They are here presenting today. Hydro is one of the leading manufacturers of aluminum extrusions made out of sustainable solutions. Curare is the mother company of the laminated glass interlayers, Throsifol and Sentry Glass. Northern Façades, another Canadian company, they have rain screen systems. Rigidize is an American company, they've got all metal cladding solutions for facades and envelopes. Sherwin-Williams Coil Coatings is a liquid PVDF solutions provider. Sound Solutions, another Canadian company, distributor of many cladding products for the facade, terracotta, and few other stuff. Tactile, American company. UHPC, Ultra High Performance Concrete, another interesting material which is picking up speed in Europe and now in North America too. Vitro Architectural Glass, formerly known as PPG, one of the leaders in high-performance coated glass. Vitrum Glass Group, one of the local glass fabricators here in the region. And a post-event reception host. So post the event, we've got a networking reception. I think if you're on time, 5:30 to 6:30 it is. It's going to take place at the exhibit area, courtesy Alutech. This is the Canadian division of Alutech. Alutech is a leading facade fabricator out of the Middle East. Our refreshments partner is Moso. Moso has some interesting bamboo products. 24 core LUs can be obtained for the event by the AIBC. Mr. Susan? Yeah. Sign up after the event, right? Okay. You need to sign up after the event. At the registration counter, please give your membership number and sign out while you're leaving the event. Our next event is next week in San Francisco. We've got one in Chennai in India after that. We've got Cairo the following week, and then a couple of days after that, we've got Milan. We've got Washington, D.C. next month. We've got Hyderabad in India again. We've got Hong Kong. We've got Shanghai. New York, Montreal in Canada later, and this is something which we have collaborated with. So the Society of Facade Engineering facade engineers would have heard of this. They're based out of the UK. They are an affiliate of SIPSI. SIPSI is the ASHRAE equivalent in Europe and the UK. They have this. They have this association called Society of Facade Engineering, and they do these awards in London. It's a black tie event, high-end event, 400, 500 people attending, where people from all across the globe can nominate themselves for projects they have done which are related to the facade. These are the categories. Basically, they've got 6 categories which they do. So if you want to nominate your project, or you want to get your client's projects, or want to nominate your colleagues for Young Facade Engineers of the award, you can definitely enter this competition. I think it ends in the next 3 or 4 weeks, the entries. But this is something very interesting. It was more a UK-Europe thing, but we collaborated with them last year, trying to make this more global. And eventually, this will also come to North America, starting with the US very soon. So this is our collaboration with SIPSI, which is with SIPSI and the SFE, which is the Society of Facade Engineering. These awards to reward people who have some fabulous work done on building envelopes. So just to let you know, we've recorded today's event, so we will pass on the YouTube link of today's recording a week from now, along with the feedback form. We're not going to take any questions. We are tight on time, so if you have any questions, we request you to meet our sponsors, our speakers outside in the networking break. All our partners, associate partners, presenting partners, they all have booths outside, which you would have seen. Request you to please go interact with them. Some nice products are on display. I think one of the complete range of products, anything to do with those windows, facades, cladding, we have on display. So feel free to interact with them. And that's it from me. My role ends here. I'd just like to call upon our event host and convener, Heather Reid. She's a Senior Director for Technical and Commercial Relations at Shard Development. So she's going to be hosting this event and be taking this discussion forward. So I'd like to call up Heather on stage, please.
Good morning. I'm Heather Reid, your MC for today. Thank you very much for coming. It's always nice to get together in person. We've survived COVID, so I'm happy to be here with you. I don't want to take up too much time because we're getting started a little bit late. We've got an excellent and packed program today, a lot of heavy hitters. The day is broken into 4 sessions. There's going to be 3 breaks. Because we're getting started a little bit late, please keep your eye on the time and pay attention. I think we come back from our first break at 10:55, so we might be starting that break a little bit late. Get used to my voice. Some of you already know it. I ask a lot of questions, as you might know. So I'll just get to some housekeeping really quickly. The program expectations, there's food and drink. The venue asks for you to keep the food and drink outside and please not bring it inside. Again, please pay attention. We really want to keep this on track. I wore red so you can see me, and I'll probably be moving around trying to get people to come back into the conference area. Please silence your cell phones or put them on vibrate. Some of you are here for chatting and networking, and probably you're working today for parts of the day. If you have to take calls, we just ask that you take the calls outside. If you know that you're going to be taking calls, maybe you could sit near the back or towards the aisles so that everyone else can stay focused on the content. The presentations are quite short, so there's a lot of information, and I'm sure a lot of you would like to pay attention. So as Ahmed said, there will be recordings, but there will be no decks. So the YouTube channel will have the recording of this event. The sponsors and booths, I mean, these events aren't possible without sponsors, so please make sure to go outside and visit the booths. Social hour at the end of the show is sponsored by Alutech, so please stick around for an hour. And I think the learning credits have been covered. I believe you have to sign a form for every single speaker or session that you go to, so please go to the registration and fill those out at the breaks. Okay, I think I covered everything. I'm going to talk very quickly as we get through this. Thank you to the organizers, the venue, the sponsors, presenters, and all of you. It takes a lot of effort to put these on, and your support and attendance is greatly appreciated. Here we go. First up, we have Anna Maria Llanos and Anthony Brown of Diamond Schmidt, who will present the Tellus Ocean project in Victoria that's targeting step 3.
Good morning. It's a pleasure to be here with you and to have been given the opportunity to open today's session. So thank you for being here. Just a quick agenda. I'll introduce the company and then I'll pass it over to Anthony that will give you some background on the Tellus Ocean project, and then he'll jump right into the traditional assembly versus the alternate approach that we've taken for this project. A little bit about Diamond Schmidt. I'm Anna Maria Llanos. I'm a principal with the firm, have been with the firm for the past 23 years. I moved here 8 years ago to open the Vancouver office of Diamond Schmidt. Some of my projects involve the Emily Carr University of Art and Design, the Tellus Ocean project that we'll talk about today. I'm also involved in the Oak Ridge Redevelopment project with many of you here, I'm sure, and among other projects that are currently underway.
Hi, I'm Anthony Brown. I'm a senior designer with Diamond Schmidt Architects. I'm a registered architect in the UK since 2015 and have been in Vancouver for the last 5 years. During that time, I've worked on a number of schemes at Oak Ridge, Tellus Ocean, and our whole community centre. And my background prior to moving to Vancouver was largely large-scale residential units.
A little bit about us. There's about 275 of us, 32 here in Vancouver. Our head office is in Toronto, and we also have a small office in New York. Very proud to have received numerous design awards, among other kinds of awards. We've been around for about 47 years. In terms of the sectors that we're involved in, performing arts, lots of rec facilities across the country, residential work, also libraries. You might be familiar with some of these. Also healthcare and academic work, civic work, among other sectors. Even though we didn't have an office here, we've been practicing in BC for close to 25 years now, and very proud to be here. Over to you, Anthony.
Excellent. Okay, so it's my pleasure today to introduce you to the Tellus Ocean scheme in Victoria. The client is Tellus, and the design team is Diamond Schmidt Architects, RDH as building envelope consultant, RJC for structural engineering, Introba for mechanical, electrical, fire, security, lighting, and sustainability, Alice Don are the general contractors, and Flynn are the design assist partner for the curtain wall, with Evoke as the energy modelers as part of their work. So I say the site is located in Victoria. So we recognize the land development must stand on, on land that has existed under the stewardship of the Lekwungen peoples for thousands of years. We acknowledge with respect the beautiful and traditional territories of the Lekwungen people and the Esquimalt and Songhees nations. The site itself sits on the boundary between two rezoning locations, the core business district to the north and the inner harbour and legislative buildings to the south. And it sits in a triangular site wedged between the intersection of Douglas Street and Humboldt Street. Historically, the site was slightly different, and James Bay used to actually extend to where the site is today. This space was traditionally mudflats and tidal pools. During the construction of the Empress Hotel in 1904, this area was actually reclaimed as part of that construction. So we have here a historic aerial photo of what that looked like back prior to the construction of the Empress. You see the site here in red. The Empress Hotel was actually constructed in the location of the bridge, as you see here on the left, on Birdcage Walk, which is actually now Government Street. And you can actually see here just to the left, you see the legislative buildings of Victoria. The site originally was used for heavy industrial uses with a waterfront access. However, at some point post the construction of the Empress Hotel, it was actually the site of the laundry, complete with a smokestack, that was interconnected via a tunnel back underneath the convention center back to the Empress Hotel. So this is the site as it was a few months ago prior to excavation and shoring starting on site. And as you can see, it's a very particular triangular shape, say wedged between Douglas, as you can see here, which is at the main street, north-south through Victoria, and Humboldt just to the north. You can see here on the left, the one of the wings of the Empress Hotel, and then the green copper cladding of the Victoria Convention Centre. Is flanked on the south by Crystal Gardens, which is this low-rise building you see here at the bottom of the page, and then on two sides by high residential units. The core business district is, again, say to the north. This would actually be the kind of the end of that core business district. So as with a lot of the Talus buildings, they start with a theme, such as gardens in Vancouver and sky in Calgary. And this scheme's no different, and we didn't have to go far to look for historic context to draw inspiration from for Talus Ocean. As I say, originally James Bay used to be this tidal swash with tidal pools and kelp. And historically, the land around would have been the Garry Oaks grasslands. So as with any site that's as highly constrained as this one is, it kind of dictates the form and massing of the building, and so we're shoehorned into this kind of flat iron shape from the day one. But what we sought to do was to manipulate height at the north to create prominence at the apex of the core business district to the north. We also cut back at ground level, as is important with any large scale building. It's important to create some kind of human scale at grade. And so the cutback allows us to create this kind of sheltered soffit overhang at grade. We also cut the corner on the south end to preserve key city views and to improve daylighting into the floor plates. To improve privacy, the core and washrooms are located onto the southwest corner of the site, therefore maximizing an opportunity for the office spaces to connect with the west. With the cut that we created on that south, that afforded us the opportunity for vibrant roof terraces on a number of the office levels. And in keeping with the ocean theme, we integrated a series of saw-teeth elements across the facade. And so with any large public realm, it's important to create high quality space, and we actually extend an existing plaza that's between the development and Crystal Gardens to the south. So let me just walk you through the scheme. The scheme is 3 levels of parkade with access off Humboldt to the east of the site. There's 2 commercial retail units above this at grade, one of which has direct access to Humboldt Plaza to the south. The office lobby is located to the north and has a water feature which blends the transition between interior and exterior space This is interconnected with level 2, where we have a bleacher auditorium arrangement over the entrance lobby. So there's 8 levels of office space, and some of these have access to their own private terraces. Level 10 is an indoor amenity space, which is interconnected with a large roof terrace at level 11, complete again with a bleacher arrangement auditorium. And the PV array creates shade and weather protection to this space. So as I touched on this previously, we wanted to create interest and articulation to the facades. And so we introduced these sawtooth elements. They're paired in double height units with a roof and soffit associated with each. And the drawing on the left illustrates the 3 different panel sizes. We had a 15, a 20, and a 25-degree articulations. During the detailed development stage and working closely with RDH, we drew up options for how these might be constructed, and the original scheme called for a cranked stack joint between the 2 intermediate units, which we'll come back to later. We also established the module size at 1,500 centers, and it was dictated by a large number of different factors, including availability of glass manufacture and coating facilities for the number of different e-coatings that we're applying to the skin here. So we wanted to create a slick, seamless appearance to this curtain wall and to accentuate the verticality. And it's important then to be selective about which horizontal breaks or other breaks and transitions are accommodated for in each of the panels. And so we looked to a previous scheme in our office, which is the Globe and Mail in Toronto. And we have this detail that we refer to as a kissing mullion, which allows for the insulated glass unit to sail past the mullion at the spandrel uninterrupted, with the mullion itself silicon sealed to the back of the IGU unit. We feel that this helps to accentuate the verticality of each of these elements, and in the case of the double height sawteeth, further accentuates these too. The return panels, as you see here, incorporate a wood look metal panel finish. This is to kind of be in contrast to the cool tones of the glass, and also ties in with the wood effect soffits that we have at level 1 and the numerous interior finishes that are in wood. So one of the first concerns we had with such a high transparency building is that of bird safing. And there's no there was no specific Victoria guidance at the time. So we turned to Toronto guidance and also the CSA 460 standard. We reviewed a number of different options for bird safing. We looked at ceramic frit, we looked at acid etch, and we looked at a multitude of different transparent UV coatings. Eventually landing on using just a ceramic frit as the most appropriate tried and tested methodology for this. So the guidance states that up to 16 meters from grade is the highest strike incident rate. And so we've opted to not only include it up to 16 meters, but it also actually follows the same kind of wave pattern as on the rest of the elevations in terms of where the sawteeth are set. We also have it in other high-risk areas, such as areas where we have glazing, which is exterior on both sides, which happens up at the roof terraces. It also happens on the acute corners where we have a potential view through the corner that a bird might see as an access route. Also, with the heavy planting that we put on the terraces, we felt it was important to put it up on the terraces as well, given the heavy planting would attract birds anyway. So the image on the left is from the intersection of Douglas Street and Humboldt, and you can clearly see here that kind of wave pattern. And you're seeing the short end returns here. The waves themselves kind of increase in size as they reach the northern tip, but like waves on the shoreline, they actually flip back on themselves as they hit the north end, and they're actually orientated back the other way, which is why you can't see any of the returns on this end. This same motif exists along the Penwell and Humboldt elevations as well. And in these cases, that sawtooth element is also present in the metal and the glazed units here. You can see on the right-hand image at the bottom here, the Gary Oak Meadow theme coming back over the parkade entrance, and the extension to the Humboldt Plaza here with the retail patio spill out just on the bottom page. This image here clearly shows, the extension of that plaza between Crystal Gardens on the bottom right-hand corner and the new development, and also the number of terraces and the planting that we have on each of these as we go up the building. So TELUS had high aspirations for the building and high sustainability goals. And so the building itself is targeting 0 carbon, is targeting LEED Platinum, is targeting STEPCO 3, which is currently the highest tier for this usage class right now. Salmon safe as well. So given a need to meet the STEPCO 3 compliance and the associated TEDIs, we needed a high performance from all of the areas, but particularly from those areas which were solid metal panel. So prior to tendering, we felt that the metal panel requirements were particularly onerous and were not ones that we could include as part of the bid for the curtain wall. So we opted for a traditional assembly here, which is metal panel with a cavity on Z girts, and then 250 mil of semi-rigid insulation fill on a substrate. And at one point, the substrate 2 was also filled with 150 mil of mineral insulation. We also needed to balance a number of different other performance criteria, be they aesthetics or physical constraints of construction. And so we actually subcategorized each of the vision areas as well. And in the case of the level 1 glazing, this gave us the opportunity to actually downgrade the glazing originally from triple glazing down to double glazing, given there were a number of curved glass units here. And so a triple glazed curved glass unit would have been extortionately expensive. So the images here show you how we subcategorized each of the assemblies on the scheme. So the pink is this double glazing that I just referred to at grade. Dark blue is the majority of the conditioned envelope vision glazing. This is what we refer to as CS2. And then EW10, which is the solid metal panel areas, are here in yellow. And as you can see, we concentrated them onto the southeast corner in an attempt to improve privacy on this corner, given the residential units that were on this side of the building. The purple areas are the areas of glazing associated with each of the terraces. And then light blue and dark orange, as you see here, are actually outside of the conditioned envelope. They were what we refer to as the windscreen components. They're physically separated from the curtain wall below. However, the intent is that they should appear as if they were seamless, and we're looking at double glazed units here with specular coatings in an attempt to try and mimic the appearance of the glazing that we have triple glazing below. So step code 3 was challenging, and we went through a series of iterations through energy modeling during the process. And one of the most important things on the scheme was a balance of solid to glass. So as you can see here in blue, the vision areas, we have light gray are all of the spandrel areas, and then dark gray are the EW10 metal panel areas. So we landed somewhere around a 50-50 split. And let's say we went through multiple iterations. There were a lot of things to consider as we went through this process of trying to balance the thermal performance against of solid over glass, but without impacting the daylighting to the southeast corner and the office spaces behind. We also looked at a number of times looked at reducing the number of saw teeth, given the amount of increased surface area each of these contained. They were thermally not as efficient, and also there's a cost impact in each of those saw teeth. So we land somewhere around a 45 to 55% glass to solid ratio once you accommodate for all of the other areas of thermal envelope on the building. So when I first joined the team, I think around 2 years ago, and during detailed development, one of the first things I needed to do was to start itemizing each of the panels that we had on the job within Revit, and this proved particularly useful for the energy modeling and also for communication to prospective curtain wall trades. But it was important to be cognizant of the number of variations that we have. Sorry, mouse is on wrong. Yeah, important to be cognizant of the amount of variations. We have a number of different geometric variations. There's planar units, there's 3 different saw teeth angles, both with upper and lower units. And then coupled them with them being full glass units, those with a kissing mullion, those which are louvers, full spandrel, metal panel. It quickly ends up a large number of different panel configurations. Once this process was done, we also overlay requirement for bird safing. This, as I said before, this kind of follows a sort of a wave pattern too. And then there's also an opportunity for perforated artwork to go in some of the return panels. So you can see it quickly becomes very complicated and complex, and it's important to make sure that there's a clear and effective communication of design intent between ourselves and the prospective curtain wall trade. This also helped a lot with the energy modeling process and our work with RDH. Through the use of type marking all of those different panel types, as I was able to build in parameters that would actually calculate the spandrel areas, the metal panel areas, and accommodate for the increased surface areas on saw teeth. And this informed a lot of our discussions around the energy modeling and subsequent TEDI targets, and assisted RDH in terms of material takeoff for these kind of things. So as I say, we originally looked at the metal panel areas being of a traditional build with a metal panel on Z-girts back to a substrate. But it quickly became clear that there were also challenges in doing it in this way. Challenges of having 2 separate systems adjacent to each other and the sills that you would require between each. Especially as in the case that you see here, which is the Humboldt Street elevation. We change between the 2 frequently in a random pattern, and quickly once you map all of those red lines on as perimeter sills for air and water, it quickly ends up a considerable as I say, once you actually map those red lines onto the elevation, you end up with a considerable linear length of transition and tape joint between two different scopes. And this was a challenge for a couple of reasons. You know, it's unclear as to whether the curtain wall could potentially end up being given to one trade and the metal panel given to another, and then whose responsibility does this transition lie? Also, who takes ownership of the warranty of the transition? And given it's the air tightness sill, which was critical for the commissioning and then the blower door tests that we would be undertaking, it felt like there was a lot of inherent risk in this. No, this is doing something else. It looks like your Teams is trying to come up. Okay, it's working. Thanks. Another challenge which we identified with RJC when they calculated the seismic drifts was also the racking between two different systems. The unitized system is hung from the top and interlocked with its adjacent units on the stack joints and the split mullions on the other three sides. Speaking to RDH on this during the detailed design, we identified that it was important that all of the curtain wall would rack uniformly. And so to do that, the intention is that one corner would be pivoted, and therefore all of the panels on one elevation would all rack in the same orientation. The issue being, if two panels were to rack independently of each other and in different directions, you'd end up applying stress to the units and potential failure of the system. The challenge here, though, is that the metal panel areas will deflect as well as move in seismic in a different way. They're tied back to a traditional stud assembly that's associated with each of the floor levels. And in that case, that actually means that the kind of load pathing for the metal panels is to the slab below, but the adjacent curtain wall next to it is to the slab above, given their top hung. And so the two units next to each other would actually move in very different behavior, not just in seismic, but also during lifelong deflections that would occur during the building settlement. And it was felt that this would create like a shearing motion in those transitions, and potentially more chance of and likelihood of failure. So the scheme was tendered as a design assist, and given the challenges of the two systems and having metal panel and the unitizer separate systems, we ended up addendering in the metal panel areas in the hope that either or any of the trades who were that was bid to would take full responsibility for both the metal panel areas, either as a traditional construction, or would come to the table with an innovative solution to this problem. And that's where Flynn's speedwall system stood out as an innovative solution. It had the potential to accommodate for all of the metal panel areas within a single unitized system, but it also had the opportunity to exceed the performances that we had in the specification. So the speedwall system offers a one-stop shop, effectively. It benefits that it's a single unitized system for the entire job, and therefore would rack and behave all as one system. It also utilizes tried and tested methodology for creating the airtight and weathertight sills between units in the traditional curtain wall stack joint and split mullion form. The system itself introduces a 6-inch quad-core kingspan panel, which sits over the face of the mullions and actually improves the performance of these areas over a traditional curtain wall system, given that you're overcladding the weakest element thermally, which is the mullion. Interestingly, as the design developed, the saw teeths actually end up as both having, as you can see on the right here, they actually have a roof and a soffit condition for each of the saw teeth. And so effectively, we don't have a difference between the upper and lower units as we did originally envision, thereby reducing the number of panel types effectively on the project. So Flynn worked with Evoke as the energy modelers, and they proved that they could actually exceed the thermal performance requirements in the spec. The original EW10 specification was for an R40 thermal performance, but Flynn Speedwall promised R50 and helped to increase the buffer in the energy model. And that concludes the presentation. It's been an interesting project to work on. And at times we felt we were definitely pushing the boundaries of kind of what was feasible for such a highly transparent glass building, whilst also balancing the aesthetic design considerations for the saw teeth and the inclusion of metal panels. So I give thanks to the great team that we've had on the project, RDH, Troba, LMDG and RJC, but also to Flynn as a design assist partners for the last year or so. And obviously to Tellus for giving us all this opportunity to design and develop such an interesting and sustainably focused development. Thank you.
Thank you very much for the presentation. We're just getting set up with Bryan Hubbs, who is a good friend and mentor of mine in engineering and boat purchasing, surprisingly. Bryan Hubbs is the founding principal of RDH Building Science, and he's going to talk about one of his passions, other than fishing, outdoorsing, and cabining, forensic engineering, the CSI buildings. Thanks, Bryan. I hope you also learned one more thing. You don't want to run into Bryan Hubs in a courtroom, or you want him on your side. Okay, our next presenter is John Krouse, the president and CEO of Boston Valley Terracotta, and he's going to talk about architectural terracotta facade systems.
Thank you.
Welcome, John.
Thank you. Good morning, everybody. Bryan, great job. I'm a little bit different than wood. I'm fired ceramic. We're located in Buffalo, New York, where we manufacture our architectural ceramics. I am the president and CEO of Boston Valley, and we've been doing this since 1889. And back in the early 80s, we started into the restoration of terracotta for historic buildings, and then by 2000, we started really, or 1999, we started really investigating the possibility of converting our facility to adding a product line for rain screen systems, thanks to the Canadian market and our proximity to Toronto. We're about 2 hours from downtown Toronto, but we're in a very good spot to deliver materials to the construction trade within a 500-mile radius of our facility. So my feature building that I love talking about, which is just coming to completion, is the Well in Toronto. And I put that up as my beauty pick for this presentation because everybody needs to go and take a look at it. It turned out so nice. And we're going to talk a little bit about it, but I know I only have like a 15-minute window just to talk about the product. But anyway, the Well is a terrific job that illustrates what you can do with architectural ceramics in a rain screen application in a northern climate. So what's nice about working with architectural ceramics, it's a little bit different than other building materials. It's been around for centuries, and soft clay can be molded into all kinds of interesting shapes and configurations at about 4 times less the density or weight of solid veneer stone or granite or that type of thing. So the industry really exploded turn of the century, and there's evidence of it all throughout North America from our friends in England who helped to engineer basically a substitute material to replace carved stone with decorative ornament that lasts as long as stone. So the beauty of the material is it's soft, it's flexible, it can be molded, and it can be made hollow to keep the weight down. So some of the inherent qualities that I just talked about are, that's a ball of clay that's soft and sticky. You can see how sticky it is on the guy's hands. That can be formed in a number of different forming methods that we employ at our facility. One of them being extrusion, which is the most cost-effective way to mold lightweight veneer for ceramic rain screens. It could also be slip cast. It can be hydraulically pressed using a process called the ram press, and it could also be hand packed into plaster molds. And we'll touch on a little of those forming methods through the presentation. What really brought this material to the forefront, turn of the century, were buildings like this. In Canada, they refer to these as heritage buildings. In the US, we call them landmark buildings. They're basically one and the same. They're very important examples of architects working with architectural ceramics at the highest level. The building on the right is Louis Sullivan, one of the most famous architects that worked in Chicago and left his mark using this material. That was really his signature material. And then on the left, Case Gilbert was another master architect that really had a firm command on how to design and build with this material. Now, the building on the left actually suffered a major catastrophe during 9/11, and one of the debris of the airplane from the World Trade Tower crashed into this building, and the trade tower was leaning into it, and this building was literally on fire for 6 days before the fire department could put it out. After all the chaos and the cleanup happened, the engineering teams went into the building and discovered that literally the structural component of the building was sound thanks to the ceramic cladding that had clad around the steel. So again, the beauty of the material is it's a wonderful fireproof material, but the building did not have to be demolished and taken down because it was still structurally sound. It suffered a fair amount of fire damage on the outside, and the interior had to be completely gutted. But at the end of the day, the building survived. It underwent a major restoration, and there it is today, standing fully occupied. So it's a testament to the material of what it can withstand regarding fire and just a general accident of that size. When you decide to look at this material for using it in your project, one of the things that's nice is you can leave it like a standard brick. It comes in red, different shades of red, but that's the basic color palette to start with if you're an architect. We can also customize the through body, so if you have a very sensitive client that wants to match the existing brick on campus or whatever it may be, we can develop a formulation to tie into that existing unglazed clay body mix. Then you can take it a step further, and then the designers really have a lot of fun with this part of it, because you can really emulate just about any type of finish you want on top of this unglazed ceramic by working with glazes. Glazes are basically a complex glass that are fused to the ceramic in the kiln when it's heated up and fired. We control all our own proprietary glaze formulations. More recently, we've been working with recycled glass from Vitro, who's here, using a borosilicate glass that's being recycled that we can incorporate into our glaze, so we're trying to be as green as possible. But really, the sky's kind of the limit. We can go anywhere from a dry matte glaze that looks just like a limestone finish, all the way to a very high gloss glaze where it's pooling off the ceramic itself. For example, that piece on the far right and the far left, you can see where the actual glaze will break off the edge of the bisque and reveal a slightly different look to the finish. Some people like it, some people don't. It's really a personal preference. And the piece in the middle is simulating metallic finish, and we have a number of those formulations pre-engineered for architects to investigate as well. So just locally here in Vancouver, we've worked on a number of heritage buildings. Barry McGinn, I don't know if Barry's in the audience, but Barry is one of our go-to guys that we do a lot of work with. Very knowledgeable in the building restoration of ceramic facades. This was a job I did with Barry probably almost 20 years ago. Simon Fraser owns the building, the university, and the cornice needed a lot of repair. At the end of the day, Barry was able to systematically number, catalog, remove what he felt were the terracotta units that were in good shape, carefully organize it, and then incorporate new replacement pieces in where some of the pieces might have broken from rotten steel. You had to disassemble the building just to inspect the steel to make sure that everything was structurally sound before you really got into it. So there was a number of probes that were done ahead of time to understand the condition of that steel and how far the damage was done regarding rusting steel and terracotta blocks failing. But he did a terrific job in putting this building back together. We worked with Kirchhoff Masonry, who did a fantastic job also at reinstalling all the terracotta. These were the players that were involved with the project, and there's an overall shot of the cornice. Beautiful heritage building. These are buildings, your best and greenest project is the building that's already built, but we try to keep these buildings around and restore them for a long time. So this building is well over 100 years old, and we'd like to keep it another 100 years. So through proper care and maintenance, we can do that just through paying attention to those little details like Bryan talked about, maybe with sealants and water infiltration and stuff like that. Another great shot of that cornice. Another project that we worked on more recently was the Sun Tower. There was a lot of damage up top. Did a complete study. Barry, again, was the facade engineer, architect on the project, and we worked with Alpha Masonry to do a terrific replacement. So some of the things that we get involved with when doing this type of work, we like to get out and survey the buildings, work hand in hand with cataloging the actual parts where they go on the building, and then identify them on the architect's blueprints So the contractor knows exactly where each replacement piece is going. Very important. And then in doing that, our facility has completely embraced technology. So about 12 years ago, we partnered up with the School of Architecture and Design at the University of Buffalo, where we're located, and lo and behold, they have all this new software available to recreate three-dimensional objects simply through scanning. And now we can leverage that technology through hand scanning devices and then tabletop scanning. So we don't necessarily have to have the extraction of the historic facade element off the building. We can actually get up on the wall, do the scanning, and we're in research mode right now on trying to figure out how to use like a ground penetrating radar to figure out how deep the block goes in the wall, because that's kind of where the guesswork happens. When you scan it, you can get all the information on the outward side of what you see, but you really don't know what's going on behind the wall. So you got to be careful not to rely too heavily on the technology. And it is a team effort when you're working with a facade engineer, architect, and a building contractor to work together as a team to understand how these buildings are put together and how to put them back properly. So by working in 3D, we're able to generate a model and then break it down into what we call a standard shop ticket. But this actual drawing goes to work for us in the factory. We will actually take that approved drawing and then run it through a CNC machining operation and carve that ornament as accurate as that scan was. It's really incredible. So the ability to replicate historic material has gotten better and better, and we're leveraging that at our facility. Another thing that we do too is we have a pretty intensive QC process at our factory, and part of that process is controlling the finish on the product by just paying attention to your batching operation, making sure there's no mistakes. Once that little 3x6 tile is approved, then we develop range samples, which are on 12x12 tiles. And what we do by the range samples is submit that to the architect and the design team, building engineer, owner, so they can understand that terracotta is a natural material. It's fired in a high temperature kiln, and it's impossible to get a perfect uniform glaze color when you're firing in these gigantic kilns. So you will get some range depending on how thick the glaze was applied and where it's positioned in the kiln. But one of the things that we like to do is express that through explaining to everybody that you will get a subtle range. You can't just pick up that little chip and move it all around the building and say, oh, it doesn't match. That's the beauty of working with the material. So if you understand it and work to its strengths, then everybody's on the same page and the expectation is met. And one of the tools that we use to do that is a Minolta color meter. We don't use our eye. Everybody sees color differently. The meter really doesn't lie. It sees a grid of color, and we apply it in a scientific methodology that creates a plot. So everything coming out of our factory is checked individually against that plot on those range samples to make sure we're not getting outside of that box. Gives the owner, architect, everybody that comfort level to know that we're paying attention and it's going to look right when it gets up in the building. Another beautiful heritage project that we worked on locally here in Victoria was the Union Club. Early on in our technology shift, we did have a problem. We had a young drafter that forgot to expand the model 7% to accommodate for the shrinkage. So we blasted through this job. Everything came out great. They checked everything for color. It looked good, but the shrinkage on the baluster pins was about 7% too small. The contractor called up and said, I don't know what's going on, but your pieces are all a little too short. We admitted the mistake and corrected it immediately, and were able to move on with a successful project. These are the types of failures that you're seeing out there in architectural terracotta, and it's not so much to blame on the material itself, it's the underlying attachment system that was employed. Typically through every window head, there's a piece of steel behind it, and there's moisture getting in from the top. Once that steel gets wet, it starts to rust, it expands, it's got to do something, something's got to give, the terracotta will break. That doesn't mean it's going to fall off the building, but it's something that you have to pay attention to. So a lot of the type of work we do as manufacturers is we're replacing where a lot of that steel is rotted and putting new terracotta blocks back in. These are those baluster pins that I just described to you. Those are the historic samples that were shipped to us. the pins, the baluster pins in the middle. It even says remakes. We remade them. That's what the parts look like on the right. This is just an awesome detail of the beauty on the building. Ceramics are mesmerizing, and it lasts a long time if you put it back together right. So we're very proud to have been part of that project as well. Another shot of the same building. Another beautiful shot after it was restored. Now we get into a part of our company that is separate from Boston Valley, but also not separate. It's what we call our research wing called ACAW, Architectural Ceramic Assemblies Workshop. We host this every year. We're on our 8th year now. And it's an effort to basically educate architectural firms on how to design and build with the material. So it's not just on paper or a Zoom call or looking at details. It's literally inviting firms in that have worked with this material and enjoy working with it and want to take it to the next level, or maybe even learn a little bit more about it. So it's an invite only from us, and we bring 8 teams in annually from all over the world. I think we have Diamond Schmidt scheduled for next year because they wanted in this year really bad, but we filled up pretty quick. But we have a number of firms from across North America and Europe that will be participating this year. This particular exercise we're working on, we're trying to understand a little bit more about the physical properties of the material, about how you can harness the thermal mass of the material and how we can leverage that to help the building performance even better in the future for offloading heat back into the building by heating coils that go into the building. So it's a lot of fun research, and we're all learning together without the pressure of an owner and an architect or a contractor breathing down our throat. So it's really an opportunity for the architect and the facade engineer to roll up their sleeves, work hand in hand with the manufacturer and problem solve, and actually gain a lot of great information working together without the pressure of having to have a failure or whatever happens when you're doing research. So just a quick shot. I think most architects probably saw this back in the 60s. This is your food pyramid for building products. Terracotta falls down at the bottom. It's or in the 0 range, not in the negative range. So it's a very low embodied carbon footprint to start with. That's one of the reasons why we think it's got a bright future going forward. And through exhaustive research with our PhD help from Alfred University, my alma mater, it's a glass and science school. I worked with Dr. Cardy on this for a number of years to get it right. After he fact-checked it twice and I had somebody else fact-check, we are in the 2 to 7 gigajoules per ton of energy that is consumed with our products. So it's very low compared to all these other materials, especially when you look at cement. You would think, how can it be lower than cement? But there's a lot of processes that going into making cement that you don't see or hear or think about when you're thinking about low carbon footprint. With terracotta, it goes right from the pit into the factory and boxed and shipped to the site. So it's not going through as many energy intensive processes, which is one of the reasons why it's low on the chart. So that's what a typical clay pit looks like. It can look a little messy by the untrained eye, but if you're a geologist, you want to run right down that pit and just check it out because it's really exciting. It's just what I call clean dirt, but we're actually mining a fire clay that is in a very specific region of under the Earth's surface that was formed thousands and millions of years ago through erosion of granite mountains and then carried by rivers and streams, and then it settles in deposits. So if you're a geologist, they core drill and sample for this to find the best clays or what is actually underground in the earth, and then you look for these raw materials, and then you have to carefully extract them and then put it back through the Land Reclamation Act, and I'll show you that in a minute. This is a form that we send to every submittal that we work on. It's our EPD form, just proving that we meet the low carbon energy footprint. So anybody that would like a copy of this, it's online on our website. Not terribly exciting, but if you're into all this type of science, it's something that we're really pushing toward being as green as possible. Not only do we do that with our EPD form, but we also use recycled content back in our proprietary mix design. So all the cuttings off the rain screen panels can be sorted, ground up, and recycled back into our clay. That's what the Land Reclamation Act looks like when you're mining clay out of a pit. You put it back and it fills up with water and it turns into a full pond and everybody feels good. The well, beautiful building. Those are the players all involved. It was a long process, design, build, design, assist, a lot of budgeting went on. At the end of the day, they made the right decision. The terracotta is stunning and it actually is integrated beautifully into the whole complex of the 7 buildings. So I urge you to go visit Toronto and check it out, and I think you'll be pleased with what you see. Again, getting into the details is just like heritage work. We number every stone. It has a spot on the map or the blueprint exactly where it goes. And the detailing, we have our own track and clip system. We agonize over these details like you guys do on all your projects. We ask that you reach out to us well in advance if we work with any of you that are considering this, because we can bring a ton of valuable information on detailing and making sure you get it right. And then we mock everything up. Okay, so I'm going to wrap it up right there. It's one of the little beauty pics of the different shapes, but if anybody has any questions, we have a table out back. I'd be happy to answer them. And thank you for listening to my presentation. I know we're out of time, so thank you.
Thank you, John. Okay, this is our last 15-minute presentation. I don't mean to speed it up, so Jason, I hope to give you the 15, but if you can do it faster, please try. Our first break, we're aiming to go out, well, at 10:45, but we're going to be a bit late. If everyone can please come back in around 11:05, and we'll try to get started promptly. So yes, please come in, and we're trying to make up time because we want to get it all in. And then Anna Maria, Anthony, if anyone sees Bryan Hubbs, and John, if you could please come up at the end of this presentation to have a picture. We're going to take pictures of all the presenters after each session. So I'll leave it to you. We have Jason Isackson, a senior director at HALIO, and he's going to talk about dynamic glass, architectural glass technology.
All right, thanks very much. I love coffee and I love coffee breaks, so I recognize we have a short time here. Anyways, thanks for the introduction and thanks for the warm welcome. My name is Jason Isackson. I'm Senior Director at HALIO, and we're going to talk about smart tinting glass technology, the need to elevate building performance, and we'll review 3 projects that have successfully implemented smart glass technology. It's an honor to be here today and to speak to such a distinguished audience and group of innovators and sustainability champions. So we are living on the edge. It is known as an Anthropocene, which is a geologic period of Earth's history when human activities start to impact Earth's natural ecosystems and our climate. So we see on a daily basis, oceans are changing, the Earth is warming, living systems are in decline. This is a big problem, especially when we see on the nightly news stories like this, where it's impacting people's lives and their livelihood. Some places have not enough water, other places have too much water. Do we remember this event? This was back in 2019. The mayor of New York City made a big announcement, and he got the, all the developers in New York got really excited about this. He said, we're going to ban glass skyscrapers in a bid to tackle climate change. Why is that? What's wrong with glass skyscrapers? Well, let's look at a typical building performance. We want to maximize visible light transmittance, so we can do that. With that, we measure the solar heat gain coefficient, which is the amount of solar radiation that the glass will allow into the building. But then if you look at the thermal performance of a glass unit, we're really low. We're at R2.5. The challenge, though, is we live in a very dynamic world. Dynamic weather conditions, dynamic temperatures throughout the year, and so we're left with a static piece of glass that's not keeping up very well. There's a better way. And this is the big problem why glass skyscrapers are, not very good for greenhouse gas emissions. It contributes 30% of Canada's greenhouse gas emissions. And, there's been a study that showed that buildings contribute more greenhouse gas than even cars. So here in Vancouver, 2019, Council declared a climate emergency. And so we have a climate emergency action plan, a number of different bylaws and advanced building standards that are being implemented to try to reduce carbon pollution and the impact that buildings have on the environment. So we need to rethink and reimagine how buildings are heated, cooled, designed, and constructed. And this really impacts every asset class: offices, airports, life sciences, and multifamily. And it's a privilege, and it will be amazing to see the presentation later today about the curve and the really elevated sustainability goals that they put forward to deliver a passive house 60-story tower. So we're looking forward to that later today. But we're going to talk briefly about smart facades and the value that HALIO smart glass technology will bring. And so this is exactly the experience. It is clear and high visible light transmittance when you want it, and then it tints and reduces visible light transmittance, rejects that unwanted solar heat gain when you don't, when the sun is shining on the facade. HALIO smart glass technology isn't new. Electrochromic technology isn't new. We maybe have flown in a 787 airplane recently, and the window was an electrochromic window. We may even see electrochromic rear view mirrors in our cars. And so what's new, though, is the manufacturing processes that allow smart glass to be built into a sustainable business and to deliver the performance that we expect in a dynamic window system. So how does this go together? Well, the HALIO founders cleverly devised a new manufacturing process where they can coating, a cathode coating to very thin display glass coated with transitive conductive oxide. They will take those two pieces of glass and then they'll sandwich it together with an ion conductor in the middle. This probably sounds very similar to maybe a lithium-ion battery, and that's exactly how it works. You apply a charge to the device, and the glass will change state in according to that electrical energy. To clear the glass, you extract that charge, and we deliver a really nice, dynamic, durable device that can be laminated into any glass unit. This is a cross-section of a HALIO dual pane insulated glass unit. HALIO is the expert in the tinting technology that gets embedded in the outboard light of that dual pane insulated unit. We partner with high quality glass fabricators, and our primary glass fabricator in North America is Viracon. So with this configuration and new manufacturing processes and the way the device is fabricated, we're then able to combine our technology with any other high-performing technology, low-E coatings to deliver, the design intent and beautiful glass. We can improve U-value performance by going to triple pane and even maybe incorporating a VIG element like the Vitro Vacuum Max that we'll hear about later this afternoon as well. So how does HALIO work? Well, we have a sky camera that's on the roof that takes a picture of the sky every 30 seconds. It senses illuminance in the local environment. We process that intelligence in the cloud. We then will set the right tint on the glass. Every single window in the building will get the right tint at the right time. And then we have a closed loop control system to continually respond, analyze, sense, so that occupants are always comfortable. The building is maximizing its energy performance and energy saving opportunities. For multifamily projects, this is also a selling feature that you could leverage. You can enable your occupants to control their glass. Just imagine saying something like, "Hey Alexa, tint my windows." And within seconds, you'll see the tinting of the glass change and occupants are significantly more comfortable. The core of the intelligence system is our rooftop sky camera. We have a HDR camera on the roof that takes a picture of the sky every 30 seconds. We analyze cloud formations, what will happen in a few minutes, and we will set the tint on the glass accordingly. So HALIO always sets the right tint at the right time. We're able to do that because we have fast tinting, responsive smart glass technology. Coming soon, SeaTac Airport. This is a very interesting project because it also has a sawtooth-like facade. And so we supported the design team with understanding daylighting and modeling and how the tinting performance and technology can really elevate the occupant experience at this airport location. This project, Williams Parkway Fire Campus in Brampton, Ontario, has a grand entrance as pictured here. If there was no dynamic glass on this facade, this space would become a really hot box in the summertime. With dynamic glass, this becomes a very comfortable occupant experience. And one more project, the Cooperators' new corporate headquarters in Guelph, Ontario. The Cooperators have a bold sustainability goal. They are the first to zero carbon design, plus WELL, plus LEED Platinum. And so HALIO is a big part of their sustainability strategy and their occupant experience. They want to deliver the best office experience for their employees, and HALIO is a big part of that. So my colleague Del Bankston and I are here today. We have a little booth in the back. We love to come and talk to you and show you HALIO smart glass technology in person and how fast our glass technology tints. And so thanks for your time and attention, and enjoy coffee.
Well done, thank you. So again, if the presenters from the first group could please come up to the front for a quick photograph. And then we'll be back at 11:05, so get it in you, get back. We've got a great program to come up. Thank you. Thanks to everyone in the room who got their coffee and their food. And I just want to apologize for the quick start and a bit of the delay. Thank you for going with us. We might have to shave a bit of time off these presentations or eat into your lunch. Please, if you're hangry, I just went to see there's no more food outside, so I have some trail mix if you're really, really gonna lose it. But you're not allowed to eat in here, so do remember that. I just wanted to say it's the utmost importance is actually the acknowledgement of the land that we're currently gathered on. We got started so quickly that I didn't get to do that. So I just wanted to acknowledge that we are gathered on the traditional, ancestral, and unceded territory of the Coast Salish people, including the territories of Musqueam, Squamish, and Tsleil-Waututh nations. And I grew up in Victoria and I live in Vancouver, and I'm very grateful to be here. So anyways, I want to start this next session off with a couple presenters, Bryan Lemos Beça of OMB and Tim Wong of Entuitive, and they will present on the contextual facades of heritage vertical expansions. Exciting.
Okay. Can you hear us?
Next, back.
Yep.
This is a clicker. Okay.
Perfect. All right. I think we're a go here. So thank you, everyone. Thank you, Heather, for the introductions, and looking forward to talking about this unique projects with you guys today. So just to start us off, we're going to be actually talking about the 837 BD Street project here in Vancouver, and really looking at the contextual facade approach when designing with a heritage building. Just to give you a real quick primer on who we are and where we're coming from, as well as the greater team. So myself at Intuitive Consulting Engineers, we're about a team of 270 plus engineers and designers and consultants. We have 6 offices in North America. And then Bryan, my colleague here, is at Office of Mcfarlane Biggar, who are the integrated design practice of architects and interior designers. They have about 50 plus team members and 2 offices, both on the island and in Vancouver. Also want to acknowledge that there was a larger, greater team that was a real pleasure to work with and collaborate throughout this whole process. And so there's a lot of gratitude to all the other team members on this project. And with this, I will give it over to Bryan to start us off telling the story.
Great. Hi, good morning, everyone. So we're going to start by telling you a little bit about the contextual facade approach that we took at this project, and that requires having a bit of an understanding of the context that we were working in. So we're going to give you a little bit of historical and contemporary context, and we're going to talk a little bit about how that context creates development pressure on heritage sites and what kind of risks and opportunities come with that. We'll talk about the approach itself and some of the objectives and challenges that arose from it, and then we'll finish with some lessons learned that we hope will be useful to you if you take a similar approach at your own project. So the project at 837 BD Street, it's a 1911 brick and beam warehouse located just near Yaletown in downtown Vancouver. It's part of Block 68, which is this really distinct, fully intact block of Edwardian warehouse buildings. The street wall itself is very cubic and muscular, so it's got a very kind of solid presence on the street. And our particular building, which you can see in white there on the right, is the shortest building on the block. It's despite being at the highest part of the street. And it's the product really of this fascinating kind of boom time in the early 20th century in Vancouver. With the anticipation of the opening of the Panama Canal, there was investment pouring into the city from all kinds of different places, and primarily in the form of warehouse building construction, anticipating needing to store, distribute, move goods from the port. And at this time, as our heritage consultant talked with us, buildings were going up so fast that sometimes they would permit a building, they would go in to amend that permit just a couple months later to expand the size of the building. And so we see those expansions sometimes took on a couple different phases, and there's examples throughout the city. There's a couple here at the Hudson's Bay Company original warehouse at 321 Water Street, and there's an example at 576 Seymour Street where those expansions were built a few years apart. This building was one of those kinds of buildings. It was originally permitted at 3 stories, so it's 2 stories from the street, 3 stories from the lane, but their ambition was actually to build another 4 stories on top. And unfortunately, the First World War happened and kind of halted that whole boom of building at this time. And so that expansion never materialized, and the building kind of remained at this modest scale. So we can, in the lower image, you can see the other end of the block with the larger buildings that were constructed during the boom. And what that meant was the site actually evolved into being quite an underutilized site. So we actually studied the density of Block 68 as a whole and found that this particular site was the least utilized of all of the sites on the block, with an FSR, which is the floor space ratio or measure of density, of only 2 out of the allowable 5 or 5.5 with a heritage density bonus. And that underutilization meant that the project also wasn't providing as much employment space as it could have. And it's situated in a neighborhood that for the city is a priority area for economic development. So really providing job space is critical to the ambitions of Vancouver. And that combination of low utilization and high potential creates a lot of development pressure. And that development pressure can be a positive thing because it kind of drives economic growth in the city. But when it happens in heritage districts, it actually creates a little bit of risk for us as well. Because how do we then deal sensitively with having to densify on heritage sites? And when we think about how we expand heritage sites, especially on tight urban sites, that expansion typically takes a vertical form. And we see 2 predominant approaches to vertical expansions on heritage projects. The first one is what we kind of call the setback and hide approach, which is more or less what's built into a lot of heritage policy. The ambition of that approach is to preserve the experience of the heritage neighborhood from the pedestrian level and pretty much to make the expansion functionally invisible from the street. And so it has its uses in particular areas, and we see that deployed in Gastown quite extensively. But its limitations are that you can't provide that much density, and not providing much density means it's harder to achieve the economic requirements of the pro forma that the developer will have. And it also limits how much you can satisfy the objectives that the municipality might have for the area. It also doesn't participate in the present, which is something we could talk about, but from our perspective, that's a little bit limiting as well. The other approach we see a lot is what we call the cinched waist, which allows for larger expansions, typically several stories on top of a project, with that first floor above the heritage structure being kind of deeply inset from the edges, providing that clear distinction between old and new. So you get that clean break. The benefits are you can get more density. The limitations are it's tougher to be structurally continuous because you typically have some kind of transfer slab at the original roof level, or you have to sister structure going down the building. It could be maybe material compatible, but we typically see it sort of deployed as a glass box over top of a heritage building. So what we wanted to do was take a more site-specific approach here, and we really drew upon the original design ambitions of the building from 1911. So they actually had the foresight of pre-installing all the windowsills at the future level 3, which was quite interesting. And they had put a parapet on the building that was intended to be sacrificial, which would be removed when the expansion was completed. And had it been done at the time, it probably would have been completed in a very similar Edwardian design language. It never happened, so what we decided to do was, well, let's take that same idea and actually bring it into the 21st century, be structurally continuous with the heavy timber grid, and come up in a very similar fashion. The problem with this is it's not really condoned by heritage policy, so it was an interesting conversation to have. But it allows us to tell a really cool story about old and new, because we can actually complement the original heavy timber with modern mass timber. And in the case of our floor construction, we're actually using the exact same thing that they did 112 years ago, which is nail laminated timber. So you can start to tell this really nice continuous story from between old and new across 2 centuries. So because we were doing something a little unusual, it became really important for us to prove to the Heritage Department that we were in compliance with the standards and guidelines for the conservation of historic places in Canada, which, if you've done any heritage work, you're familiar with these guidelines. They're the primary document that heritage consultants and departments use to evaluate projects. And when it comes to additions, there's Standard 11, which has 2 key criteria: that you have to preserve the character-defining elements of the original building. But anything new you do, you get this kind of paradoxical statement where it has to be physically and visually compatible with, subordinate to, and distinguishable from the historic place. And our team joked that I should have a t-shirt with that made for me. So that led us through this really rigorous study of the building, particularly looking at proportion and materiality, and trying to find the original logic and order of the building so that we could express a 21st century addition that was not mimicking in any way, but was congruent with what had been done before. And so that included using things like expressions of mass and depth, durability and solidity, but also achieving openness and lightness that's important for contemporary office spaces. So we used a buff brick that's materially compatible with the original red brick masonry, but of course different in its color, and precast concrete bands that provided a horizontal expression of each floor. We also studied the character-defining elements of the exterior and tried to reinterpret some of those, including these really interesting bird's mouth corner details. And one of the primary expressions was really maintaining the street wall flush with the rest of Block 68 to really stand in solidarity with the other buildings. So that approach got us unanimous support at the Vancouver Heritage Commission and had particular objectives. We wanted to be materially compatible. We wanted to achieve depth, mass, and integrity. And when we say integrity, what we really wanted was, we wanted brick to behave like brick and concrete to behave like concrete. So we wanted an honesty to it. And we wanted openness, transparency, and light. And we also needed the facade to perform at a high level. And that brought with it a series of challenges. So I'm going to turn it over to Tim to walk us through those challenges.
All right, thank you, Bryan. So looking at those challenges, I think just to highlight some of those key aspects and how they translated to issues that were maybe conflicts or studies that we had. Specifically, we were looking at creating that depth, or that reaching out from the structure to support the facade elements. We definitely looked at like recessing the glazing line so that there's a hierarchy from the mass and the opaque elements in the facade. And ultimately, we wanted to manage all of these sort of articulations with air, moisture, mitigating thermal bridges. And ultimately, when you look at these combination of assemblies, are there advantages or disadvantages to site-built construction, or maybe even prefab construction? So as we started this project, or looking at the performance of the envelope, we did have targets in mind, and really those were dictated by how we were modeling the project from a whole building perspective. So we did have our strict TEDI and TUI targets, as well as our greenhouse gas emissions. So following that, we're looking at the City of Vancouver Bylaw 2019, Part 10. We're also achieving our performance targets with knowing that our building is connected to a low carbon energy system. That sets the stage to start to distinguish what each of our envelope assemblies are doing. And in particular, we had to manage the fact that we were also dealing with the heritage performance. And in that sense, with the energy model, there was many discussions with the city in terms of organizing how do we treat the heritage component in this addition, and what value and what performance does it play. So our concern was that we never wanted to reduce the performance of the new addition by taxing it with the heritage structure, knowing that the heritage requirements wouldn't require a necessarily upgrade to the current level of performance that we have for new construction. So in that sense, there are distinctions of where the envelope is reduced to meet NECB 2015, and the new envelope is also meeting those targets for the TEDI. Getting sort of the glazing done first. In terms of, we're looking at a performance glazing. In this case, we did evaluate triple glaze and double glaze systems to kind of reach different targets. However, we did find that given the cost of triple glazing, it actually was a better lever for us to stick with double glazing. And in particular, in this case, we tried to conceal the glazing in some ways by recessing it back from the mass elements. So all the glazing, as you note in this detail, will be maintained and installed from the interior. What that does is creates a clean discussion or language between glass and brick. Looking then at the sequencing of the opaque elements, it was important that we had this sort of hierarchy between brick and precast, specifically because what we were looking at doing was supporting the brick off of the precast components. There were a number of sort of iterations and discussions had with precast manufacturers on how do we achieve this, how do we shape this, how do we connect back to the mass timber structure. So all these components coming together were often a discussion point. And specifically the brick shelf support and the tie back to the slab edge was where we spent a lot of our time. So looking at those slab edge components, ultimately we knew that we were interrupting the insulation and that we were going to be reducing or increasing our heat loss through that slab edge. So one of the first mitigation strategies was to introduce a thermal break. And in that study, we did we noticed right away that with those 3 anchor connections happening at every precast horizontal band, we were able to reduce our psi value by a decent amount to impact the model. Looking at the brick support methods, specifically the brick is varying because of that discussion of language on the facade in terms of proportions and scales. The brick piers are changing in widths. And so we did need to look at a strategy of supporting each brick back laterally with different tie-back methods. So other than doing a straightforward sort of cable tie or pin tie connection, we would look at doing a full plate support, which through conversations with Faro Corp, it ended up being a very advantageous connection back to the structure. So as we get into evaluating each of those pieces and we started looking at those details and it started affecting our overall performance, it's important that we really do calculate all of our effective clear field. As you all are aware, we're really tracking each of these area weighted assemblies, and then we're proceeding with applying the thermal ridges. So you can see that these are the sort of targets in reaction to our TEDI compliance. And then these are some of the impactful connections. So today we kind of hovered over the biggest topics or the biggest contributors or impactful moments in the facade, right? So as you can say, the glazing interface to the wall is really one that is taxing on our heat loss throughout the building. The precast band connections are very significant in that sense. And so each of those detailing discussions had to respond to that percentage or impact. And so one thing that I wanted to bring up is that the process of the detailing was definitely one that was informed by a series of iterations. And often enough, we did have to revisit through costing exercises on where could we get any advantages through prefabricated components. So there was an extensive cost benefit analysis with Etro, our partners there, during a pre-construction stage to really evaluate, could we design and still meet the intent of the heritage articulation by also trying to prefab or maybe modularize some of these components of the facade. As we all know, or maybe what we tend to know is that if we do prefab, that means that we can start early in the factory. We can reduce some of those times in construction. We can ultimately end up reducing our full timeline. That's our assumption that we would go forward in when we start talking about prefab. However, through some of the discussions and the analysis, the scale of the project, we started to find pros and cons and cost implications that steered us one way or another. So just walking you through what we did evaluate, we evaluated the traditional method, the site-built masonry and glazing. With all these components, as we know that's a lot of trades on site. There's a little bit of coordination. There's also a lot of interfaces that happen between different players. Looking at modularizing just the opaque elements through a lightweight, thin brick adhered to a precast panel. We did look at this as an option. However, it didn't respond very well to, I think, the honesty of the brick going with a thin brick approach, but it also created a number of joints throughout the facade that were not responding directly to the scale or the modularization of the face. Ultimately, also looked at unitized curtain wall by integrating opaque elements. However, that did push us to creating less of a recess, right? It took away some of that depth and that distinction between opaque and glazing that we were really striving to achieve. And to respond to that, maybe unitized curtain wall approach that flattens the panel element. We did look at a panelized wall system, which would allow for those deep recesses to kind of be distinguished in the facade. But ultimately, this meant a heavier system, heavier panel, a lot of consideration for each of the horizontal and vertical joints. And ultimately was not one that I think the industry that was reflected in the region was ready to accomplish with the sort of heavy set a cladding assembly. So ultimately, we compared all of these together. There were various trades involved in looking at various pricing procedures here. And because of the scale of the project, really the three-story addition, because of the modularity, because of the heritage context that we wanted to strive to achieve and respect in that sense, ultimately the site-built masonry glazing approach was the cheapest, the most economical approach, but also the most responsive to the context of our design. So when we start to look back at that chart, the assumptions that we had really in terms of saving times in the construction timeline actually didn't outweigh the cost and the direction of the design intent. And it also, what was interesting through all these conversations was it really made us start to question and ask ourselves, how do we design with an intent with the same material, but in a new context, having new project requirements from a thermal comfort perspective, from an overall building comfort perspective, and just also the sort of trade comforts, as well as what are we used to designing this day and age, right? And I think, Bryan, you have a good way of sort of bringing this together in terms of how that responded from an architectural perspective. So I'll pass it back.
I mean, for us, it became this really interesting kind of essay and study in how do you build with brick across 2 centuries. And, recognizing with some humility that the folks who did this in 1911 had a particular set of concerns, a knowledge base, particular requirements they were trying to fulfill, and ours are quite different now. We expect a brick wall to do a lot of different things. Not all of them are the same as what they were doing before. And I think that what was fascinating for us was just to try to understand that and recognize that we could have a dialogue between those 2 pieces, same materials, but bringing that brick wall into the 21st century. And so we have just a few slides of some images of the building as it will be completed. It's under construction right now, and we expect it to be finished in early 2025. So we'll just run you through some of the images here. And we'll just finish with an acknowledgement that making a project like this takes a very big team, a very big and committed team. So we just want to acknowledge from our 2 respective teams, all of the people who've contributed to the project and how much we appreciate all of their effort. And also just to keep the conversation open, if you're ever interested in talking about what it means to build with brick, I want to talk more about contextual facades or any of the approaches here, we're definitely interested in talking about it and could talk about it for many hours, probably longer than you would like. So thank you very much for your time. Appreciate it.
Thank you.
Thank you. Thank you both. We just have a quick minute here before the next presenter comes on. So, little audience participation. I'm just curious, how many people are here from out of town, like traveled to come here and are staying in Vancouver? 1, cool. 3, okay, great. Okay, there's some more people. Vancouver really showed up. The weather's incredible. I think, unfortunately, we have some forest fire smoke, so if you are here for the long weekend, try and get out to see some things. There's some pretty iconic facades in town, and it's not a very big city, so take a walk and look at some of the projects that we're talking about today. I also wanted to take this opportunity to plug another event. I'm on the BC Building Envelope Council. That's another local industry here, and we have an event on May 24th, which is next week, at the Italian Cultural Center. Delicious food and a great venue, and it's a half-day workshop, and we're hosting it with BC Housing, and it's about enclosure and mechanical systems and overheating mitigation. So it's going to be a very good event if you're in town or are going to stay to see that. I believe the registration closes next Tuesday, and it's about $120 for non-members, and there's discounts for students and members. So if you're interested, please come and see that. It's focused on enclosure and mechanical. So, are we ready, Ahmed? Okay, great. Maybe a little bit more audience participation. How many? I'm curious to know the mix of people here too. Architects, do you mind raising your hands? Great. Engineers. Okay, awesome. Manufacturers. Cool. Any policy makers? That would be good. Maybe next event we could get some policymakers in here because they're part of the conversation too. But yeah, take an opportunity at the breaks to mix and mingle. I know it's difficult, especially I'm an introvert, if you can believe it, and this is like the Everest of social interactions. But please mingle because there's a lot to accomplish in building new and renovating buildings, and we need to work together. So I think we're ready to introduce our next presenter. So we've gone from contextual facades to customized facades using bespoke aluminum solutions. And this is presented by Teodor Caragioiu, a project engineer at Rayner's Aluminum. So please join me in welcoming Teodor.
Hi, everyone. Yeah, good morning, everyone. My name is Teodor Caragioiu. I'm a facade specialist at Rayner's Aluminium, working as a project engineer in the International Projects Department of Rayner's Aluminium at the headquarters in Belgium. It is a pleasure to be today in front of you to give you a brief presentation of what Rayner's Aluminium represents and how we are supporting our clients and how we are supporting special projects from concept phase throughout the completion. I will use the clicker maybe. Good. Rayner's Aluminium is being a leading European specialist in engineering, developing, and marketing of aluminium architectural solutions. Our goal is to increase the value of buildings and to enhance the living and the working environment of people worldwide. One moment, please. Our business model consists in providing off-the-shelf all the components, highly engineered facade systems needed to assemble the final product. So our fabricator is our partner. We are sharing the know-how by training them in our facilities in Belgium and by paying them regular visits to their facilities to guide them through the logistics and through the fabrication process. And we are therefore making sure that the final product is up to the intended level of quality and performance when it reaches the end customer. Here we see a nice aerial view of the Rayner's Aluminium headquarters in Belgium, with more than 500 people employed here. In our engineering department, departments are working more than 100 engineers to develop and engineer these systems. Reyners Aluminium is a family business established in Belgium in 1965. For over 50 years, Reyners clearly and consistently focused on the corporate values, innovation, excellence, loyalty, and respect. Those values are the fundamentals of our company and the driving force of our successful business approach. We have a strong presence in Canada for more than 4 years, working closely with several partners. Reyners Aluminium Canadian subsidiary is the fastest growing among all markets. We have a well-established local team in Canada serving our clients and partners with plans to invest in an even stronger presence in the years to come. We are currently also involved in early stage design for several high-profile projects in Canada, providing strong support technically and logistically to our local team in Canada from our headquarters in Belgium. And next, I would like to introduce you to the workflow process we typically take to support a project from the concept phase throughout the completion. The Quad Business Center is located in Malta. It's the smallest European Union nation, with the tallest tower standing 19 stories high and 92 meters or 300 feet tall. The facade system total surface is in excess of 33,000 square meters or roughly 355,000 square feet. Every project study begins with a transmission of the architectural design intent and the expected performance levels, performance requirements. We were involved in an early stage in the project. Therefore, we had the opportunity to collaborate closely with the rest of the trades, like concrete structure builder, like the tower crane company, like HVAC company. For this project, the performance requirements were significantly high, starting with the wind load resistance to water penetration and air tightness, thermal performance, and finishing with the seismic movements and live loads that needed to be accommodated by the facade system. We received the building information module of the building, which enabled us to integrate it into our Avalon 3D visualization cave, where the stakeholders could visualize their project in a very early conceptual phase. Sorry, the time is so limited and I do not have time to integrate some of these slides in this presentation. Malta is known for its powerful Mediterranean gusts of wind. In fact, the wind tunnel test report simulation revealed wind pressures of up to 4.5 kilopascals. That's roughly 92 pounds per square foot. This provided the information we needed to perform the preliminary static calculations and determine the section properties and the design of the system with the correct profile inertia and sizes. The proposed system is a male-female facade system widely used in North America with a straight cut butt joint screwed assembly, which works pressure equalized, already proven on other high-rise projects, and tested thoroughly in several performance mock-up in our testing laboratory in Belgium, in Duffel. By the way, our laboratory testing center in Duffel, it's the largest privately owned test center in Europe. So yeah, we have this advantage that we can test all our systems and project solutions in-house, and then when needed, we just bring certifying bodies to have official certifications for these tests. This system also incorporates opening elements like top-hung windows and integrated sliding elements in the most minimalistic way possible, while keeping the focus on the thermal performance of the system and trying to avoid thermal bridges. For this solution, we extruded 30 aluminum profiles, 4 plastic profiles, 2 molded PCs, and 9 gasket extrusions. So basically, we created all the Lego components that our fabricators need to put together to end up with the final product. One of the design requirements of the project was to have a global system throughout the building that can be installed both as a curtain wall and as a window wall. Curtain wall is in front of the concrete slab, window wall is in between the slabs, as well as a window wall, window wall between the slabs. For this purpose, we generated a 3D model to demonstrate the connection nodes and to help the installer visualize and establish a strategy for closing and waterproofing the envelope of the balcony slab edge protrusion through the facade system. For the window wall installation, we designed a starter profile with an identical shape like the top transom of the curtain wall system, but without the box cavity underneath, there on the left-hand side, so that you can place it as low as possible in relation to the concrete slab and lower the finished floor as much as possible. The sliding door element is designed following ADA regulations with respect to the maximum rise, slope, and gaps, so that disabled persons could access easily and safely the external terraces. We prepared 3D models for all the typical panels we designed for this project to help the customers visualize and the assembly and streamline the fabrication process. What you see here, it's a typical panel cutting and material list to be provided both to the fabricator, but also to be integrated into our Reina Pro software for panel configuration and cutting optimization and material takeoff. A typical drawing indicating the drainage, ventilation, and decompression drillings and cutouts to support the fabrication of the elements by our fabricator partners. As mentioned, 3D models, assemblies containing full machining and profiles preparation for assemblies were made for all panel typologies. From these models, we were able to extract each individual profile and prepare detailed machining drawings so that they can be programmed into the CNC machine of the fabricator. So basically, all they need to do is just place the profile in the CNC machine, push a button, and then the profile comes out exactly as it needs to be to assemble the panels in the final shape. We also provided a full hardware set layout for the opening elements, containing the correct hardware like friction arms capable of holding up to 180 kilogram vents, as well as laying out the position and number of the locking points needed to extend the safety wind load of 4.5 kilopascals or 94 PSF. Thermal simulation models were also prepared to determine the U value of the thermal joints. With this information, we put together calculation spreadsheets for all panel typologies based on the size. So basically, those are 3 input sizes right there in the Excel file. You just put the size of the panel and automatically the U value calculation is adapted to the size of that panel. To calculate the global UCW value of the entire building envelope. So once you calculate the UCW for each panel, you put all panels together, you do average weighted calculation for the thermal value, and you end up with a complete building envelope UCW value. As mentioned earlier, we performed wind load calculations using a space frame software for a significant section of the tower with the largest wind pressures. A determination of maximum deformation and maximum stresses was made to confirm that we were in compliance with the relevant regulations and the local standards. Building connections were fabricated by our fabricator, our partner in Malta, but they required our help to design building connections suitable to be applied to our aluminum system and to be capable of transferring safely these loads to the building structure. From the space frame structure analysis software, we extracted the maximum reactions that we have on these building connections. And then we proceeded with this information to prepare detailed finite element analysis. We did the same for the top Malian building connection brackets for the window wall system. And ultimately, all the static and structural analysis simulations were validated by an external engineering office. The design of the curtain wall building connection brackets were provided significant allowance for brackets adjustments on all axes. So you have quite a lot of adjustment possibilities, back and forth, left and right, and up and down, up to maybe 50, 60 millimeters probably. But even with the large adjustment capability, once the entire facade is installed to the building, it becomes very challenging to re-level the panels for secondary slab deflections when they happen in the building. So in order to account for that situation, normally what's happening in a building, you have probably 70-75% of the slab deflection happening immediately as you apply the dead load of the facade system. Okay, so that's the major component for the slab deformation. We therefore prepared a detailed study together with a concrete structure subcontractor, which provided a finite element analysis of the slab deflection during the initial facade installation, life loads and concrete creeping as well. Following this study, a decision has been made to cast the concrete slab with a pre-camber. Pre-camber is practically a counter deformation of the concrete slab to account for the initial slab deflection under the facade dead load. Then the subsequent secondary slab movements were much easier to accommodate by the panel stack joints and system movement capabilities. In Malta, they actually had exactly the same type of constructing concrete structure, very thin slabs, a lot of columns, not so many beams, so the concrete slabs deflect a lot. The curtain wall building connections were thoroughly tested at our laboratory in Belgium to ensure that there is no failure or plastic deformations in the brackets material up to the safety wind load requirements for the project. And some photos with the installation of the building connections on the performance mock-up on the top there, or the project site on the bottom photos. We then prepared 2 visual and performance mock-ups to be tested in our technology center, the largest privately owned facade test center, like I mentioned already, in Europe. We prepared a 2-story high mock-up for the curtain wall area, here on the left side, and 1 single story for the performance mock-up for the window wall on the right-hand side, including the largest size of the sliding element we had in the project. With this occasion, we invited the Maltese fabricator team to assist and receive training on the fabrication of the test elements. This also served as an assessment of the fabrication capabilities and skills of the workshop team, which proved to be very satisfactory in the end. Some photos of the installation of the plastic molded covers that close the cavities of the vertical frame members as we milled them open to make room for accommodating the frame of the opening elements. So basically we designed this with a very minimalistic integration of the opening vent. It's really flush. You don't see, when the vent is closed, you do not see that you have an opening window in that location. We carefully glued the inner glazing gaskets and sealed them at the ends to prevent water infiltrations and water to travel underneath the gaskets along the gasket channels. We then transferred the frames to our local Belgian glass processor, who demonstrated the structural bonding of the glass to the panel frames to the fabricators from Malta. We continue with the installation of the 180 kilograms or roughly 400 pounds vents into the panel frame. So you can see we used a vacuum lifter and a bunch of guys installing all the friction arms right there. The completed panels were then hoisted and installed to the test wall. A second installer's team from the Maltese fabricator visited the facilities to receive installation training for the finished panel. So the workshop team received the fabrication training, and the guys on site, they received the installation training for these panels on site. All right, application of the final air and water barrier. A big advantage of this system is that the sealant can be applied after the facade system is completely closed, so that the extreme outside temperatures do not affect the curing and adhesion of the sealing agent. And mostly this is a huge problem in very cold countries, because the sealing agent does not work below 5 degrees Celsius. You put it, but it doesn't do anything. And it does not work above 40 degrees. So in hot countries, again, you cannot use it until the temperature drops down. And yeah, applying it once the facade is completely closed and being able to control the inside temperature, it's a big advantage. The second window wall mock-up installation was placed on a different test wall and tested to the project performance requirements as well. And upon successful completion of all the testing sequences, a control dismantling followed. So we removed all the panels, we placed them on the floor, and they were evaluated by the third-party independent certifying body for any possible hidden damage that may have occurred during the safety wind load of this test element. Then the fabrication started in Malta. We visited the fabricator facilities to make sure that all the information is available, all the steps and procedures are performed as instructed. Some photos from another follow-up visit to inspect and further advise on the fabrication workflow. For this project, Reyners Aluminum provided powder-coated profiles with a paint adhesion to the aluminum substrate certification performed directly by our surface finish supplier in Belgium, following a specific certification procedure. So basically, they cut samples out of every painted batch. They were tested in the laboratory for paint adhesion, and then when all the samples passed, these profiles were stamped every half a meter as certified for structural bonding of the glass to these profiles. However, the structural silicone adhesion to the paint must also be very well documented, and specific batches testing procedure for the structural silicone gluing to be performed as well. This falls under the responsibility of the fabricator, who documented carefully every single batch of silicone bonding. So every day they started a siliconing process, and they were preparing the mixture of the structural silicone. They would take this kind of samples, and they would do 3 kinds of tests. Snapping time test, butterfly test to check the homogeneity of the mixture of the silicone, and finally the peeling and adhesion test, which we can see in the next slide here. So what you see here, it's called a Roman scale, which applies a specific tensile force on some specifically designed samples to test the peeling and adhesion of the silicone. And yeah, the target is that the samples are passing, you apply the load that needs to be applied and nothing happens. But eventually, yeah, you also have some failures sometimes in the silicone, and then you know, okay, this batch is not good. We have to redo the mixture. We have to prepare again the panel bonding. Of course, the desired way of failure, it's what you see in this picture here. You want the fracturing to happen in the mass of the silicone and not the silicone detaching cleanly from the surface of the glass. That's a horrible failure in this case. All right. We also did visits on the construction site where we performed, we went at the beginning of the project, but also at later stages, both to confirm that installation is done according to the prescriptions, but also to discuss how to address complex details on site. Photos from the inspection of the window wall starter profile, ceiling and drainage, and the inspection of the fire stop installation between the slab edge and the panel frames that you can see on those photos on the right-hand side. A nice drone video showing the progress of the project, but click. No. Maybe click here. No, nothing happens. Maybe if you exit the presentation screen, it will run.
No, I think it's not. I don't know why.
Okay. It is what it is. It was a nice fly around video with a drone. All right. So for this project, all the corner panels profiles were curved by a specialist bending company in Denmark. And also the glasses were supplied as well from a large Spanish glass processor, and they were curved using a hot glass bending technology. So all the corners of the building are done with curved glasses. Yeah, and I will conclude with some more photos. Nicely synchronized shot right there. Okay, and finally another drone video showing the completed project, which probably will not run. Yeah, it's a pity. It's fine. right, so this concludes my presentation. I would like to thank you everyone very much for your attention. Thank you.
Thank you, Teodor. That was excellent. Yeah. I've always wanted to go to Malta. Now I know what to look for when I'm there. So we have one more 30-minute session, and then we have a panel, and that would conclude the second session, and then we're into lunch. Our next presenter, it's another exciting design case study, 601 West Pender, a new paradigm. Peter Krouse will be presenting, and he's of KPF. Are we ready?
Yeah.
Okay. I am also curious, and maybe we can chat at lunch if you see me out there, about the facade access consulting, or if there are any facade access consultants in Vancouver. Well, I know RJC is, but it's a very niche business, I guess. And as we build more complicated facades, I used to be one, and it seemed to be thought of kind of further down the path, and that you have to integrate anchors and stuff into curtain walls and onto roofs. So anyways, I'd be curious to chat with anybody about that on the break, just the facade access piece, because that would help at the early stages, I guess, and save time and money later. Anyways, I think we are ready for the next presenter. So please join me in welcoming Peter.
All right, thank you all. Okay, I think everything's working, maybe, hopefully. Quick introduction to who I am. My name is Peter Krouse, and I'm a principal at Cohn Pedersen Fox Architects. And KPF, who some of you may know, some of you may not know, we're a global architecture firm, about 600 people, 8 offices worldwide. And so I'm out of New York, so I'm one of those people from out of town here in the presentation. And so I'm here to talk about one of our projects here in Vancouver. We actually have several towers that have been built here. We have a number of them under design right now, both in Vancouver and in Richmond. It's been a fabulous environment for us to work in, and so it's a relationship that we want to continue. So looking ahead, okay, here's the project. This is a project right now that is still in design and documentation, and it's been moving through the process and the approvals process. This project exists on the corner of Pender and Seymour, right in middle of downtown, down towards the waterfront, which we'll look at in a minute. But it's an office building, and it's probably 445,000 square feet, 28 stories, typical floor plate about 15,000 square feet. And so it's a very compact building, modest in scale. But for us, the noteworthy thing about this is that it's a project that really allows us to explore and to take a look at what it means to build in context. And what does that mean in terms of developing facades? And those contexts are multiple, one of which is an urban context. You're dealing with a historic city. You're building modern buildings in a historic context. What does that mean? You're also dealing with a context of a climate. There's a unique climate here in Vancouver, and what does it mean to do that? So we developed a design that is trying to respond to the traditional city, the nature of the gridded facades, the gridded city, whoops, there we go, how we develop a building that has the traditional base, middle, top in response to that, but also goes a step further to try and give it a different character, not just a flat facade as in some of its adjacent properties, not just the traditional idea of a kind of classical language of stacked elements. In this case, we actually wanted to look at something that had a more dynamic quality to it, an idea of weaving and an idea of the facade that it could actually have a gesture of motion, could capture light, and in so doing then respond to the climate context of, the fact of the matter is that it's gray here a great deal of the time. So how do you create a building that then animates itself, captures light, reflects light in a different way, uses color to enliven the cityscape. So that was our charge here. Okay, as you can see, pretty self-explanatory. The building is down towards the waterfront in the downtown area. So it's a marvelous context, very, very rich context in the historic fabric, and an interesting combination of new and old buildings. And so we sort of, our work is sitting at that nexus between the two of them. Okay, here's the site, and I'm sorry you can't really read the street names on that terribly well. It's a little small, but to my point a moment ago, you can see the different kinds of facade typologies that sit in the surrounding area. And one of the interesting things, or one of the nice things, is that we also sit, you can see there's the alleyway right behind the site, Alley Oop, which I think you all are familiar with, but that's a wonderful contextual element that we get to respond to with the building. So, oops, there we go. Okay, just to walk you through some of the nuts and bolts of the building, just so you understand what it's about. Essentially a rectangular site, and so rectangular footprint to the building. And as the building goes up, we have a variety of facade conditions. So as our part of our expression of the base, middle, and top, we tried to animate the base portion and the top portion of the building with a facade that then actually had depth to it. It folds in and out. And then sits in contrast to the more planar nature of the middle shaft section. So you can see in the ground floor plan in the corner we have the entry lobby, retail surrounding or on the other facades opening out onto the street, and on the back side in the service entry, which is actually along Alley Oop. One of the nice things is our loading dock is painted, or will be painted, in bright colors to fit into the context of Alley Oop and can be used as a performance space along the alley once it's all finally completed. So moving up through the building, you can see, again, as you get into the typical shaft of the building, very simple, straight center core building, straight facades. And then once you get up to the top of the building, you get actually then the animation, the articulation of the facades at the upper office levels and in the amenity levels at the very upper floors. So building section, we have, it's all office except for the amenity elements at the top. But that you can see the facade stepping back at the base and stepping back at the top, which allows for the folded character of that. And that responds to the intended use of sort of boutique office in those areas versus more conventional office in the middle floors. Okay, facade. So the idea of weaving was something that was important for us, that we wanted to try and capitalize on. And it's for take advantage of two different things, one of which is the idea that there's an inherent sense of motion in weaving. Weaving is not static. Weaving is literally just that, moving in and out. So that implies a kind of animation to the facade. It also responds to a heritage, a historic context of sort of native traditions that would be appropriate in the area. So weaving is something that has a long history, and we're trying to bring it forward into a modern context. So our building is obviously the big one in the middle there, but trying to recognize the fact that in the urban context, it is fundamentally a gridded context. Buildings are for the most part rectilinear, and that the scale and character of the single story, single window unit, it has a particular, there's a commonality in the buildings that we were trying to respond to and recognize that. So just diagram showing then our building, if you sort of take these facades and then, in their projected sense, but you can see in the middle portion there where we actually start to distort the simple grid and introduce the weaving idea in contrast to the more planar nature of the adjacent elements. And then you can see it in the final element. So you have that sense of animation of the facade, not only in the typical shaft of the weaving of the column covers and the spandrel panels, but you also have it then in the weaving and the articulation of the base and the top of the building. So here's a rendering of what the finished project will be, and you can get a sense looking at this of particularly when you look at it obliquely, you can see the motion in the facade, and you can see that as it sets itself apart from the more traditional city. So it's responsive to it, but at the same time, it shows a kind of new interpretation to that as well. And our hope is that in so doing, not only does it give character to the wall, but it will also pick up light in a way that no other buildings in the city do, and will be something that, as we said, even on cloudy days, when there's not strong direct sunlight, still you'll understand how those different surfaces take on a different character. Okay. At the base of the building too, we're trying to respond to a varied context, scale, different components of the street, the pedestrian scale and the building scale. And so we've tried to be responsive to some of the local buildings in the articulation of the facade. And you can see down here, this is our primary canopy, which sticks out, picking up the level of the adjacent building, but also being responsive to some of the other gestures nearby on the street, so that our whole 4-story, 5-story lower podium which is the portion that's setback is picks up on the scale of the other elements in the context. Okay, and so this is just a simple elevation. I realize that there's an error in this. This is supposed to be both elevations. We actually have 2 studies of the same elevation. Sorry for that. Not everything goes according to plan, but it gives you the sense of what we're dealing with. So it is a facade expression of the folded cladding is a 2-story expression. And so that gives it a kind of modulation that helps to fit into the local context. And these are the components of it. Obviously, sitting on the structure, we have a traditional unitized curtain wall, single-story construction, and that's built to be, a high-performance curtain wall. But layered on top of that then is a 2-story expression of the articulated, textured, folded panel facade elements. Okay, and so then again, you get a sense to see how that the building in context again, and how all those components come together. Also, to note that the advantage of setting back the building on the lower floors allows for a sheltered zone to help with inclement weather for the street scale, which you see here. And the idea of trying to integrate greenery into the facade, and it occurs at several spots going up the facade, you'll see in a minute. So both to animate the street life and also to become a sort of thematic echo through the tower. Okay, so one of the things that we wanted to do, or we had to accommodate, was the desire in this building to have a DOAS ventilation system, dedicated outdoor air system, which I think many of you may be familiar with. But the idea is that you have dedicated air intake and exhaust ductwork going directly to the outside that comes into the air handling equipment, which is separate and independent from the air distribution system within the floor plate. Benefit of that is that it allows the easier treatment of the air, removal of humidity, et cetera, and is in fact more energy efficient on buildings of this kind of scale of floor plate. But what it means is that there are penetrations of the facade at every floor. And we were, while we clearly support the idea of the system, we were a little, that was one of our challenges, is how you integrate the mechanical into the facade. So this is just a simple diagram which shows the 2 types of ductwork which are up in the ceiling. This is intended to be an open ceiling, so you're looking at would be seeing the concrete slab. On the left-hand side is the standard distribution air. On the right-hand side is the DOAS direct intake and exhaust going from the mechanical units in the core straight to the outside wall and intersecting with the outside wall. So what we did is, you can see those diagrammatically, those ducts coming into the outside wall, and we integrated louvers, ventilation zones, into the facade. But we were concerned that you would see those. We didn't want to have that be part of the character of the building. So what we did is we concealed them. And the folded facade panels that are used to give the architectural character of the building also are used to mask the ventilation system. And so you can see in this diagram, and I have another one following it. But the idea is that those vertical folded panels, which are here, are actually kept off of the facade. They're bracketed out, and it allows air to come in around the side of them and then be taken in. So we have bird screens to protect it and coming in through louvers. But that way, through that sort of simple adjustment, we were able to achieve a very, very clean look and to maintain the integrity of the vertical column covers without having to have them appear to be interrupted. It's another version of the same thing in slightly more detail, and you can see that these ventilation units will occur every unit, or ventilation penetrations occur every floor. And you can see there's the top there, you can see the 1-inch gap of air coming in around the side, both intake and exhaust, to get through. We, in an effort to try and take advantage of as much daylight as we could. These are relatively tight floor to floors, in fact, very tight floor to floors. By not having a ceiling put in and having the interior space go all the way up to the slab, it gave us the ability to take the window systems and push them up as high as possible. That's helpful in getting light deep into the space and making the office spaces feel more open and more brighter and more daylit. And we have, the building has been calculated for, obviously to comply with all the energy performance requirements, the dedicated amount of solid portion of the building, which is heavily insulated to meet necessary performance needs. But then we were able to tune it so that the glazing, which is in this case is just a double glazed insulated glass, and that was done to try and achieve the benefits, cost benefits of doing double glazing versus triple glazing. And so it required a certain amount of the solid wall to help counterbalance that. And so we were able to put that portion towards the bottom, give a sill on the inside, and push the units up towards the top of the slab. So that you can see that's what the effect inside. Those would be the regular air distribution ducts diagrammatically on the inside. The DOAS ductwork is hopefully integrated with any of the partition work to minimize its impact. But this way you can see that the window units go up as high as possible and to gain the best value of light coming deep into the space. Okay. So in talking about the materials of how we created the facades, it's primarily a metal clad building, aluminum clad. You can see in item number 3 there that we also, what I referred to earlier, have tried to integrate planting into the facade. So not only does it occur at the ground level, it occurs at the canopy level, and you can also see it reappearing at the very top in all of the folded areas, so that every time the facade folds, it gives an opportunity to have greenery integrated into the facades. But the most noteworthy thing is the metal, and so to try and to express more fully the idea of this woven facade, we set it up to be a series of contrasting metals. One is a smooth metal panel, the other of which is an embossed metal panel, with the fact that those will reflect light in different ways. So that will help by having that contrast. It gives the sense of that kind of in and out movement, that weaving character. Is further expressed through that, having the contrast between those two elements. And so we looked at a lot of different kinds of metals for it, and to see what had the best, light quality, to see what would be, perform best, to see what would be economically appropriate. And what we ended up with was either anodized aluminum or painted aluminum. Both are still under final consideration. But you can see the difference between the brushed finish or some kind of satin finish and the embossed character of the aluminum panels. And so this is just a few final images of the project, and you can get a sense of what happens at the ground floor, where that that folding character creates a lower scale appropriate to the pedestrian that's further enhanced by the canopy, picking up on that same language of the folded character, all done with the same warm colored aluminum panels. So again, on a day like this shows where skies are gray, streets are wet, having that kind of warmth, having that kind of life to the facade is something that we think will be a great asset to the project. And you can see again how the sort of different characters, different material textures help to support that idea. And then I think this may be my final shot, which is just then the building on the skyline and the idea of the sort of re-expressing the integration with nature through the top folding elements of the building. And that's it. Thank you very much. Oh. One thing before I leave, just I do want to express that as I'm here as one member of the KPF team, I do want to make sure that the other key team members are recognized in this, that Richard Nemeth and Marianne Kwok, Dorina Zlateva, and Greg Mell, who were instrumental in making all of this happen. And so the project truly was a team effort. So I want to make sure they're acknowledged. Thanks very much.
Thank you, Peter, I think, for the last presentation. As we get set up here, I've had a few questions about Q&A of these presentations. Some people have booths outside, so please seek them out if you have questions after their presentation. Write them down if you got a pad, and then go see them. And other presenters, you just have to go and find. So that's if you'd like some answers to your questions. And then as we set up this panel, I just want to do some more plugs for Vancouver. For those visitors here, the food scene in Vancouver is very good. We've just had a number of Michelin star restaurants announced last year. I don't know if you'll get in on a long weekend, but hey, you could try. They're in some quaint but close neighborhoods to downtown. We have more breweries than we know what to do with, but we're trying. Brewery Creek, there's a number within stumbling distance. The North Shore Mountains, there's many things to do in Vancouver. I can give some more plugs later. But we're in continuing with the program, and right before lunch, we've got an exciting panel. So we've got 4 presenters today. Excuse me for a sec. I have to get my program, just a moment. So to close off the session, we're going to talk about retrofits, deep energy retrofits, existing buildings, which is a passion of mine. We have the moderator, Pattrick Ropel from Evoke. We have Christian Cianfoni from Ellis Dawn, Dan Geddes of Flynn Canada, and Leonard Pinalto from RJC. So please welcome our panel, and we'll see you at lunch.
Okay, so the discussion today is going to be on 3 big themes. One's just decarbonization in the context of electrification. We're going to talk about synergies between upgrading seismic performance and also prefabrication. And then kind of the final theme will be just kind of scaling up deep energy retrofits and doing it in a cost-effective manner. So just to start off this discussion, I'm going to get Christian to talk a little bit kind of the policy direction and kind of give him an overview of why we should all be caring more about deep energy retrofits.
Great, thanks. Hello? Testing?
No.
Testing? Yeah, working? Good, okay. Okay, thanks, Patrick. So, yeah, I think when it, we've been focusing, especially out here in this part of the country, on new codes for new buildings, for new construction. We've had a lot of advancements. Yeah, sure. Yeah. Okay, do this the old-fashioned way. So as I was saying, we've had a lot of advancements on building codes within new construction over the last several years, especially here in BC, and especially in this region here in Vancouver. I think what we're looking to now is what's going to happen with existing buildings and how do we regulate existing buildings. And so one of the there's a term called building performance standards where many jurisdictions across North America, some have already implemented it, like New York City and Washington, D.C., Washington State, where they start to require the reporting of energy and or carbon use in existing buildings to those jurisdictions, to those cities or states. And over time, they impose limits on how much energy or carbon those buildings are able to use with 5-year milestones. And so Vancouver just passed regulation in the last year to do something similar, a building performance standard that will come into effect with mandatory benchmarking and reporting for all buildings over 100,000 square feet starting next year, and then with having to meet certain carbon limits starting in 2026. And so that means that buildings over time who get captured by that carbon limit will have to do something to that building. We'll have to retrofit them to some extent to achieve those targets. And that number is to go to zero by 2040. Okay, so even if 2026, the number is not overly aggressive, it'll only impact probably a few dozen of the large buildings in the city. It will start to go lower on a pretty steep trajectory towards zero by 2040. And so that starts to give a sense of the scale, and it won't just affect large buildings. It'll start to, within a few years, move beyond the 100,000 square feet to buildings of 50,000 square feet, beyond offices to multi-unit residential, and so on and so forth. So that's something that is starting to happen. There are dozens more cities across North America that are looking at very similar building performance standards for existing buildings. So I think that's going to really drive the market, and a lot of our clients are already starting to plan for that, right? Especially the large real estate firms are looking at their portfolios, trying to understand what does it mean to decarbonize our existing buildings, both in terms because of corporate commitments they've made, but also recognizing that these are real regulatory requirements with significant penalties that are going to come into play. So just for context, carbon tax is under $100 a ton, and the penalties for not meeting the carbon limits in a city like New York, or what'll happen in Vancouver, is in the $250 to $300 a ton range, right? So those penalties will be imposed in those buildings that don't meet it. So there are some sticks to ensure that owners will get there. So I think those are the primary drivers. We're also hearing the province and federally coming out with the existing building code. Details, I think we don't quite know yet. As far as I understand it, it may not be something similar to a building performance standard. It may be things like time of equipment replacement. So when a building is going to undergo a major replacement of major equipment or do renovation, that might trigger them having to do it to a higher standard, whether it's mechanical systems or envelope. And so it'll look a little bit different, but it ultimately mean the same thing towards driving down to net zero by 2050 or sooner.
Okay. Leonard, can you give a kind of high level, kind of setting the stage of where the opportunities, synergies, and challenges for scaling up retrofits?
Yeah, I put together this slide in anticipation of that question. Just to reflect on the challenges that we face in trying to achieve these targets. This is one of my favorite graphs. I'm an engineer, I love graphs, but it's energy consumption per person on the horizontal axis, plotted against quality of life index, which is measured by how long you live and what education you have as a society. And you can see that there's a clear, a trend, right? The more energy you consume, the better your life is. So, right, we all know that. The highest energy consumers are, Japan, US, Canada for sure. So that's the challenge. That's the rub. We're trying to push this line in the other direction, but we all want to have a good quality of life. So we're also faced with another challenge here in Canada. We enjoy very cheap electricity. So we're not even motivated to reduce energy consumption because it's so cheap. So this is the thing that I guess keeps me awake at night, but then also gets me out of bed, pumped up in the morning to try and solve this challenge. And from an engineering perspective and from an adaptive reuse perspective, this is the sort of really high level, at the highest level challenge that we face as engineers, is to fight our very nature to want to live longer and be more educated and try and use less energy while we're doing that.
Thank you. So in Europe, there's some programs like Energy Sprung, where a lot of people at the policy level or some think tanks think you could import this to Canada, where you've kind of retrofitted buildings within weeks. I'd like to get your thoughts on that, Dan, from a contracting standpoint.
Yeah, so my involvement with Energy Sprung was for about 3 months. Loved the concept and behind it, but really found that our existing building stock is driven by different construction techniques, predominantly wood frame in the multi-family residential, and added to the fact that we're a seismic zone. To retrofit in a couple of weeks, we just could not get those loads back to structure. Again, the concepts would work better on concrete structure. Again, looking at seismic, but trying to bound basically a round peg into a square hole is very challenging. Commend for what they've done worldwide, but we've really got to look at homegrown solutions in that space.
Thank you. So Christian, kind of switching gears here a little bit, we're all here interested in facades and that, but a lot of the things that are first looked at are mechanical systems and electrical are the first things that we should do to reduce loads in buildings. Can you just speak a little bit to kind of when those kind of upgrades make sense versus doing a deep energy retrofit where you're improving the thermal performance of the building or seismic or whatever?
Patrick's outing me as a mechanical engineer at a facade conference, but that's okay. Yeah, I mean, I think the main goal of decarbonization is to get off fossil fuels. Okay, that's just plain and simple the primary goal, and sometimes that can be quite straightforward to do. I'll just give a very basic example. In my house, I replaced my gas furnace with a heat pump. The house isn't egregiously leaky, so I was able to do that without improving my envelope, without having to upgrade my electrical service. I live in a mild climate in Vancouver, so it was pretty straightforward. But in many other cases, if not most other cases, that's just not possible, or it becomes extremely expensive to do so. So we talk a lot about electrification as, getting off of fossil fuels as a way to heat our buildings and instead using electric-based heating sources. The challenge with that is, you probably heard a lot about heat pumps in the last year or so. Everybody's talking about heat pumps when it comes to decarbonizing buildings. These are devices that produce heat at 1/3 of the energy use or 1/4 of the energy use compared to fossil fuel equipment. However, they don't operate the same way. They can't spit out gobs of heat the same way gas appliances do because they don't burn stuff, and they take up a lot more room in many instances. And so in order for us to move towards a building stock that is primarily heated not with gas-fired or fossil fuel-fired equipment, the buildings need to have significantly reduced loads. Okay, there's a lot of mechanical sort of nuances that come up when retrofitting buildings, and if those loads aren't reduced, it makes the solution of electrification quite a bit more challenging. There are more straightforward ways to do it, just replacing gas-heated equipment with pure electric equipment, but then we come up with challenges of it being very expensive. Although electricity is cheaper here, as Leonard said, it's still 4 or 5 times the cost of heating with gas. And so just using straight up electric equipment can be quite expensive when we're trying to not just reduce carbon, but also operating costs for our clients. And the other thing that happens is that when you move to a heating system in a building that's very inefficient from a gas system to electric, you need a lot more power to do so, and many existing buildings just don't have that capacity available without significant and costly upgrades. So really having to improve the envelope, better air tightness, more insulation, windows, all of those things contribute to reducing that load to make that final, most critical step of electrification feasible, practical, cost effective. And so we're seeing a lot of these policies driven by carbon limits or focusing on this idea of electrification. But again, that's sort of the goal. And to get to that goal, there's several other design and construction interventions that need to happen to make that successful.
Okay, so Dan, I'm going to switch over to you. So we're going to improve the thermal performance of the building envelope on existing building. What are some things that you wish designers would think about more from a cost perspective, but also realizing the overall thermal performance that people want to achieve on these projects?
I think optimization of materials is a big one. All too often, designers looking completely at the design intent of what they want to see. Quite often we see projects that we see 60-65% utilization on those materials, and the other 35-40% goes off for recycling, hopefully. So working with manufacturers and design teams to really hone in on what is optimum use of glass size, panel sizes, and things like that. And trying various different scenarios. Sometimes you go down a path so far that you can't back out and look at a different way of going about things. And Anthony this morning with Telesocean is a prime example of that. And that project turned around to be looking the same but constructed fundamentally differently. So bouncing ideas in that space and not narrowing in on exactly what you think it should be at the beginning, and being open to ideas really helps in that space.
Can I ask a follow-up question? I'm curious, just from your perspective. A lot of buildings are 5-foot modules. Is that an optimal module?
Yeah, 5 by 10 glass is 50 square feet before you get into oversize. Composite panel systems, again, 1,500. 1,500 is a good module. We're working on some hospital projects at the moment where the floor height is 4.7 meters, but it's not divisible by any material on the market. So we're really struggling to lay system out on that floor height. So structure has a part to play on that. So you may go down a different path on material. Some panels do 12 inches quite well. So trying to optimize structure against facade and having modulation through that process definitely helps on cost and ease of install.
Okay, on a follow-up question, we'll switch to glass. A lot of buildings, when you're going to do retrofits, there's a discussion of what if I'm going to do all this work, I might as well go really big and go triple glazing and do the best I can. But there's some synergies of cost and other things they have to consider, and there's some cases maybe triple glazing doesn't make sense. I'm going to start the discussion. I'm hoping it's a bit of a dialogue and everyone jumps in, but Leonard, can you just start off with your thoughts on double versus triple glazing?
Yeah, I've been involved in projects where it's kind of gone both ways, and I know in the one project where we elected to go triple glazing, the upcharge was not significant. The big cost was just getting you there, the mobilization cost. So it didn't seem as though that was a driver. So it just made sense to do it because it didn't cost very much. In the other instance, where we went with double glazing, there was other site constraints because we were reusing the framing. I have an image of actually, might I go there? This is the assembly that was done here. You might recognize the building on Granville Street. Perkins and Will was the architect. Glass Tech with the curtain wallers, but you can see that we used a veneer system and attached a bunch of gaskets and aluminum on top of the existing framing. And in this case, we went back to what was double glazing originally, and really we were constrained by the site conditions, and the motivation to reuse as much as we could limited us to use double glazing. So I think on the energy use side of it, I don't know that there are huge gains. There was an earlier presentation, I think, where that was discussed, where it didn't seem to make a huge difference. So you went with double glazing. I don't know if there's other,
I can add to that. We've done some analysis for existing MERB where going to triple glazing didn't even move the needle from a greenhouse gas emissions perspective, but energy. And I think from an overall perspective, you need to do the analysis to figure that out. But if we want to retrofit all these buildings and we only have a finite amount of money, it's worth doing the calculations to figure out if it makes sense or not.
There's other considerations too, like sound attenuation can be optimized better in a triple glazed unit. So it's not just about energy, I guess. Occupant comfort is.
So that's a big one that's brought up a lot too. But if a lot of people in Vancouver had single glazing, if you're retrofitting a building, you're going to double it. You're doing pretty good there from sound and comfort perspective as well. But
yeah, I mean, I think it's when you're looking at carbon, greenhouse gas emissions, once you get off gas, then nothing else you do is really going to move the dial much more. So I think the question is, from a mechanical engineering perspective, even if going to triple isn't necessarily reducing your carbon number very much, because electricity is such low carbon here, it may be the difference in whether you can actually move away from fossil fuels, right? So the way we design mechanical systems, the current infrastructure in the building that's providing heat, you may not be able to do that without doing a higher improvement on the envelope. And I'm not saying that it must be triple, but it's, I often look at it not just from the perspective of what's the best, bang for your buck on energy, but also what does it allow you to do from a mechanical design perspective that's going to help you get off of the fossil fuels into a heat pump, or if you are constrained with using electric baseboard heating in some of these older MURBs, how do you get that number so low where it's not significant that they're using electricity to heat their building? So I think there's design factors other than energy that might come into play as well.
Yeah. All right, kind of switching to the theme of kind of looking at synergies and that. Kush, can you just talk a bit of some of the advantages of prefabrication for existing buildings?
I don't think I'm the right guy to ask, but I think we always hear the promise of it's faster and it's cheaper. And I think on a lot of our projects, that doesn't usually appear to be the case. And usually it's done, if it is done, it's done for other reasons. But I suppose my question would be back to the group is, what are the conditions in which that promise holds true, where it is faster and cheaper to go that route?
Yeah, so I'm going to put that to Dan and just kind of frame it a little bit more. Do you think the market's ready? There's Flynn, but there's also everybody else. And what do designers need to consider when they're considering prefabrication?
So prefabrication, I mean, that's quite a broad term. I mean, we could consider window wall as prefabrication, curtain wall, then getting into modular or large panels that are 10 meters wide by floor height. And we've done a bunch of market research in that space of what makes sense. Generally finding, of course, mass timber on new construction, but in the retrofit market, you've sort of really got to be getting into that sort of R35 effective wall, 40% window to wall ratio, and over 8-10 stories to really shift the dial on what's the most cost-effective way of going about it. If the facade doesn't need that higher performance, then I would suggest more manual techniques, swing stage, trying to reutilize the back frame section that's there. And then again, it ties back to structure. Is the existing system line loading slab, or is it point fixed balloon attachments? There'll be very specific times where modular would fit, and other times going back to more traditional construction techniques. But again, it's sort of getting into that passive house levels of performance where modular seems to be slightly cheaper than traditional. And of course, it's not ideal for wood frame either. So it's really mid to high rise concrete structure where that'll work. So if mechanical systems aren't far off getting off of fossil fuels, and you just need a bit of a cleanup on the facade, then modular is probably not a good fit. But if you're really driving that R35 effective 40% window to wall ratio, that would definitely be something that you'd look at.
Okay, so I'm going to go to Leonard, and then this is one that I'm hoping Dan's going to have a rebuttal. But can you just, Leonard, outline how a facade engineer can help put together performance specifications for a prefab project, and how does that help get competitive bids?
I think this is a good example. again, you couldn't really use prefabricated panels on this because we were looking at a way to reuse the framing system and put a veneer over top. We did try and come up with a way to use a prefabricated system. The other benefit of prefab panels, I feel like I'm going off on a tangent, but is that you can see the number of different components that are involved in the assembly. If you're assembling that in a factory, you're going to get much better quality control versus trying to put all these little pieces together on site, regardless of how skilled your tradespeople are. So the way we did this is we developed a scheme and then wrote a performance spec around it and invited a number of bidders to bid on it. And then they presented their own ideas around how they would manufacture and implement the scheme. And so I think there was an iterative approach to it. And I think the consultant plays a very important role in that because you establish your performance targets and your aesthetic aspirations, and you can outline that. And then when you invite bidders, they're all sort of trying to achieve the same thing. And then you can kind of lean into what the different manufacturers or fabricators bring to the table in terms of innovating your ideas. And so I think the consultant can play an important role in terms of establishing a consistent performance so that you can get equal bids out of the different fabricators and contractors and kind of lean into their ingenuity. I think that's really the optimal way of kind of, separating the design aspect and the building of aspect.
So to segue over to experience that Dan and I had for a project was a passive house project where the base of the design was a clip system. It's maybe similar to the Telus Ocean one, but a different project where there was a preconceived idea of how it would be kind of constructed, and then the contractor came on and a design assistant, the design switched over more to what the systems they had available or whatnot, but it also helped out with the overall design. So can you just speak a little bit kind of how that kind of works with a facade engineer and a design system from a contractor perspective?
It's still in a similar vein from what Leonard said, but I mean, we had awareness on technology with the EOT clip out of Europe, right? And we tried to. It was originally designed with the Canadian-based system, but coming to it as a contractor, I mean, we wanted to win the award, right? And we saw efficiencies in using that clip instead, and it goes all the way out to 16 inches. But it's structurally stronger than most clips on the market because of the diagonal brace. So we actually use that as a contractor as a competitive advantage in a tender environment, which was a change from spec, but again utilized thermal modeling to prove out that we were providing as good or better performance than originally designed. I'm not really here to rebut what Leonard's saying about going to market in competitive environments. Good contractors like performance-based specifications. It does give us freedom to come to the table with experience that we have on our end as contractors and manufacturers. But sometimes we feel like we come to the table too late, especially in retrofit. Because we don't get the feel of the project, doing things like concrete pullouts on anchors, geometry, trying to hone in on those unforeseen conditions. Over the years in contracting, involved in a removal and replacements on facades and roof systems, the projects that have gone bad have always been the ones that have had unforeseen conditions that are fairly systemic, rusting structure. We had one with post-tensioning that completely rusted out, and pulling that apart and putting that back together in the middle of a facade renovation was extremely challenging. And ownership groups don't like change orders or delay the schedule, so it's and the teams on sites stop work. So sometimes we think performance-based specifications and the documents are complete, but being involved in exploratory and understanding the project is key to competitive bids. And you know, if every time we have an uncertainty, we just add risk factor into that estimate. So performance-based proposals, RFPs, great, but having the trades involved early is a great way of doing it.
Okay, so we're just gonna at the home stretch here in the last couple of questions. I'm gonna start off with Christian, just allowing you to kind of open mic to share some things that you think are cool that haven't kind of gained traction yet.
Yeah, I mean, it's an interesting question. Often clients will come to us and ask us, you know, we want to, they tell us they want to build the most sustainable X or retrofit a building to be the most sustainable in Canada or whatever it might be. And, you know, as you work through the conversation, you find they're looking for, you know, what are the really, what are the technologies that can be deployed that are new and exciting? And, you know, it's hard to answer that question because most of the stuff that really moves the dial significantly are the stuff that we know of, you know, better envelope, windows, air tightness, heat pumps. You know, a lot of this stuff isn't sexy in and of itself. But every now and again, there are clients who want to have those technologies. So we are seeing, you know, those deployed on various projects. We have several projects right now that are using things like electrochromic glass. And again, it's usually not energy that's the driver. It's some other client objective or vision or user objective that's driving it. Building integrated photovoltaics, another one. We have a few projects, both new and retrofits, that are deploying building integrated photovoltaics. And again, they're typically not, you know, they're more costly. They're not as efficient as rooftop. But again, there's, you know, often these are institutional settings where clients are trying to make a statement or trying to test out new technology. So I think it's great to see them. It's great to see those, you know, those, call them pilot projects or examples of new technologies. And as the price comes down, you know, the threshold for integrating them gets lower and lower. But ultimately, the things that are driving the major energy and carbon reductions are the things that, you know, we've been doing for years and just need to keep doing more of it.
Okay, so kind of the one final question that I think everyone has something to add to this is, when you're going to do a deep energy retrofit, what are the kind of the key investigations and tools that you need to do to have a well-planned project so it's cost effective and you're meeting all your targets? I don't know, do you want to start, Dan, or?
Well, from an execution standpoint, use of scanning technologies, 3D scanning, like a P40 and building point clouds, it's, you know, now you've got a fairly accurate model of what that skin is in relation to structure, and then based on exploratory, you can work out those offsets and then digitally rebuild the new facade. And even go one step further and upload, you know, that models into something like Revisto and project manage through that, which works out your clash detection and all those sort of good things. To do the dry run digitally, which we're finding on new construction, to do it on retrofit would be a huge benefit for having very little site instruction or change order and proficiency and on execution on the project in a timely manner. Especially on retrofit, you want to get in and out as fast as possible, especially if the building's occupied. So using upfront digital services to achieve that, I think, is a must.
Leonard or Christian, go ahead. Yep.
Yeah, for me, I think the key is to do, when we're talking retrofits and dealing with an existing building, you got to do fulsome investigations. You got to get in there, take things apart, work with the contractor in your investigation phase. On this particular building, we worked on this building for many years, investigating leaks, fixing leaks. And so we really got to know the insides and outsides of this system. And so that, I think, is an important part of developing a performance spec. It's not just, you know, meet a certain air tightness and water tightness and energy target. It's about specifying a performance around something that you know is achievable. So as a consultant, you kind of have to know how things are built. And I think that's one of the defining characteristics of a true facade consultant, is that you don't just know how things should perform to meet the codes. You should have a sense of how things are built. Another consideration, I have another slide here, is it's dealing with the existing occupants of the building. And the scheme that you choose will be highly dependent on whether you can evacuate the building or release all the tenants from the building and have a building that's unoccupied, or whether your building is occupied and the type of occupants and so there was a great example in one of the images I had. But so we reglazed the Blowdale Conservatory a number of years ago, and that is it's a tropical kind of environment. If you're visiting, you should go there. It's on the top of Queen Elizabeth Park, and there's 200 species of birds. So while we were reglazing this thing, we had to stop the birds from escaping, and we had to stop predators from coming in to to feast on the birds that were in the structure. So these are all kinds of great and interesting challenges that again, you may be trying to solve an energy problem, but there's so many other practical realities around that. And those are definitely some considerations that have to be made when you're retrofitting.
Yeah, one thing I was going to add, and then you can add something, is air tightness testing or tracer gas testing. We were looking at some existing buildings where you don't really know what the existing air tightness is. And if you look through all the research of what it could be kind of thing for an existing building, it could be the difference between having to do a full upgrade to the electrical infrastructure or being able to keep the existing electrical infrastructure and being able to do all the deep energy retrofits and that, which it could be like over $500,000 kind of on a MERB. So I think that's one thing that people need to kind of really think about is what are your existing loads, and if you can't touch something and you can't improve the air barrier systematically across the building, what do? You need those numbers to make an informed decision.
Yeah, I mean, the only thing I was going to add is I think there's often still a big gap between, very high level analytical, like, well, okay, we kind of know what your building has and what it needs to do to achieve its decarbonization goals, well, in order to get a really tight budget and understand exactly what's required, as Leonard was saying, all the investigations is quite a large expense. So that, clients are often in between trying to figure out how much investment do I need to make before I know that I can even retrofit this building and get the benefits out of it. So I think the more that technologies that were mentioned can play a role in sort of giving more confidence earlier on for projects to go ahead to that next stage without doing all of the work to find out if you need to do all of the work, I think is going to be important for the industry.
So how are we doing on time? You have 11 minutes? Oh, okay. So, okay, so I guess it's just kind of open discussion now. If Leonard, I'll pass it to you if you want to. You had some things that you might want to share. You have some slides here.
Image of the Blowdale Conservatory, and you can see the netting that was there. This was interesting because there was some. These are acrylic panels, acrylic blown panels, and just like any plastic, it degrades over time. And what was happening? If you grew up in Vancouver like I did when you were a teenager, you climbed all over this thing. Eventually, the acrylic became so degraded that people were falling through. So the city of Vancouver embarked upon this project to reglaze it. Is that better? So this was deemed a heritage building, which I think is great, but it's a slight irritation for me because it was built the same year I was born. So we were, but what was the defining heritage characteristic was the bubbled appearance of the acrylic. And so when we were asked to try and look at ways to improve the energy efficiency, we said, well, let's use double or triple glazing. And they said no, because it had to be bubbled. So we looked at cast glass, and that's just ridiculously expensive. And then in the end, it didn't matter because there's this big hole at the top, and I think it's 8 or 10 air changes per hour in that structure just to maintain the environment. So didn't really matter in the end. So that was just my opportunity to say how irritated I was that this is a heritage structure.
Tell us more.
It was one of my favorite projects, though, because it was a great success. Budget, schedule, that kind of thing.
Well, the other thing that we were throwing around of what we wanted to talk about is, and I think you had some insight on that, is double skin facades, and I think everybody had some thoughts on that.
Yeah, we've been involved in a few in town, and for retrofitting a double skin facade. In one case, it was just because it was a telecom building, and all the equipment was pressed up against the outside walls, and so it was cost prohibitive to do that. So the idea was to just add a second skin over top and create an interstitial space, and well, that's what we did there. I think double skin facades on new structures is a totally different discussion, and reasons why you would or would not want to do that.
Yeah, and I think you're touching upon one thing, is this, can you keep people in the buildings while you're doing a retrofit? So that's where a double skin would.
Yeah, so I guess it's, again, talking about the occupancy of the building while you're doing the work, and the type of occupants. Again, we have birds here and plants. In the other case where we used the double skin facade, it was telecom equipment, wasn't people or animals. And there was a building we did in Edmonton where the lease, they were able to evict the tenants, or most of the tenants left, knowing that this was going to happen, and there was a new tenant moving in, so it made sense to just rip the facade off and put a new facade on. So again, I think it's considerations that are unique to every project.
And Dan, you had some thoughts on that? Or?
Well, it's depending on occupancy use, you could also look at having the tenant vacate for a couple of weeks and do demolition and replacement on a floor by floor basis. You have to look at especially access systems and whether you could get rigging and winch systems from the top of the building, and it'll come down. Geometry is going to impact that, but there's more than one way to look at things, and if the contractor can remove and wrap a floor on a 2-week basis, maybe the tenants are willing to maybe work from home for a couple of weeks and things like that. You just got to put everything on the table when you look at these projects and see what's benefit for the owner, the tenants, and again, total construction costs. So yeah.
That's all my kind of questions I want. Do you want to open it up to audience, or I don't know?
I think everybody's hungry.
Yeah, we could eat. That's probably a good idea too.
We're doing great for time, so why don't we wrap it up, and
okay.
Please join me in thanking the panel here. And if you can stay, and the other presenters, Bryan and Peter, if everyone in the group that just finished, if you could come to the front for a picture, we'd appreciate it. And everyone else, enjoy lunch, and we'll see you at 2 o'clock. And we're back. We're going to get into this very quickly, but I would like to say thank you very much to the service staff. This is not an easy task, so please say thank you on your way out. Delicious food. Okay, we've got a bit of a marathon coming up. We've got 6 sessions. A couple of them are 30 minutes, 20 minutes, and then we've got a few that are 15. The first one up is Greg Borowski and Louise Webb of Merrick Architects. And then we've got Balazs Bognar from Kenya Kumar live from Tokyo on the video feed. So they're going to talk about the Alberni building. Those of you who are visiting, it's literally a couple blocks down, and it's one of the coolest buildings in the city. So I highly suggest you go take a look at it. Please come on up.
Okay. Do you want to start? Good afternoon, everybody. Ooh. Oh. We're just going to wait for Balazs to get on the screen. He's going to give you the first 10 minutes to tell you about how the vision of the building, and then we'll take you through the execution.
Okay, you can start. You can start your live.
You can be seen there live. Okay, you can start.
Wonderful.
Yeah.
That's great. Thank you. Hopefully everybody can hear me. Hello, everyone.
We can hear you.
Appreciate your patience as I'm calling you from Tokyo, Japan. And it's a real pleasure to be here on screen, and I wish I were there with you in person. The way this is going to work is I will take you through a little bit of our show and then pass over to my friends at Merrick Architecture.
Recording in progress.
It's a distinct pleasure to be able to introduce to you Alberni by Kengo Kuma, the work with Kengo Kuma and Associates and Merrick Architecture. And what we'd like to do for you today is to give you both a really deep background on the concept, but also kind of intricate detail on some of the technical aspects of the building. So before I get into some of the concepts of the building, what I'd really like to do is to share with you a few notes on the way we do things at Kengo Kuma and Associates. And as you all probably understand, Skyscraper is very much a paradigm of a kind of capitalist world, a developer model, and of course it has very much to do with the kind of maximizing of FAR and so forth. But we as optimists believe very strongly that we can do something else with this kind of an approach. And just very briefly, without going into too much detail in each project, we believe very strongly that actually the Skyscraper has much to do with the way in which it meets the ground and the invention with which it interfaces with the surrounding city. So from left to right, you can see there's always some measure of something new. And it has to do with the screen facade, a kind of integrated base, as you see in Hong Kong, Soho, and Shanghai. Rolex, Dallas avoids a kind of typical parking podium that you see elsewhere in the city, and it aligns to city views. Shibuya Scramble Square is a deeply mixed, highly mixed function, building up commercial activity all the way up until kind of a surprisingly high level. It's also connected directly to train lines. In Seattle, we also have a kind of integrated landmark and a stepped building envelope that really attends to the way that Seattle City works. And in Sydney, we've got no typical setback. It also rotates its orientation towards the view of Circular Quay north of there. And as I'd mentioned before, we're really interested in varying ways in which we engage the city, and that is how we connect to the life at the ground. And you can see here those very same towers, each having a different approach into the way in which they connect to the surrounding fabric. We are also interested in the way of the kind of detailing of the skin of each building, and you can see here our strategies are always varying. We don't really care to repeat ourselves. We also find it really important to note that for us, it's not so much about an invention of the skin, it's about the kind of presence of the volume in the way it breaks down. It's kind of the paradox of a big volume and delicate pieces. And I'll get back to that in a bit. But you can see here those same 5 projects are all manifest in different ways. I'd also like to give you a few notes on the way in which we've been able to kind of dive into Vancouver and at a very, very high level, especially since the time with you is limited. You can see here immediately, and you all are attending there in person, there's this incredible beauty of the city. It's relatively compact. It's kind of hemmed in on all sides by water, and with the immediacy of a short drive or short ride away, you can see the kind of elegance of the mountains in the background. You can see Stanley Park here towards the north of the block, and in case my cursor is showing up on screen, our site is in this stretch in through here. But just so that my mouse might not necessarily be visible, you can see here the site is marked by both the arrow and the little heart pin. This is a screen cap from Google Earth from my phone. But you can see there that the building is almost on the cusp of this incredible surrounding, this natural environment, and also the stem of the city as it kind of grows north towards Stanley Park. The building, as you can see highlighted in magenta, it sits almost at the confluence of 2 grids of the city, and it's set back a little bit from the water, but you can see there the proximity is almost immediate. And the reason why that's important is that we almost have an opportunity for the building to really kind of mark where the city tapers out and transitions into nature. And that has a strong effect on the way in which we think of the building envelope, the way in which the views start to shape it. There's almost a daunting amount of regulation and city review and so forth, and it's not necessary to go through that all in detail. But what's important for you, the audience, to understand is that it's the context of Vancouver is both this incredible nature, as you see on the left. It's almost atmospheric and kind of magical in a way. It's a kind of a mythological presence. But then on the right, you can see there are all kinds of things that we had to go through with regard to view protection, community guidelines, usage, and an overall kind of a development plan. So there are a lot of these kind of internal and hidden pressures that start to affect the way in which we consider the city. Vancouver is also distinctive in the way it's manifesting its use of glass. And you can see there's almost a kind of consistent sheen of green-blue glass. Vancouver sits in the Pacific Northwest, really beautiful, moderate climate. And so you could see there's almost this kind of allowance or a kind of permission to be able to use so much glass in this kind of typology. It's also a huge opportunity to maybe do something a little bit different. There's also kind of a final point that I like to note is that generally speaking, the city is keeping to kind of a shaping of the skyline. It sort of tapers down at the ends. And so you could see here analogous in the view above and then the section below. Alberni sits within this zone where that line is starting to descend to the ground. Let's talk a little bit about the way in which the building is shaped. And as with many projects in our office, there's a reference to or a kind of inspiration from a natural source. And you can see there on the left that's almost apt to our conditions today, something of deep responsibility. So it's with both optimism and maybe an eye towards our role as architects that this is kind of emerging. And again, this is a morphological reference, but you'll see some of the other aspects we're attending to. You can see there's a kind of reference where nature is shaping the building, or kind of surrounding environmental pressures are shaping the envelope of the tower. And what are some of those things? Well, you can follow along from the diagrams left to right. There are orientations and views that are the most critically important, and in the larger gesture, it's allowing for views from other buildings to pass through. And you can imagine the towers almost dancing or maneuvering around some of those view cones. There is an aspect of access and frontage, so how we approach the tower. And then finally, the way in which we are kind of oriented towards solar exposure, inclusion of wind and airflows and so forth, and you can see there on the right. And again, these are kind of high-level diagrams. So just to be really clear about this, the way in which this is done is that you can imagine the site is a kind of a maximized extrusion from which we subtract. And you can see there in the middle of the diagram, we start to see large Boolean scoops that are exposing the interior of the building. And for the sake of really clear explanation, you can see the blue there is the skin, is the glass skin, and we'll get into detail in a moment. And then the green is sort of the exposure of the interior, the kind of natural wood-like material that we're using. This is a rendering from our concept design stages, and you can start to see, this is along Georgia Street, looking down towards the spine of downtown. And you can see that the paint glass building and some of these others are really almost uninterrupted. They've got their free access to the view, but also what it does for our towers, we really kind of allow for new vistas and new kind of good neighbor behavior with the volume and the views. A really brief note about the structure. You can see there are models on the left and diagrams over on the right. And on a really reductive level, it's basically a conventional building. There's kind of standard cores in the middle, and there's a bit of kind of intricate gymnastics in the way in which these reinforced concrete columns are kind of bending and curving in. And it's no slight at all to our collaborators at Glotman Simpson, but that is to say we were looking for a really quite logical and straightforward solution to a relatively complex structural problem. And what this does is on the kind of floor plate level, surprisingly, the scoops and the structure allow for relatively consistent floor plates throughout. So you can see there the rainbow colored diagrams over there on the right. Those are roughly the same size. The scoops also allow for a rather broad swath of terraces on most of the units there. You can see all floors have dry gardens that are flush with the decking. There are no raised gardens, so the view is uninterrupted. And you can see here my boss and mentor, Kengo Kuma, our client and a friend of ours. Many of the units have exterior tubs. So there's a real kind of enjoyment, a really direct access to nature. And that's relatively uncommon. These large Boolean moves, these large scoops also have the effect of the ground. You can see there's a restaurant underneath in this kind of gently elevated podium. And also there's a kind of opening where the entry of the building is really a large open air atrium with some of our other kind of motifs there, as you can see. So what this does is that you can the main moves of the building have very much to do with these large gestures. They're gentle, they're curving, and they have this kind of dynamism wherein one moving around the site can get a different sense of the shape, of the morphology, a sense that there's privacy from below, but there's a real presence in the city. These are all photographs of mine during the construction process, very late stage, as you can tell, and each of these views is dramatically different. You'll note as well that the building is made up of a series of these pieces, and you can see there all of the elevations, all the facades present a different face. So that's going all the way around the building there. There is no back to the building. It's all frontage and all incredible views. I'd like to talk a little bit about the skin in detail and in some mock-up before handing over to my colleagues. A model view on the left shows the way in which this building is made of a series of pieces. So it's not just a big solid volume, it's actually a series of particles. You can see references from other projects that we've done over there on the right. It's all predicated on a 1,500 millimeter wide module. And those modules are made up of basically three things. One is glass, one is solid, and the other is louvers. And you can see some of the drawings up on screen there. They're all acting as kind of a rain screen, very, very thin kind of layer. And then of course, you could see in the photograph on the left that they provide a kind of rhythm or a pattern throughout. They're almost kind of fish scales or kind of a quilt that's floating out. These are a few images from an early mock-up that we did. My friend Louise is photographing some of the pieces, but it's really important for us to see these materials come together. Again, that's a 1,500 millimeter wide module, varying kind of glass in the mock-up, but we settled on the one that provides the kind of clearest and best combination with the solid and the louvered aluminum. And then you can see there the rendering on the upper left. That's kind of a simulation of how we interact with those pieces. Those pieces are composed very deliberately, and you can see again two mock-ups on the left. The top one shows a kind of tapering, an intended tapering of each of those balconies where the volume is scooped away. On the lower left, you could see those three materials coming together cleanly at the corner. And you can see there that the way that the pieces are overlapped reveals a very sharp, very crisp kind of definition. And again, you can see those in combination in the drawings in the main part of the slide there. Before I pass it over, I'd like to just sort of pose a question that I think has been almost implicated in my commentary, and that is, while the big gestures are volumetric and almost massive in nature, the way in which that we worked really hard with our team at KKAA and with Merrick Architecture is having to do with a kind of sensitivity or delicacy of the skin. It's not just a straightforward curtain wall that has a kind of really almost direct presence. There's nuance in the way that the light plays, with the shadow plays, the way in which we play the game with the units on the inside and the views that you get. All of this is incredibly important, and so the totality of what you see there on the right has very much to do with this balance between it being kind of a carefully developed volume and an intricately detailed skin. So with that, I will pass over the screen to Louise and to Greg, and I will stop my screen sharing here and it'll flip to more local channels. So thank you very much, and Louise and Greg, all you.
Okay, thank you, Balazs. Can people hear me okay? I'm Greg Borowski, principal from Merrick Architecture, and this is my co-principal, Louise Webb. We had the opportunity to work on this project initiated in 2015, further to a request from West Bank to work on this. We also undertook the Shore Tower Tea House, which some of you may have seen, which won a Wood Award a few years ago, which is actually on the 17th floor of the Shore Tower, but a remarkably tiny building, and that was our first project in collaboration with Kengo Kuma and Associates. So Louise and I will be endeavoring tag team to present how we achieve this project, the detailing of the project and so forth in collaboration with Kengo Kuma's office.
All right. Thanks, Greg. So we're going to give you a gallop through the salient points of the overall facade without going into too much nitty-gritty, because we'd really be here all afternoon. So Thomas Edison once said that a good idea is 10% inspiration and 90% perspiration, and this project was no different. To put it in a slightly less elegant way, it was a lot of collaboration and a little bit of compromise, which after all is what all good relationships are about, isn't it? Before we start, I think it would be remiss not to first acknowledge that Alberni is built on the unceded and traditional territories of the Musqueam, Squamish and Tsleil-Waututh nations. We'd also like to thank KKA for their vision and Westbank for affording us the opportunity to work on this iconic building. And of course, our excellent partners in crime for the facade component, for whom we can't say enough good things. Graham Construction, our construction manager, especially Rob and Lily, they may be somewhere out there in the audience, and Ilchin, now Lotta, especially Ian and Sue and Ben, hi, who are the design assist, facade contractor, and RDH, our envelope consultant. You were entertained by Bryan this morning, and FDG, who were the install crew. We spent probably 60 meetings together, even before we got the building permit, working through the details on, for what on the face of it looks like a very simple building, when in fact it's anything but. Pulling apart 3D printed details, working out where we needed another drainage hole or another flexible movement joint. And throughout the process, Ilchin produced a set of working drawings on the fly, which we molded, so that at the end of that, it culminated in a 3-story mock-up, which if I actually go backwards in the slides slightly, the image on the left is the 3-story mock-up we built in Korea. And I can personally attest to the fact that mixing up big pails of PMMA gets very hot. Anyway, back to the slides. Forward to the slides. So, as Balazs already mentioned, the main module for the building comprises a 1,500 mil wide unit, whether that be a solid panel or a glazed unit, with the full slab-to-slab height. They are low iron, triple glazed units and solid panels at a ratio mix of 60-40 approximately. These stagger by half a panel on each floor, and that means we had to split the panel physically in half on every half floor. If I try this spotlight thing, you'll see, woohoo, that sometimes there's a whole panel, sometimes the whole panel is from here to here, so we had to split it in the middle because this is the envelope. And of course, we also had to work out how to shed the water off the balconies while maintaining enough meat at the edges of the slab to be able to, for the embeds for the curtain wall and the guardrail. So we created a series of castellations. All this sounds very simple, of course, but some of that 90% perspiration at the time. So let's move on to the next slide, because I think this slide encompasses an awful lot of what we were talking about, or a lot of the design intent. So we've got, I'm pressing the wrong button. So the idea is to have a zero view out with the mullion being set down into the slab. So we have the floor inside the unit, the mullion, the exterior of the deck outside, and the guardrail shoe being submerged too, so it's just one line. We also wanted that for the underside too, but as with all curtain wall at this size, and this is a technical term, the top can be chonky. So to hide that, there's some kind of, I think it's about 200 mil or so. In the end, we decided on balance that it was better to keep the inside soffit plane 60 mil higher, and really you don't notice that in the final analysis. And you'll see you will go in a minute. And here's the, you see on all the long balconies, it's actually a gutter. So that picks up all the water off the balconies. They all slope towards the edge. And this is one where there's the curb. It's the up bit of the castellation, and then it doesn't exist outside of the connection to that slab, and the water flows off into the gutter. Off you go.
Okay, great. So we thought what we'd do is we'd vary between the details and some photographs of those details realized on the site. So what we see in this case is, oh, there, that's great. We can see how the ceilings are further down below the slab, but you can see also the slab step from the level above. So because the building, all of the balconies step from level to level in different locations, these had to be very kind of carefully aligned floor by floor, but also this kind of just setting down of the soffit level in order to run sprinkler pipes and to run electrical conduit through, in addition to accounting for that slight step in the slab, means that once the ceiling surface is put in, there's just one smooth plane from the inside to the outside. Now when we look up into the balcony soffit, we can see, of course, there are in-slab vents, very usual in Vancouver, but in this case, they're actually then, come on, oh, that's the wrong one. They're concealed in the soffit, behind a soffit panel. So there's this perforated vent with the same wood print material as the soffit itself. So these are very kind of carefully and cleverly concealed. As you head towards the outside gutter detail that Louise was just talking about, we then see that soffit condition tapers up to provide a fine point at the outside edge. Now, in looking at the balcony surface from above, we can see what Louise had been describing about the cantilevered glass rail. So you can see then that there's the continuous shoe that allows the balcony rail to be supported, and then these intermediate curb elements that also allow room for the water to drain from the balcony into the gutter. What we're looking at now that has the composite panel on the top of it is the gutter that's outside the guardrail. We can also see the top channel on top of the, oh, we still got the volume on top of the guardrail. And importantly, probably most importantly, the transition from inside to outside. So to create that flush detail from the flooring inside to the balcony outside, there's approximately 2.5-inch step in the slab. And that's what we saw concealed from below by that very slight drop ceiling. But you can see there's also a back dam just behind the window system. But that little detail and the waterproofing on it means that the water has an awfully difficult job to get uphill and inside the suite. Similarly, for the composite panel of the decking, we can see that things are carefully concealed. For example, we have things like roof anchors on those balconies, but those roof anchors, oh, I'm pressing the wrong button all the time. There are removable panels to allow access to them, but then it's a very flush detail at the end of the day, and that those board joints are staggered. So there's a kind of a naturalistic, slightly organic flow to the placement of the panels on the floor surface and also on the gutter surface beyond. So it's kind of looks like as though one continuous plane, despite having the shoe embedded for the guardrail in the joint between the balcony and the gutter beyond. There you can see that transition from inside to outside, that it's flush. Also, we'd be using things like triple glazing. So in order to get the envelope performance, we needed to use triple glazing. The windows, of course, the sliding doors are also triple glazed, which means they're very heavy. So there's a special hydraulic mechanism to allow them to be able to move and be able to move them with facility despite the weight of the panels. And you can also see the flush windowsill here, what Louise was describing in section, how the base of the window wall, it's actually the same profile as the curtain wall panels, but it's recessed just below the level of the door, of the floor inside, and you see that transition inside to outside here during the construction process. One further point here, you see the Japanese rock garden. You think, well, what's a Japanese rock garden? It's this unique feature of almost all of the balconies where there's an area of kind of contemplation. You've probably all seen the Japanese rock gardens and the raking and that whole tradition. So this is a characteristic of this project too. Very unlikely and unexpected discovery for many people who come out onto the roof. Some of them also have very carefully placed rocks. Louise.
Thank you. I see that we have 6 minutes.
Okay,
We
I'll shut
better
up.
get a shimmy on. No, we both better shut up or move. So this, I put this in because this is kind of the seminal detail of the project. Again, we saw a presentation this morning where I think Telus Ocean, you didn't want to see the slab behind. Same here. We don't want to, didn't want to have any spandrel panels. So this top hung piece of glazing in this case off this large connection to the slab, and the mullion is at the same height as the finish inside. This is unusual in Vancouver. We would normally see that higher. It also means that we have to hide the inside in some way, and we've got an engineering judgment for this part of the slab. It's a very large gap at 100 mil, so we have all the fire stopping with insulation, etc., in that gap, and a large steel panel that I'm pressing the wrong one too. Oh, back. Yeah, a large steel panel at this level to close that gap so that, you know, your grand piano leg isn't going to fall into the gap and ruin the fire stopping. And then underneath, as Greg said, we have a drop ceiling throughout, and this does double duty, not just to hide a lot of the services, but also because we have in-slab ducts that have to that would normally get through at this point to the outside, and we can't because there's a curtain wall embed there. So we drop out about 600 mil before the edge of that and come through at this point into a solid panel, which we'll see a little bit later.
Great, thanks, Louise. So looking at what I'd call this inverted valence detail at the junction of the curtain wall and the slab. So here we see that kind of metal surface that basically carries across the slab and allows us to have that zero spandrel joint at the floor slab. In this case, you also see the overlap of the shingle panel. So because they're offset 1500 mil each floor, or half offset, you can see one of the shingle panels overlapping this detail, and beyond it, of course, is simply the glass. We also see that metal detail at where the curtain wall joins the floor slab. As Louise was mentioning, it's basically, yes, your grand piano won't fall down the hole in the gap between the curtain wall and the edge, but it also contains then the fireproofing at the joint. And you can see the insulated back pan to the curtain wall panels where we have a spandrel glazing panel outboard. This is now the gap between the curtain wall and the slab, so you can see those brackets that you'd seen in the detail, section detail that Louise was showing. So this means that, of course, those in-slab vents need to offset and come through the curtain wall at a different location. You can see then, necessity to put all the services inboard of the back pan to the curtain wall. So there's basically a furring wall inboard of it for electric boxes and you name it. And you can also see then the detail for the window openers to the right. So that shows the opening windows that outside have a zero vision line because they're silicone adhered. The glazing is silicone adhered to those panels. So they look seamless from the outside, even though it's visible from the inside. But you can also see the flush detail at the base of the curtain wall there.
Ooh.
All yours.
So, all right, this will be quick. So once we've gathered all that water into the long gutters onto the balconies, how do we get it out? So you might see from this photo on every other column we've added a notch into which we put a rainwater leader that gathers all the water and brings it all the way down to the ground. On most of them, for some of them on the northwest corner, of course, we've got glazing starting at this level, so we couldn't do that. So we have to, there are partial notches in some of them to bring it to the other side. And on the right there is the finished product. Over all the notches, we put a large steel panel that covers it all. You wouldn't know that they were in there. Every 10 floors or so, we've got access panels in case there's a blockage at any point. What's next? Huh?
Oh, do you want to talk to that?
Yeah, sure. Yeah. I'll talk to the left one. So this is where I was talking about the exhaust and intake. Oh dear. So here is an exhaust or an intake on one of the panels when it's dropped out and comes through one of the solid panels. And this is one of the elephant trunks, as we came to call them. So we can't have an intake and an exhaust at the same point, so we had to come through and then drop it so that the intake and exhaust are separate from each other. But of course, you can't have an exhaust or an intake right next to the exhaust. Did I talk about 90% perspiration? We had to go through every single one of these, and there are relatively few solid panels, and coordinate all those. And I don't think we have one issue on those. It's finished now, so I can say that. Nearly finished, that bit of it. Do you want to talk about?
So the image to the right shows the net aggregate effect of all of those different strategies to achieve what Balazs was describing earlier for the texture of the elevation and the details of it. So we see both the louver panels. I won't point to it because you can see the whole elevation at once. These actually have a series of vertical louvers, and they allow the panels to kind of overlap what are recessed balconies. So it means that the balconies don't have to be always kind of literally represented on the elevation, and also provides a kind of slight kind of shielding to the balconies. We also see the concealed opener, as I was mentioning, from the inside. You can see those opening window panels, but of course, because they're silicone adhered, they look seamless from the outside. And the shingle panels, most importantly, the kind of angling of those panels that Balazs was also referring to earlier, the picking up of the light. I think any of you haven't yet seen the building, even though we're right beside it, but some of you maybe have not been in Vancouver recently. Just walk down the street and you can see the way that picks up the light of the sky in an interesting way. Go to the next.
I see that we're out of time, but 2 more minutes. So we have to wash the windows or replace something on this building also, and provide stabilization buttons for the crews who are on the swing stages, etc. So we do actually have the swing stage buttons or stabilization buttons incorporated into the side of normally a panel. It's always a panel adjacent to a glazed unit. So there it is, sitting there, so someone can drop off and plug in when we're on I don't think they're always on a swing stage on this building. So that was nice, and this is just showing you the building maintenance unit that runs around on 3 sides of the roof on a huge track, and is designed to withstand, to be able to take one of those large triple glazed units over the top and replace it if anything happens. And also window washing, of course. And these are covered at the main, this is the last penthouse level. So they're covered by a series of hinged panels.
And you can also see the curtain wall bypass. So up on the roof level, the windows apparently continue. There's, of course, an envelope junction between the inside and outside there, but you can see a fairly sizable steel structure to hold up those window panels up on the roof level. Go to the next.
Okay.
So here we see some of the effects from the inside. So you say, well, that's all great. It looks beautiful from the outside. How does it look from the inside? Here we see some of the 3-dimensional modeled curved kitchens. Probably never seen anything like that before, and it's quite an undertaking to achieve. But also as you look out towards the outside, you see that flush curtain wall sill. Just seamless interior, exterior. You see the window openers that we mentioned earlier, but also the sheer curtains, and then the glass as though disappearing behind that recessed valance because of that zero curtain wall junction with the slab. So basically as you get closer to the curtain wall, the sky appears more and more. And a view towards the kitchens, including the cantilever kitchen islands. It's kind of an interesting feature. That's one of the smaller ones. Some of them are larger off a single point of support. You can also see the Japanese rock garden, flush detail from inside to outside with the flooring and the roof decking.
Okay. All right. Well, I think we'd like to finish just by showing you we've given the skyline drama now. So this was in the middle of construction. And a wider view from Stanley Park. And these are some of the money shots. Oh, dear. Moving it off the stage. I don't think we need to say too much about these. I'll just scroll through them. But Balazs, I don't know if you want to add anything. It's really quite striking. And you might remember the original rendering for the rezoning with the maple. It's almost exactly the same.
One of the beautiful things about the rendering is it was also presented in the rain or the mist. So it was interesting that Kengo Kuma's office and team thought about the way that the building would look much of the year. It wasn't only the, with the blue sky behind, but also how it would look in the fog and the mist. And this is exactly the same view as was presented quite early on at the rezoning stage back in 2015. So thank you very much.
Thank you
for listening to our presentation.
Thank you.
Thank you very much. We are just about ready for the next presentation, which goes back to Southern California, where I spent some time. Pattrick of Morrison Hirschfield will do a presentation on the Orange County Museum of Art's engineering and modeling of a complex facade geometry. So please welcome Pattrick.
Thank you, Heather. Thank you.
Next back point.
Sorry.
Next back point.
Okay. Great. Thank you again, Heather. Yes, as Heather mentioned, my name is Pattrick from Morrison Hirschfield. Morrison Hirschfield itself is a company that's been around for about 75 years and does a range of engineering services. On my side, I work within the facade engineering group, and as part of that role as well, look after our secondary structures team there. And we do a range of facade consulting to designers, architects, as well as to contracting side. And also through our secondary structures team, we do engineering on curtain wall systems, glazing, specialist glazing, facades of a range of materials, guardrails, and a range of other things. As Heather mentioned, today I'm going to talk about the Orange County Museum of Art project and the cladding attachment system on that project. So I'm going to talk about sort of three key things kind of spread out throughout my talk, really focusing on the parametric modeling that we undertook to do the cladding attachment design on this and some of the complexity involved in that. I'll also talk about some of the challenges that came through that and some of the lessons learned through there. And then also talking about some of the contractual arrangements and how and when best to engage a facade engineer or facade consultant to assist through the design on projects such as these. So just a little bit about the project. The museum, Orange County Museum of Arts, or OCMA for short, it is based in California, in Costa Mesa, which is just south of Los Angeles. They, as a museum, have been around since 1962 and focus on 20th and 21st century artwork. But this new building that they developed allowed them to double up on their existing space, and so they've got now about 25,000 square feet of exhibition space. Morrison Hirschfield got involved in a project in 2019, and the project was completed in 2022. It's predominantly a three-story, it's a steel frame structure building, and the majority of the facade in this was an undulating terracotta facade, which, as you note from some of the pictures there, didn't really follow too much of a singular plane, right? So it varied in its geometry throughout the project. In terms of the actual project team on the design side and with the core focus on the facade, the designer for this was Morphosis, and I believe they're actually presenting in San Francisco next week as well at Zak Facades, so they may cover some more of this project as well within that. The structural engineer was John A. Martin Associates, and then Walter P. Moore was the facade consultant on the job working for the design team, and then the general contractor was Clark Construction Group. Just a little bit about the project, just to give you some oversight. So actually, the main exhibition hall is actually underneath the plaza, which you see towards the left here. So actually, the main exhibits occur underneath that space. Towards the right, where we've got this grand staircase below, that's the museum entryway and sort of museum shop. Up on the upper left there, where we kind of got that curved undulating facade, behind that is primarily event space, meeting rooms, and the facade actually projects up above the roof level there to hide a mechanical system. In the center, there was a central atrium entrance space, and the terracotta facade actually wraps through and actually goes into the interior of the building. So there, and then there's sort of on the right side, an education pavilion which wrapped around that atrium. And then sort of towards the lower right, there's kind of this avenue of arts gallery, which is this long rectangular shaped part of the project. And just kind of getting in towards the interior, you can get a sense of how the geometry varies and how the terracotta cladding actually carried on through into the building. And this is where we actually got into the more complicated geometry, really. And really got into sort of some interesting shapes and curvature. You'll notice, as we kind of get into some of the edge perimeters there's some really odd shaped terracotta panels there, and that did prove a bit of a challenge for us when we were going through our engineering and modeling, just to make sure we could get support to those panels there. There was a clear separation, at least between the glazing and the terracotta. So actually that made our modeling and coordination relatively easy between those two elements. And as continue to look through towards the interior there, you can kind of see how the terracotta again continues through that whole atrium space above the museum shop and up into the central atrium. There was also some link bridges that we had to coordinate through with that design there. So just a little bit more details then into the cladding attachment system and our scope there. So just to give a sense of the project team that was involved in the actual facade side, on the contracting side there, we had Clark Construction Group as a general contractor. And then the actual installation side of the facade was done by Best Contracting Services. The cladding material itself was terracotta, Boston Valley, so you heard from them earlier today. They supplied the cladding for this, and they had their own engineer working for them. And then our client was SFS Envelope, who actually supplied the cladding attachment system. And so Morrison Hirschfield, as their engineer, was responsible for doing the 3D models for them. We did shop drawings and calculation packages for them for the engineering of that system there. We've worked for many years with SFS Envelope and actually know their systems pretty well and throughout projects in North America. This is definitely one of the more complicated ones we've had to address with them through the years. And then also just to highlight, typically when we're getting into sort of facades on these kind of things, we don't have to worry too much about, let's say, the stud spacings or even the secondary steelwork or any steelwork, because it's usually pretty consistent. But in this case, it was quite integral to our cladding attachment design there. So those are mentioned there as well. But you can notice that there's quite a few engineers and teams involved in this and trying to coordinate this design. So in terms of the cladding attachment systems, on that sort of long rectangular part of the building you see there, we could follow a pretty traditional cladding attachment system, just some intermittent brackets on the studs with horizontal T-rails. And then we got into sort of what's shown in the center there. Because of the geometry, we ended up having a double layered system. So we had intermittent brackets, I'd say vertical T-rails, although they weren't always vertical, and then horizontal hat tracks running through. And then there were certain areas where we had a double curved facade, and so we had to deal with that with some discrete brackets, and we did metal strapping between the cladding, between the metal studs to support those brackets. And taking a little bit closer look at the actual project there, so again, pretty traditional or easy system on this sort of long Avenue of Arts gallery there. The one thing I'll note is that the envelope system is actually a thermally broken cladding attachment system, but in this particular case, that wasn't sort of required here. We weren't worried about the thermal side within our scope, but there was usefulness in using their system, just because with being an aluminum system, there was a durability aspect, and also their system allowed for a lot of adjustment of the rails, and so we didn't have to worry too much about misalignment on the base substrate there. And then again, kind of getting into this sort of system, which actually formed the majority of the facade, you'll notice that sort of in that picture on the right, that some of the angles that we had to deal with varied quite a lot. So there was a lot of coordination of trying to make sure we set up our model and knew where rails were going to be and setting those out early on to deal with those angles through there. And then finally, getting to sort of the 3D curved spaces. At some point early in the project, we were looking at using curved aluminum rails to kind of deal with these areas. But really, from an effectiveness perspective, it was decided, hey, just to provide some metal strapping between metal studs there, and that provided us a structural support. We could just do discrete brackets too there. And then the center image is really generic to all systems. That was really just showing the Eclipse system for connecting in the terracotta panels. Getting a bit into the modeling side here and discussing how we went about our modeling and coordination. Just because within our project and scope, we were contractually obliged to do a coordinated model for the cladding attachment system. And so we had to sort of bring in all the architectural, structural, cladding models and what you call secondary structures, or even the middle studs, and had to get those all modeled in 3D and to bring those in. And I went through a process of coordinating that with those various entities and doing our engineering through on those elements there. So that was a process we hadn't ever been through before with SFS Envelope, so it was definitely a learning experience with them as a client and going through that process. And through that as well, we're producing takeoffs for them too for their supply chain. Getting a little bit into the Rhino model and showing sort of the complexity we had to deal with. So if you look at some of the steel work that we had and this is just a part of the model, definitely not something typical to deal with. And so we would bring those models in there and then bring in as well from the metal stud supplier their studs. And it's not following our traditional 16-inch on center spacing, which I had to deal with here. Studs were varying in terms of location and things like that. So we did have to bring that in. And initially, as all things, the hopeful plan was that the metal studs would get brought in and be fully engineered and coordinated before we would actually start taking over our modeling process. But inevitably, that didn't really happen. We had to work with a system in parallel where their model was constantly updating while we were trying to model our system and engineer our system. So what we did with Rhino was we ended up linking our cladding attachment system to their stud layout. And so as they were changing their model, we were automatically mapping and aligning our cladding attachment system to that and getting that to be automatically mapped out and aligned through there. So we didn't have to go through and manually go and model and reapply all our brackets and our cladding attachment systems onto there. And then equally, through that process, we also linked in with the terracotta cladding panels because the clip systems that had to be attached to there needed to align with our rails. And so we would have that all linked together. So as the metal stud package was getting updated, or if any of the modulation here was getting updated, our model would automatically update and we wouldn't have to go through and redraw everything over and over again. What was really critical in the beginning for this was, from our structural engineering side, was to really create some strict rules and criteria which we could then feed into that Rhino model. And so working with looking at the terracotta, understanding where could we place the clips on the terracotta panel, defining those limitations and putting those into our Rhino model, defining that there. And then same thing on the actual cladding attachment systems, defining what is the maximum spacing on brackets, what are the maximum rail lengths, what are the maximum cantilevers we could handle, and what are the maximum sort of angles we could handle. We plugged all of that into our Rhino model, and that way, as we were mapping out our cladding attachment system onto the metal stud layout, if they moved the metal studs, we could automatically update our model within these defined constraints here. And so getting into that coordination of the model, generally what we're looking at the image in the bottom right, a large bunch of the area we could really coordinate well, and using that sort of Rhino model and bringing in all these elements, we could really coordinate that work very well. So again, as the metal stud layouts were changing, they were coordinating work, our model could get updated automatically. But even within that, still some of the lessons learned was there was still a lot of manual work that still had to get done, which maybe wasn't recognized early enough, was even just transitioning from these more planar elements into the 3D curved areas, defining where that breakdown occurs. And that required a bit of manual integration and coordination through that process there. There was some early coordination as well, sort of in that image on the top right there, which is sort of a performance mock-up that we had to do, which integrated the curtain wall system as well, glazing system into this. But definitely a lot of sessions working with the other design teams trying to coordinate all our work through there. The one area where, as well, which as we kind of went through the process that we struggled a little bit with was, it worked well where we had structure and we had metal studs coming through and we had secondary structure coming through it we could pick up and align our system to. But when we got like on the far right image there into corners of buildings, the basis of design or the models we're receiving didn't have any structure in those locations. And so we had to spend quite a lot of time, actually we probably dedicated a vast majority of our time to these kind of transitions because we had to deal with a lot of bespoke details there and come up with bespoke brackets or steel support to actually cantilever out from the main structure to then pick up our cladding attachment system. Same thing along sort of the lower and bottom edges, the bottom and upper edges of this cladding system, where we kind of get into these odd shaped panels. Sometimes just because of the odd shape of the terracotta panel, the cladding attachment, the clip for that panel wouldn't line up with any of our rail system, and nor was there any structure behind. Typically, as you kind of look at the image in the top right there, the steel structure would end much higher up above our cladding system, and that geometry varied. So we spent a lot of time having to deal with those areas and solve those and coming up with bespoke solutions. And so again, actually a good 90% plus of the facade we actually could generate very much on an automatic basis, but going back in time, definitely would be good to focus on these areas earlier on in the process. And then further, in terms of our shop drawing production, one of the deliverables that they wanted on site was to actually still have some shop drawings even in 2D format, although they were doing a lot of set out from 3D models. So what we did was we took our Rhino model and we actually transformed and transplaced sort of all the all the planes of all these 3D elements, all the various, the primary structure, the cladding, the brackets, the rails, and transform them onto a singular plane, and then unwrap that into a 2D shape. So we kind of end up with some weird, sort of shop drawings where we had these sort of weird elevations which were unraveled from 3D into 2D shapes, but it was just there to provide them sort of some counter checks and take off some measurements on site to that process. The one thing with this project, what I'd say is there was a lot of coordination and optimization we're doing with coordinating with other trades in terms of our design, in terms of aligning our cladding attachment system with their studs. We didn't really get into a lot of optimization in terms of, hey, what are the different systems we can use and how can we sort of create a more structurally efficient product, just because of the nature of the project. And nor was it getting to the thermal side on this sort of project. But the one thing, so because of where we were engaged was quite far at the end of the project, we couldn't really influence that much. So, the one thing I want to kind of point out is, there's obviously the parametric tools we work through with the Rhino model, and we could actually do a lot of mapping and modeling towards that and optimization. But even there are other parametric tools which even MH has sort of developed and worked with, where we've actually kind of been able to analyze a lot of these systems and take these cladding attachment systems and iterate out in hundreds, if not thousands, of different combinations of rail lengths, of loads, of wind loads, of dead loads, of bracket types, of substrates. And through these tools, we can actually go through and actually scan through lots of different iterations, depending on what our needs are for a project, and actually kind of find the optimal solution, even from a structural side. And this is one tool which we've created, actually worked with SFS Envelope on before. But even so, we can kind of take that from a range of different suppliers and products and actually pull it together and kind of start looking through that parametrically and finding, hey, what are the actually most appropriate solutions for different projects? And taking that even a step further is that with MH's work that we've done, we've been very extensively involved in thermal analysis as well, and especially going to this market. On the Orange County Museum of Arts project, we weren't that concerned again with thermal, and it's a pretty complicated project, but even in Vancouver, even on a simple project now, we're getting to a place where it's actually getting more complicated because of the performance demands of thermal and structural. And so the one thing which we're kind of getting involved in and looking at is bringing in that thermal side and performance of these systems, as well as the structural, and be able to, again, iterate through thousands of combinations of different systems and different structural iterations of how to bring this together and find what's actually the best for a project. And again, that's been driven a lot by Morrison and Hirfield's work on the thermal bridging guide, as well as the structural work we're doing for several cladding attachment manufacturers. And just talking sort of in terms of lessons learned of contractual arrangements and understanding where to bring in facade engineering. Going back to sort of the diagram of the Orange County Museum of Arts project, the one thing which we found was we managed to make it work, but it was very much, for a complicated project, it was structured very much in your traditional spec sort of basis, right, where whoever's responsible for certain parts of the specification kind of did their bit. So when you're looking at this for quite a complicated facade, we had about 3 or 4 engineers involved in trying to coordinate this, but they're all kind of at the end of the line and trying to bring their experience and what they could do as an optimization tool. They had to kind of jump through quite a number of different hoops to kind of get that communication, never mind even up to the project design team, which sits further up above this. And so it's just one of those challenges, right, when you're thinking of your contracts and kind of bringing through is, if you've got a complicated project or even what looks on paper a simple project, but it's got complicated performance requirements, is how can you structure this to try and make sure that there's a more collaborative approach, and is there a singular person who's responsible for the facade design and taking it on? And again, especially when you're getting to facade engineering working for contractors, a lot of times they're only getting on board within that red zone. They're right within the shop drawing stage and fabrication stage on many projects. And so a lot of design effort happens up early. And if you're bringing somebody on, especially on a complicated project, and something we struggled with on this project at times was, even on performance mock-up testing, for example, that was very much dictated separately from us, even though we were the designing engineer on a lot of the cladding attachment systems, and trying to be able to influence that and get the results we needed out of there became difficult. So, the one thing it's always important to look at and see is, how soon do we try and bring in your facade engineer? And even if you do have a facade consultant on early in a project, what is the scope? What are they doing? Are they more sort of a high-level consultation? Are you getting them to take a deep dive into the engineering on some of these systems? We do that fairly regularly with curtain walls. I think we've become used to doing that on the design assist side. But when we're getting into even these facade systems now as cladding systems, again with the performance parameters and even on complicated facades, yeah, trying to drive that earlier will definitely help relieve some of that those design challenges you might have, and you can actually affect the outcome much earlier in the process there. Yeah, just sort of one thing that I would like to sort of highlight out of this is that parametric tools and what we found on this Orange County Museum of Arts project was the parametric tools definitely helped us to avoid a lot of manual work, because trying to map to that stud layout would have required a lot of manual labor to try and work that out in this project. So certainly having those tools in place helped us to optimize and optimize our workflow through this. But it doesn't have to be just for those complicated projects. As we're seeing, there are tools that will help you actually find the most efficient structural solutions, thermal solutions that can apply even to the more simple projects. The other thing I would say is that going beyond just design, and a project like this has had a really great design, but looking at, okay, how do we break that contract down? How do we, when are we going to engage facade engineers? Are we going to wait till that shop drawing stage when we engage them because they have a limited ability to affect that outcome? Try and think of that holistically and see, when do we actually engage them and bring them on to the project, so that maybe you need to engage them earlier and get them involved earlier to help steer that and influence the design through there. The one other thing, obviously, in closing, I do need to thank, we had a much bigger team than went beyond me, and even beyond the team that's presented here. It was quite from Morrison Hirschfeld, was sort of a range of effort across multiple offices. We had Kevin Breitenbach, who was in our Calgary office doing a lot of the engineering, Edlin, who did a lot of the Rhino modeling, and she's based now at San Francisco office, Marisha out of Edmonton doing a lot of drafting, Chad in Portland, Oregon, as well as Sean Stevenson in Portland, Oregon. So we had kind of a wide range of team working on this, collaboratively, and kudos to them. And also, secondly, as well, kudos to our client SFS Envelope, who we work with on this project and getting through it. And yeah, that's. Okay, thanks.
At the next break, don't forget to do that if you haven't done it.
How to open windows.
And for the presenters earlier, Greg and Louise and Brett, at the end of this session, please just remember to stay in so we can get a photo. I believe this session will end around 4 or 4:10. So we still have another 4 presenters to come. Our next presenter is Chris Franzo of Vitro Architectural Glass, and he will be talking about reducing embodied carbon and operational carbon from using glass. So please welcome Chris.
Cool. All right.
Ready?
Yeah. So we're getting that loaded up here just real quick. All right. It's good to see so many people here. Can you guys hear me? Is my mic loud enough? Oh, all right. Usually I'm a loud mouth here, so I just want to make sure that everyone can hear me on the microphone. Just a second. Okay. It's coming. Am I on? You want to check my mic back here? Or? In the meantime, please be entertained by my soft shoe. Yeah. Yeah, that's right.
Keep your handheld.
Okay.
The main guys.
Okay, cool. All right, handheld. Love that. Cool. So Chris Franzo with Vitro Architectural Glass. Today I am going to teach you on using glass to reduce embodied and operational carbon. I'm very, very thankful that you all have stayed past lunch, and I hope to wake you up here, because there is no better way to teach on this topic than to talk to you about burgers. You all just ate, you're all probably like, oh gosh, burgers. But it's delicious. Just out of curiosity, give me a number. Someone be bold enough to say, hey, how much does a burger like this cost? $5. What? $20. That could, yeah, depending on where you get that. I want to talk to you about cost because that's the world that you and I live in. We talk about costs of building products here. We live in a world of dollars and cents. What makes sense for the building? Budgets, right? Let's go a little bit beyond this. Let's talk about the hidden cost of that burgers. And as I go through this here, no crying in the audience, no guilt, anything like that. But let's go over some of the hidden costs. The first hidden cost, what is this doing to my health? If I'm on a 2,000 calorie diet here, I'm already over a quarter. I'm a half of my saturated fat, about a quarter of my cholesterol, almost half of my sodium just in this one burger. Again, no crying, no guilt. Hey, there's no shame here, no judgment. We're all in the trust tree, right? Let's go further than that. Let's talk about these fun people here. Cows, love them. Let's talk about what happens to the environment. Did you know these guys here, I'm going to say it, and I'm very, very sorry here, they burp and fart 500 liters of methane a day, which translates into 3 tons of embodied carbon annually. Like I said, no better way to teach it than something about burgers here. All right, sounds like I got a little background action here. So, why do we love these burgers? I'm going to leave this conference. I got to run to the airport real quick. I'm going to be starving. I'm going to hit up my Uber driver. I may be like, hey, pull over. Let's go somewhere. We love burgers like this for 3 reasons. Because they are cheap, they are available, and they are satisfying. Even if it's costing us here. Even if it's costing the environment a little bit. Think about that as we go forward, as I'm talking to you today. There is hidden costs in building materials. You're working with some things on buildings now that are affordable, they're available enough, and sometimes they limp along and they just barely make the spec. For now, not in a couple of months maybe. So think about that as we talk about the real costs. I want to make you more carbon conscious, and I want to help you make better informed carbon conscious decisions on some of the things you choose for your buildings. Now, let's go into some of the basics here. What is embodied carbon, and where can I find that information? I intend to arm you with great information. Embodied carbon is this: the greenhouse gas emissions associated with manufacturing and installation of construction materials. I want to show you what an environmental product declaration looks like. That's a bunch of numbers. It's Greek to many, right? And if you're Greek, I apologize. That's your native language. You're like, I read that, no problem. But I want to show you a couple of things on here. The first one is GWP, known as global warming potential. The next one is CO2-EQ, which means carbon dioxide equivalent. That's what it looks like on an environmental product declaration. Global warming potential, let's talk about what that is. It's a measure of the solar heat that's absorbed by any greenhouse gas that's out there in the environment right there as a multiple of the heat that is absorbed by the same amount of carbon dioxide. So carbon dioxide is the base here. We want to talk about carbon conscious, right? So I'm going to give you some examples of global warming potential. Because carbon dioxide is our base here, look at the next one. A very common manufacturing gas comes out, it's methane, right? Even those little fun little cows that we talked about a little bit earlier. Methane has a global warming potential. This is a multiple of 27 to 30. Nitrous oxide, and I feel, if you want to if you're just like, man, I love that nitrous oxide at the dentist, yeah, look at that, 273. Now, let me show you what that does, because we're now going to talk about carbon dioxide equivalents of greenhouse gases. Here it is. So take a look at the screen up here. Look at the fun little gas cloud just right up there. This is just Joe Manufacturing Plant right here, in Billy Bob, Oregon, right? 1 ton of gas, if it has a global warming potential of 10, that means it absorbs the same amount of heat as 10 tons of carbon dioxide. Now we're going to go back to methane. So 1 ton of methane released in the atmosphere now absorbs the same amount of energy as 27 to 30 tons of carbon dioxide. Now think about it over like how many things get produced out there in manufacturing. So the sum of all this carbon dioxide, or this carbon dioxide equivalent produced by manufacturing a product, is the carbon that it embodies. Some of you, this is day 1, hour 1 of carbon conscious thinking, and happy to walk you through this really simple lesson here. So why do we need to care about this? Who cares, right? Why do we need to care about this? Because I tell you what, carbon dioxide and other greenhouse gases have been scientifically shown to really hug the earth and really keep that energy in there. The solar radiation comes down from the sun. It generally gets dissipated quite easily on Earth, but if you have an excess of greenhouse gas emissions there, and that includes carbon here, carbon dioxide, it traps that heat from dissipating. Now I tell you what, regardless of your belief system, building performance requirements are getting increasingly strict. And this is my something is changing versus someone is reacting scale here. Now, some of you, there are alarm bells that go off in your mind, and you think there's a real crisis right now because there's an increase in carbon dioxide here and greenhouse gases. Maybe a couple of you think that something is changing as something is reacting. There's a bunch of idiots out there promoting madness and conspiracy theories. And you know what? I've heard that plenty. And hey, I'm not knocking your belief system, but one thing that is happening is that building performance requirements continually go up. I never have seen them go down. So why do we need to worry, again, about carbon and greenhouse gases? Because a lot of HVAC systems use one heck of a lot of energy, and buildings contribute to a lot of greenhouse gas emissions in their operational carbon, even their embodied carbon of all the products that are up on there. If global temperatures begin to rise, this is kind of just theoretical thinking here, a building's energy use may increase because you want to keep the occupants comfortable. How many people work in an office building that has monolithic glass and sweat it out over the summer? I was in Calgary not too long ago. I went to plenty of engineering firms over there that was in those same kind of buildings, and everyone's just sweating it over the summer. Nice big pit stains right here, real cute. But it's reality, right? They don't have monolithic glass because they did something about it to keep everyone comfortable inside. Let's make it more practical. How expensive are facades going to get because Canada keeps getting warmer? In 2021, Lytton got 49.6 degrees centigrade, which is over 121 degrees Fahrenheit. That is nearly on fire. That's far from fire. Don't say that here. Don't write me, I won't respond. But it was very, very warm. A lot of things cooked out there. But I tell you what, it costs us in this way. To keep occupants more comfortable, you're going to need more robust low-E coatings on glass. You're going to need more complicated and thermally broken facade systems to keep everyone comfortable on the inside, to keep this outside temperature from to making it on the inside. It's going to overload that HVAC. How many have heard this? This is a week ago. The 10th of May, Toronto became the first North American jurisdiction to require lower carbon construction materials, limiting embodied carbon from new city-owned buildings here. And that applies to these two things, major structural elements and facade elements. Something is happening and someone is reacting. Although this happened on the East Coast over there, I tell you what, Vancouver is a wonderful progressive city. And oftentimes it influences the United States to be better. And I tell you what, something is happening and someone's reacting, and something like this may come here. Now, where does embodied carbon in glass come from? It comes from this nice pool of molten lava here to melt raw material down into liquid material, and then it goes back to, solid material that makes the glass out here. So, in an insulating glass unit, 75% of your embodied carbon is coming from the float glass process. 13% is when I sell it to a fabricator, or other glass manufacturers sell it to a fabricator, and they heat treat it. Heat treating, like heat strengthening or fully tempered, that is words that are in your spec. That is another 13% of embodied carbon. 10% by making the IGU itself, going through the fabrication process. And then finally, just negligible 2% does that low E coating there. So now that you are armed with good information, let's go in and talk about reduction strategies. The first one is using a manufacturer's environmental product declaration, because 75% of the embodied carbon of your insulating glass unit comes from manufacturing just that float glass alone. One of the best documents that you can use is a flat glass environmental product declaration. And that's the terminology to use, flat glass EPD. So you can feel free to find all the manufacturers that do have those and review them. Now you know where to find the information. Now you know what information you're looking for as far as carbon dioxide equivalent and global warming potential. So here's where you need to talk to like other manufacturers. If you really, really want to dive into this here, let's find out what manufacturers are doing as far as collecting their raw materials, as far as what are they doing in the manufacturing process. We'll get into later, employing actions of lowering embodied carbon and operational carbon, but good manufacturers should keep this in mind. Reducing natural gas consumption and material extraction, reducing transportation from mine to manufacturing locations, and examining the global warming potential of other manufacturers or of other raw material suppliers here. But we can't control that as much as we can control what we do at the manufacturing plant. We can either do nothing. We're just going to do nothing right there. We're going to do this. Utilizing more cullet, whether post-industrial or pre-industrial here, we're going to use that in the glass recipe because it lowers the melting temperature. Again, you're lowering that energy use, lowering that. Now, net zero is great because you can continue with one activity, but you're doing all kinds of other activities that mathematically show that you can go carbon, equal or carbon neutral or carbon negative. But some manufacturers are pioneers in oxy-fuel technology that lowers the melting point of the glass and essentially halves the greenhouse gas emissions. I like that better. Why not just eliminate what's going into the atmosphere right out of the gate? Cool. We want to do total carbon reduction here, so that's in lowering embodied carbon by studying the manufacturer, what's on their EPD, what are their actions, what are their responsibility, environmentally conscious responsibilities, and lowering operational carbon. But I tell you, if you want to lower operational carbon, what if lower embodied carbon here, we can go right from all the high performance triple glaze, dual glaze IGUs, and we can go right back to monolithic glass. Someone said in a presentation earlier, man, going from double to triple, you're up in the carbon. You're right. So if you want to go backwards to monolithic glass, you can lower your embodied carbon, but you blow your operational carbon out of the water, and it's kind of a de-evolution there. So here are some things that are out there from many manufacturers. I'm going to be fair to all of us out there because the glass community cares about the gorgeous city of Vancouver, BC. So there is double and triple pane that's out there right now, and you could work with any manufacturer out there to come up with something that's going to meet your requirement or even meet something that you see coming up. There's tinted glass that's out there, which lowers the solar heat gain coefficient, can also give this great privacy and great design options out there. The next one is switchable glass technology. There's some great ones out there right now. There's vacuum insulating glass, both monolithic and in a hybrid IGU that gives you an R value of a 2x6 wall. This is great stuff to lower operational carbon. You can go through and you can even lower operational carbon by doing retrofit. There's a lot of monolithic glass out there that can easily be replaced by vacuum insulating glass and immediately give you an improvement on that. But finally, I want to give you one real world thing that happened to me. I want to let you walk out of here with a real example. This was a real global corporation that we would all know, and they were doing a massive campus redo, many buildings out there. And so what they did, do I get one more minute? Give me one more minute. All right, cool. So what they did was they said, hey, all of my trades here, I'm going to specify that all of the trades as my basis of design be below the Carbon Leadership Forum baseline. If you're not familiar with Carbon Leadership Forum, you can go ahead and check those out here. And so they did this. I didn't do all of their trades right here, but I tell you what, this was their goal, to be carbon conscious of their project. All of the materials here had to be below that were basis of design or approved manufacturer. But here's what happened. Real life happened. Real life came in and the bid was so good on a couple of trades that they had to take a look at that. But it was way above the Carbon Leadership Forum baseline. And they knew that they had a problem here. All of a sudden, this was thrown in the face of all their basis of design. And now they freak out. What do we do? I tell you what, this is what they should have done to prepare. Maybe understand, hey, this general contractor who got the project usually works with these couple of people here. What are their EPDs? What do they look like here? Let's find out what's acceptable, and if they come back lower, what's okay? Building owner, building project team here, general contractor, what's acceptable? Is something acceptable? There is a little preparation to do. But I tell you what, I got away from talking about burgers. Too far. As a matter of fact, that burger's delicious. I may get that. I may go home and have a load of fries with this thing here, right? I love that. That may be me in the airport today. But I tell you what, on a 2,000 calorie diet, and I actually, I used to not be able to button this coat. Now I can because I ate healthy. I had to go on a diet to fit my clothes to look good for you guys here. So you're on a 2,000 calorie diet. Sometimes you get a burger and a fries, and just to make yourself feel good, you do a Diet Coke with that, right? You go on a diet. Well, that's how they solved this. They went ahead and they worked with different manufacturers to say, hey, we've got 2 of these trades that are way over. Now, just so you know, how they measure embodied carbon in the different trades is different product category rules. So it's not like, hey, that one went 10 kilograms over. I got to lower 10 kilograms over here. But they knew they needed to go back to the other trades and find who had the lowest in glass, in masonry, and a couple other products there by using the EPD. That was a real situation that you are likely going to encounter when you face and you make these decisions here. I started with a burger. I'm going to end with a burger here, right? It's delicious. We love it because it's cheap, satisfying, and available, and so are a lot of products out there. I know there are things that you want to do on your projects to lower carbon. I hear it all day today. So if this is week 1, hour 1 in your journey, take active steps to be carbon conscious and to move us forward in the building industry. Architects, that's where it starts, right? It's the ideas out here. It's these idea makers out here. If you're already on this journey, continue taking these steps because the right products are out there. They're just as affordable and they're a lot more satisfying for your sustainable bottom line. Cool. Thanks, guys. Appreciate it. Yeah. I went over a couple. Sorry.
Thanks, Chris. I had one of those burgers last night and it was uncomfortable this morning. I think I need a diet. Next up is a sustainable facade design with ultra compact stone, and it's presented by Dean White of Cosentino. So please welcome Dean. And we have a couple more presentations, so stick around.
Have we got a clipper? Hello, everybody. I don't know about you, but I'm thinking how many steps it is to the nearest burger joint right now. And as you might have guessed, I haven't walked past too many either. I'm really happy to be here today to talk about Cosentino, talk about the things that we're doing on the sustainability side, introduce you to the company, introduce you to our product, and how it can be integrated into ventilated rain screens and curtain wall type facade projects. So we'll talk about Cosentino real quick. Cosentino is a Spanish company based in the south of Spain. We make all kinds of hard surfaces. We started off as a marble company back in 1949. A couple of Italian brothers moved to the south of Spain. That's why we've got an Italian name, but we're based in Spain. So everybody's got Cosentino last name and they got Spanish first names now, all these years later. And we did marble up and through the 70s and 80s, and in the 90s we developed something called silestone quartz countertops, which is a really big part of our business, focused on the interior. And in 2013 we introduced Dectin, which is an ultra-compact stone that is a unique and universal product that can be used everywhere you've got hard surfacing, including the facades. So we've got 6,000 employees worldwide. We're in 118 countries, and we distribute straight to the installers and the fabricators on the planet. So we don't go through distribution, etc. We have a factory in the south of Spain that is about a 10 million square foot campus, and we produce on the Dectin side, we can produce 250,000 square feet a day off of 3 production lines. When we're looking at sustainability, this is a very large focus for Cosentino, has been for some time, and we've been making very great strides on that front. We approach it with the ESG approach. So, the environmental, the social, and the governance. From the environmental side, we'll talk about that in just a bit. That really revolves around the production, the extraction of the raw materials, the production of the product, getting it out to market, etc. All the different things we're doing along that side. On the social side, one of the things that really impacts around the sustainability side is, I'm originally from the Yukon. We did a lot of mining in the Yukon. I spent a lot of time, I lived there 30 years and spent half of that time working in the mining business up there. And as you think of mines, you think of mineral extraction, you think of tailing ponds, you think of something that's really not sustainable over time, right? So, when we're looking at the social aspect, those towns are kind of boom bust. They happen, they close. There's a lot of social upheaval when that happens. Cosentino is really focused on supporting the communities that we're in and making sure that what we're doing is sustainable. It employs the people around there. We bring and we have great social impact in those places. On the governance side, we're talking about transparency. We're talking about how do we rate, in different rankings and so forth around carbon emissions and the different steps we're taking on sustainability. Again, this mirrors what Chris said. So when we're talking about where these carbon emissions are coming from, where this embodied carbon is coming from, 73% in our case comes from the raw materials, okay? 13% from the manufacturing. And what a lot of people overlook is they talk about the sustainability of their product. They focus on the manufacturing side. But a big part of reducing carbon emissions is also how you move your product to market. Okay, so the whole logistics around it is really, really important. And then, of course, the use and the recovery side of it is a very low part of the carbon emissions. So we look at ways, particularly we look at something like the manufacturing side. We have furnaces and ovens that melt our product down in the final sinterization stage that are 200 meters long, and they run off natural gas. So they burn a lot of energy. There's a lot of emissions there that we offset with different projects. We are moving those from natural gas to hydrogen fuel. So that's going to have a huge impact on negating our emissions. We're also collaborating with suppliers that have the same vision as we have. So on the procurement side, we're working towards that. And we use robots to move the product around our facility. So they're very efficient in minimizing the amount of emissions, moving things from the different production lines to the off-site production, cut the size lines, and also to our warehousing. So we look at it this way. We look at it, from the production side, the procurement, the ecological design of the products. How do we limit the amount of embodied carbon in the manufacturing of our products, which is very key. We look at it from the production side, including using best available technology. The hydrogen fuel to run our furnaces is one of those best available technologies, so we're moving towards it. Reducing the waste, we're moving towards zero waste, and we're getting quite close to that. And then, you know, the distribution. How do we move it around the planet? How do we move it efficiently? How do we handle the least amount of times? Packaging, all that type of thing impacts there. And then, you know, over, you know, the consumption of it. What's the longevity of the product? Dectin in particular, which we'll be talking about, has a very long life cycle. So it has a low life cycle cost. Also means it's not going to get replaced as often as, say, metal and things like that. So, or brick, etc. So you've got a very long-lasting product that has less impact. And then on the recycling side of things. Now there's two aspects to the recycling. There's a post, you know, consumer and there's a post-production. We're very focused on using recycled content in our materials. And we've got, on the Dectin side, 20 to 95% recycled content in there. And that's from years of working on taking the post-production waste that we have and finding ways to reintegrate it into the production. And the material that we can't find a way, we don't have the technology yet to bring it back into our product, we stockpile that and we're constantly working on ways to do that. So our goal is to have zero waste in our factories at some point, and we're working very hard to get to that goal. Electricity. Our very large facility in Spain is run off nothing but renewable electricity. So we produce, we have one of the largest self-consuming solar farms in Europe, but that only supplies us with about 15% of what we actually use. We use the equivalent of 400,000 homes in the factory of electricity. All the other electricity that we purchase is either solar or wind certified. So it's very, very important to us to work with renewable energy. What that does at the end of the day is that our product, Dectin, which is an ultra-compact stone, is carbon neutral from cradle to grave, which includes the logistics of getting it to market and includes the calculations for getting it back if we have to. To talk about Dectin, Dectin is an ultra-compact stone. It's an engineered stone. So we mine 20 plus different minerals out of the earth that have gone through the metamorphic process. We break them down, we put them together in new recipes. We press them with a 25,000 ton press to make an ultra-compact, very dense product that has some very unique physical properties. No resins, no dyes, etc. Then we fire them in a furnace, and this is a very short view of that right here. And you've got basically your raw material goes to the press, it gets decorated, everything goes into an oven, gets heated up to 2300 degrees, and all the colors and patterns we put on, or any kind of mineral printing we put on there, is then cooled, and it's all fused together in a monolithic material that has very unique properties. So those properties include UV stability as far as color goes, so it's not going to break down over time. It's going to look the same 30 years down the road. You might have some dust on there, you just kind of have to wash it off, and it'll look like new. It's a non-combustible product. In Canada, we tested that to the CanULC S135, which some of you may know is more commonly used for a composite type product. Ours is not a composite, but when we use it in a ventilated rain screen or a curtain wall application, we put a fiberglass mesh on the back of that. And that fiberglass mesh is there for fall protection. If someone hits with a crane at height or a lift truck, you don't have shards falling on people's heads. So you've got three materials there. You've got the Dectin, you've got the epoxy, and the mesh. That's why we tested to that. It's very non-porous, so it has very, very low water absorption. And the other aspect of that is that it's graffiti proof. So when graffiti goes on it, it won't bite into it. You can wash it off with soap and water. You can use a pressure washer. You can use harsh chemicals if you like. I wouldn't recommend it because it doesn't need it, but you can if you want. And it's very stain proof and chemical resistant. So it's a very good product for labs and so forth as well. Low coefficient of thermal expansion, okay? Freeze thaw proof. So it's not the thing that's going to suffer from the wild swings in temperatures in the Canadian winter. It's going to be the substrate, or it's going to be the attachment system that's going to be more impacted than the Dectin. It's relatively inert. Large format, we'll talk about that in just a second. And then we've got dimensional consistency. I say this because if you ever have a chance to visit us in Spain, and we do take tours there, or see a video of that factory, a Dectin line is about 1 kilometer long. We run 3 of them there, and you see very few people in the factory. It's highly automated. That helps us with our energy efficiency, of course, but it also creates a very consistent product. So from slab to slab, it's the same gauge, and the color consistency is there from slab to slab. and just a very high quality product from that aspect. It's durable. It's 7 on the Mohs scale, so it's a diamond topaz itself that's going to scratch it. You can take a chainsaw to it, make sparks fly, make it all black, and you think you damaged it, you just wipe it off with a cloth. So it's a very durable product. So it's very easy to clean and maintain, which also adds to its longer life cycle as well. The carbon neutrality, I already talked about it. So it's certified carbon neutral from cradle to grave, and it comes with a 25-year finish and material warranty. Large format, we're talking about our max size. We can do 64 by 130 inches or 1630 by 3300 millimeters. This was really important to us. We gained that with our third production line that we introduced last year. Gets us past that 5-foot width, which helps us with a lot of unitized type applications and so forth. Lightweight, anywhere from 2 pounds to 10.8 pounds for a 20 millimeter, but we do it in 4 millimeter, 8 millimeter, 12, and 20. And how you select what you're going to do is going to depend on what kind of performance you need, what kind of attachment system, what kind of budget point you're trying to hit. A lot of different standard colors, from stone-like colors to solid colors, marbles, etc., limestone type colors. Being a facade person and not an interior person, I really like seeing the breadth of the limestone and natural stone type alternatives we have to the actual limestones, etc. You're talking about a product with superior physical properties, lighter weight, thinner, easier to work with. Facade applications. So when we're looking at different ways to get it on the wall, we've got ventilated rain screens, we've got curtain wall, and then we do the old-fashioned direct adhered in some cases, often in residential or entryways where the lobby is being extended to the facade. On the ventilated side, I'm not going to go through these, but we've got hidden mechanical, we've got hidden chemical type attachments, we've got visible mechanical, we've got visible clips, we've got rivets, we've got a wide breadth of ways to get it on the wall. So it's really going to depend on what kind of performance you need, and of course what the budget is. I wanted to talk about curtain wall integration. So when we look at this product Decton, as Chris was mentioning, you notice that we kind of lined up on the embodied carbon. It's because Decton is manufactured very similar to glass. So there's a lot of similarities between those. And that gives us a really nice integration into curtain walls, glazed in, captured or SSG systems, or unitized. So the same tools are used to move around, the same suction cups, the weights are similar, the dimensions are similar, very easy integration into curtain wall. And of course, we provide design assist, and that is really key when it comes to facades, depending on what blank slab or blank sheet material you're working with. Minimizing the amount of waste in the fabrication of panel has a big impact on the cost. So design assist is something we work on all day long, and we're here to do that. And then how do we supply? So this is very dependent on a lot of factors. It's dependent on construction schedule, depending on the type of system that's going to be used. We supply either full slabs to people that do all the fabrication themselves, or we provide cut to size in the instance where they may be glazing it in and they don't need any holes or grooves for mechanical attachment, and they're attaching with structural silicone, structural adhesives. And then we provide cut to size with what we call, from the Spanish side, mechanization, which means with holes or grooves put in it, depending if it's going to be an undercut system or a kerf system, or if it's going to be rivets, etc. Real key. And our turnaround time is on the outside 10 to 12 weeks right now. Always, always, always when we're doing ventilated or curtain wall, it's going to have a fiberglass mesh on the back of it for safety. And then a couple examples here. This is a nice example of a unitized job in Munich, Cap West. Cap West, the architect was Wheel Aritz Architects. We've got 135,000 square feet on there, and we supplied it to the curtain wall contractor. You can see second picture from the left is actually the Decton with the mesh on the back. They sent us the clips. We put them on in the factory, shipped them to their facility. They hung them off their wall units. And then, of course, they had their vision glass in there. They stacked on site. You can see in that second from right that there's no panels on there because they didn't know what their finished condition was going to be at grade. So they waited to get their site dimensions on that side. An example here in Vancouver is 8X on the Park that GBL Architects designed and KPS installed. The white area there, the flat area, that's Decton 12 millimeter with undercut anchors. The Pacific by Grosvenor, here you've got Again, undercut anchor installed by KPS and IBI and ACDF for the architects on that. And then one final look here is a case study out of Tel Aviv, the Toha. This is a building that's basically flipped on its head. The mechanical is down below. And you can see that in that second from left picture. You can see the X-shaped panels there. That's so that they can get ventilation to the mechanical. We had 11 different Decton colors on there. 6 of them are custom. And I'll just finish by saying, like I started, Decton is a unique and universal product. It gets used for countertops, flooring, wall cladding. It gets used for pedestal decks, pools, and of course, facades. And this example here is Rafa Nadal's Academy. Every hard surface you look on there is Cosentino Decton. So we look forward to talking to you about our product and what we can provide to the market. Thank you very much.
Thanks, Dean. And then we're going to finish off this session with 2 Jeffs. The first Jeff is Geoff Shellard from Guardian Glass to talk about bird-friendly glass. Welcome, Jeff.
Awesome. No, I think this is working. Check, baby, 1, 2, 3. Beautiful. You guys all awake? And if you're not, I'm going to make sure you are by the time we're done here, folks. We're going to talk about bird-friendly glass today, how to design with it, how to make your buildings look aesthetically valuable by using this type of product here, folks. So there is a better way to design our buildings to make sure that birds are not impacting the built environment, because they are impacting the built environment, guys. We can use different products like UV coatings. We can use etched glass. We can use fritted glass. You may have seen some of it out in the showroom there today. They're very distinct products, and they can enhance the beauty of your building. So we're going to talk about the dynamics of birds and glass. We're going to talk about bird-friendly testing and product comparisons, get a little bit into tools and resources. So the dynamics of birds and glass. Did you guys know that 5% of all the plants that humans eat and the pharmaceuticals we consume comes from bird pollination? So it's not just the birds that are pollinating, it's the birds and the bees. See what I did there? Sex education. You didn't think you were going to come here for that today, folks, but you did. Let's talk about controlling the pest population. Not talking about spade and neutering our pests. We're talking about birds eating 400 to 500 million tons of insects every single year. Why I like that is because I can stand up here without smacking bugs off myself constantly while talking to you. Also helps a little bit with evolution, right? If we don't have birds, what do you think happens to insects? They grow to the size of my hand, and they suck on the back of my neck while I'm trying to talk to every single one of you. That's not good for my mental health. Birds, good for your mental health. Why? Well, I don't have bugs sucking on my neck, but I can tell you this much. I love watching birds. I love watching hummingbirds, where they hover there like hovercrafts. Then you've got giant eagles flying across the sky. They're fascinating. So to kind of sum up, without birds, I'm incredibly hungry, I'm off my meds, I'm being chased by giant birds. It's not good for my mental health or for yours. So it's estimated that 1 billion birds die just in the US alone from impacting our built environment. That's right, we build all these great buildings. We didn't put into consideration that birds are going to hit them. In the state of Florida, 8 birds in one particular building, 8 birds impact this one building every single day. And they are struggling to figure out solutions around that. Birds are migrating north to south, south to north, and they can fly up to 80 hours at a given time. So imagine how tired you are driving 8 hours in your car one single day, and what are the likelihood that you're going to impact something? Well, birds are impacting the built environment. This little map here, March 22nd, 2023 at 9:30 at night, 38.7 million birds are in flight. I bet you didn't think that's how many birds were flying at any given point in time, let alone the fact they're flying at night. And you can see this map actually moves across the course of a day, so it starts at 38.7. At that point, it's just going to keep growing in numbers. Now, bird perception is a lot different than human perceptions. I can see roughly in a range with both my eyes, binocularly like this. Once I get out to this way, it gets a little bit more monocular into my peripheral vision. Now, if I'm a bird, I can see with my peripheral vision, back here, I should have done yoga this morning. But if I ask my bird friends to drive my car, guess what the vision is? It's more like this. right? So if I'm flying, what do you think I can see in my peripheral vision? Maybe some predators, maybe a nice tree to land in. So I zoom this way to hit the tree, but the tree is a reflection in the building, and now I've hit the ground, I'm dead. Birds can also see, some birds can see into the UV spectrum, so it's a little bit more dynamic with how they see, but because we're not birds, we can't necessarily understand how it is that they're viewing the buildings. So we got 4 major collision causes. We've got reflection, transmission, design, and lighting, and I'll get into all 4 of these a little bit here. So like I was saying, see that tree in the glass? Fly towards this tree. Well, the tree's over there. Bam, too late, I'm dead. Good, so I'm not gonna sugarcoat this. So what we're talking about, the death of birds. Bird transmission. Trees are over here, trees over there. Bam, into the clear glass. Again, I'm a dead bird. Now we've got the design of our buildings. Oh geez, I just flew into this giant space here. I go over here, I can't go over there. I can't go over there, where am I gonna go? At some point, I'm probably gonna hit part of the building, and again, I'm dead. Then we've got lighting. So what you may not know is that the Freedom Tower in the United States has this beautiful light at the top of it. Birds love to circle around this light because they are attracted to light. Now, when those birds get to the top, they cycle and they cycle. Oh my God, I'm so tired. Oh, concrete environment, that's what they hit because they're tired and they fall from the sky. So what did they do? They cycle that light every 20 minutes to make sure the birds aren't flying around that building. This is a 2-story building. I think there's a ham sandwich sitting over there I might want. Bam, bird flies into it because the glass looks clear during the night. During the day, this might be reflective glass, but at night, it's a very different scenario. So, speaking of impact, we have legislative impact. Where does our building codes come from? They come internationally, they go nationally, they come down to municipal. Then they make their way down to the city of Vancouver because they love to do their own thing. Seattle's kind of like that too. So we've got our codes. Our codes are driving these things. We have our institutions that are basically our hospitals, our schools. If you're trying to heal in a building, do you want to hear birds smacking against the glass all day long? Probably not. If you're a child and you're like this tall, oh my God, I'm trying to learn math and I've got birds slamming against the glass, that's not fun. Then we've got the performance of glass. Obviously, we're looking at our visual light transmission, solar heat gain, all these different factors we have to consider. Then we've got aesthetics. Oh my God, I got to consider that too. Do I want blue-green? Do I want iron? What sort of things do I want? And all of that comes down to cost, right? So at the end of the day, we've got these great designs and then we want to save the birds, but can we do it? Well, we do have options, folks. You can get to the part where you can design a building the way you want to and protect our fine feather friends. Isn't he cute? So let's talk about the testing methodology that the American Bird Conservancy basically came up with. Now, there's lots of different types of tests out there, but we're going to talk about the tunnel test. So basically what the ABC did is they went out and bribed a bunch of birds with some craft beer and said, come on in, guys, let's do some testing. And what they did is they put, notice this little net here, just to make sure you understand. When birds go down this tunnel, they're not impacting the glass. We're catching them in a net. So the birds fly down this flight path and they hit this pivot point. And they either fly up to the control glass, which is clear, or they fly down to the pattern glass. And what they're doing is determining what pattern is the best way to stop birds from hitting glass. So let's say we got 100 birds. 70 of them head towards the control glass. That's my avoidance index. The 30 that head towards the test glass, that's my threat factor. You probably might be familiar with seeing that. So they determined that a 2x4 rule is roughly the pattern that they want to have on glass to keep birds from impacting the built environment. And this is the magic number, folks, equal to or less than 30. You want equal to or less than 30 birds slamming into that pattern glass. And the reason why they came up with the 2x4 rule is because, well, let's see if I can mimic this. So 4 inches across, 2 inches high. They don't want to fly into that space. In fact, 2x2 is even better, but there's a lot of different patterns you can use to achieve a threat factor of 30 or less. And there's different options. You've got UV coatings, you've got your etched glass, and you have fritted options, and I'm going to tell you a little bit about each one of these. So UV glass, what's the benefit of UV glass? Well, it has a UV coating on one side of the glass, on surface 1. I will emphasize, you want your bird-friendly coating on surface number 1. Why? Birds can see it. You move it into the glass, they can't see it as easily. So UV coating from the inside, not really perceivable. From the outside, you can see it, but you can build that into your design aesthetics. Now, it is a laminated product, so what are the benefits of having lamination on the exterior of your building? One, you've got sound abatement, you've got threat protection, you have 99.9% of the UV light is filtered out as well. And look at that threat factor. I've got options down to 18 with a double-coated low E product on my outboard. So again, emphasis, surface number 1 of my bird-friendly product. That's why I like the etch product. It gives you a lot of options. Because we take a product that already has an etch on it, an etch pattern. Then what we do is we at Guardian, or any other magic fabricator out there, can then put the low E on surface number 2. Because it's on surface number 2, it means that my solar heat gain is intact. So with a pattern that's either a vertical stripe, a horizontal stripe, say a 2x5 dot, a 2x4, you can do 2x2, you can do randomized. There's a lot of options out there, folks, and they just keep growing. I can keep my solar heat gain exactly where it was designed to be. In a double low E coating, if I'm at 0.39, what do you think happens when I move that low E to surface number 3 if I just want to use a monolithic fritted glass on the outboard? Jumps up by about 4 points. Now that's not too bad, but maybe you want to keep that low or that solar heat gain intact. Now what if I put triple silver on my surface number 3 and I've got a solar heat gain of 0.27? It actually jumps up by about 9 to 10 points. So unless you're designing for passive, you've now taken that unit, you spent all this money on my triple low E coating, and I've just spent money for nothing because my solar heat gain went up. So let's talk about fritted glass. So frit gives you some options. You've got some white dots, some gray dots, some different patterns. It gives you some variability that you can use. The only thing with that is if you're not laminating it with a low E coating on surface number 4, it means you're either doing one of two things. You're putting, again, your low E onto surface number 3, and that means you're increasing your solar heat gain. If you flip it around, put your low E on surface number 2, put your frit on 3. What do you think happens to the birds? What was I saying before about which surface I want my bird-friendly coating on? Thank you very much. Oh, I didn't even have to pull that out of you. So unfortunately, I don't have a lot of great pictures of bird-friendly glass because the problem is that it's really hard to see, right? So you can see how incorporated into the Sedgwick Zoo here, this actually has a UV coating on it, but I can't really see it from afar. Get in close and you will see it. We got the Detroit Zoo. Again, I didn't have great pictures of this one, but I'll tell you a little bit about it. What we did on the side lights is we used laminated UV coated glass, safety glass, kept the birds from flying into the vestibule. Then what we did is we put a dotted pattern up at the top. We use the exact same low E on both products. We had design options. So what happens when you get to your product or your project and you're deciding, geez, what do I do? Well, you can go to, say, guardianglass.com or any of your fabricator or your manufacturer's websites. You can find things like glass analytics, performance calculators, energy calculators. If you're using Autodesk and Revit, you can use BIM objects. You can use a product master spec if you hate typing words over and over again. Then you can order samples. I don't recommend a 4x6. It's a very small piece. Get yourself some 12x12, get yourself some mock-ups. And then if you're really stumped, you can email me or you can call me. You can text me, you can scan this QR code. Let's just leave that there. Nobody's getting their cameras out. That's okay. You can see me later. But just don't send carrier pigeons to my house because I don't have bird friendly installed in my townhouse. Thank you very much. 3 minutes left. Holy cow.
Thanks, Jeff. That was a great presentation. And then our last one of the session is with Jeff Kerr, Building Facades and Sustainability, and he's from Engineered Assemblies. So all of the presenters in this group, could you please stay after this presentation for a photo? And then we have coffee, and we'll see you after the break, but you'll see me again. So here's Jeff.
Thank you. Check 1, 2. Okay. That was a fantastic presentation. Great energy from you, Jeff. Thank you. Very, very significant presentation, very responsible. I'm Jeff Kerr. I'm the technical director with Engineered Assemblies, and I'm here to talk to you today about maximizing sustainability through building facades. Ah, yes. Okay. So if we do that, okay, and back. Super. So I guess starting off, you know, the whole idea of sustainability is a big topic today, and when we think about it, I guess I'm here to get people to think a little bit more about how facades fit into that mixture. So with that in mind, we'll give a little introduction to Engineer Assemblies, who we are. Ultimately, we are a facade material supplier. We're national, 16 years old, and although we supply a number of high-performance facade materials, our specialty is truly how to get materials onto buildings. So we're really jacked by the science of detailing and making things perform the best way they can. And that's going to fit in very well to today's presentation. So speaking a language, uniting the House of Design with the field of construction is key to achieving the best performance we can. So with that in mind, today's agenda, we're going to look at facade and the relationship we have to sustainability. And this is going to be a generic presentation about facades as they pertain more specifically to rear-ventilated rain screen systems. So building resilience through design and installation. And we're going to talk about the key challenges that we face when we're doing this, regardless of the skins that we choose to put on the outside of our rain screen system. So just so we're all on the same page today, in terms of sustainability, what do I mean when I'm talking about it? Well, exactly as the slide suggests, meeting our own current needs without compromising the ability of future generations to meet theirs. So environment is the substantial dictator. Now, this is a bit ironic because we are having to practice better forms of sustainability to defend the environment, and yet it's the environment that really is going to challenge our facade systems more than anything. And environment is challenging us more than it probably ever has before. So we're building for a moving target, and it's generally moving in a more severe direction, okay? And we have more change. So with that in mind, building for the future of extreme weather is really what we're looking at. So facades, what's the big deal? Why would I choose to talk so much about facades and sustainability? Well, amazingly enough, I mean, facades are the primary passive control system for thermal integrity. And as far as that's concerned, it's the only line of defense for environmental influences. So essentially, they're the infantry protecting our buildings. So in this primary passive control system, and this is something I want you to keep in mind throughout this presentation, it is the most significant one for the whole building. Why else are facades important? Well, let's look at design, function, and form. Form is just as important. Design matters in every manner that it's employed. The built environment, relationship between physical space and social consequences. So we can't just build things that perform well from a physical standpoint, but not address the sociological implications, sustainability of mental health. The environments that we're building are going to affect people socially, and that's important as well. And that's going to be transmitted, or at least transferred as clearly as possible through the facade system. It's the face. So when we talk about sustainability, oftentimes we jump to materials. What kind of materials are we using? So let's take a look at materials and see what we've got. Well, we've got some lightweight, high performance. We have a number of lightweight, high performance solutions out there from a number of suppliers, manufacturers, everything from ceramic, what some people choose to term terracotta, but ultimately, the proper term is ceramic. High-density fiber cement. We've got phenolic core HPLs, lightweight natural stone, such as slate, for example, and porcelain, perhaps extruded porcelain. We've got a lot of materials out there to choose from. These are some of them. These are some that have seen a stage in this province, certainly, and throughout Canada. And what do these things have in common? Well, those systems, they all have, as a speaker was talking probably about 3 speakers ago, they have pretty impressive environmental product declarations. So we look at the integrity of those materials, first of all, but they all function in a high-performance rain screen system. Okay? And this is not new to us in Canada, and it's certainly not new out here. Okay? I come from the eastern side of the country. It's just as germane over there as it is here, and it's probably, for all intents and purposes, the best facade solution for the majority of applications in this climate. And when we talk about a rain screen system, because there's probably as many definitions for rain screen as there are for free-range chicken, okay? So when we look at rain screen system, we're talking about an exterior facade, could be an open joint system or closed joint, but we've got unobstructed active plenum for ventilation, which is going to help the facade material in a lot of cases and help things beyond that. Next, that black sheet is going to be a membrane. It's going to be a high perm rate, breathable membrane, but it's going to be a secondary drainage plane. So if we do have any precipitation coming through the system, it's going to stop there, okay, hopefully flow down. We're probably going to manage the majority of precipitation, 99% of it, right here in this point, and then beyond that, we could have an outboard insulated thermally broken substructure. Now, substructures are really key. I'm going to touch on them a little bit, but this is a system that most of those materials, all those materials are going to apply to, and a lot more. So with that in mind, sustainability and materials. Okay, back to materials. So embodied energy. Materials are one component of sustainability when we look at buildings in this particular context. So initial and reoccurring in terms of embodied energy. Initial is the energy it takes to manufacture the product, which we've looked at a couple of presentations ago. And recurring, initial, manufacture it and get it to site, get it up on the building. Recurring is the energy it takes to maintain or replace the product if it doesn't perform properly. Now, this is where things are starting to get a little bit deeper, because products need to be designed in properly and they need to be installed properly in order to perform, okay? If we don't do that, then we're going to defeat a lot of the benefit of us trying to, strive for good sustainability, because things are going to end up in landfill. We can't have materials failing, and materials failing are generally a result of them being designed in incorrectly to incorrect applications, or not installed properly. And this is rarely something that we touch upon when we look at materials, controlling the installation of materials so that they can achieve their due lifespan. So durability of buildings, by having these high performance rain screen systems with good materials. Durability is not a material property. It is, however, a function of a material's relationship to its environment. So there's a subjectivity to it. It's also a function of a material's installation and maintenance, okay? So when we look at something like that, designing something improperly, Ted Keswick suggests underwear and purlins. Steel makes great purlins, bad underwear, okay? So we want to make sure that we're putting the emphasis on the correct syllable. And then sustainability through design and construction, what I was leaning towards there. Okay, this is where we need to ensure that we've got the correct guidance in the industry to make sure that our single most important passive control system is going to be able to do its job. We need installation training, subcontracting of installation. That's a touchy one, specifically in this climate of installation where oftentimes things are subcontracted and then subbed and subbed and subbed. Are we speaking to the right people? Shop drawings, great shop drawings. Are we insisting on great shop drawings? Because shop drawings ultimately are something that are going to instruct the installers on the location of the substructure so that it meets the needs of the materials. Are we getting L over 300 deflection limit because we've got our spacings correct? Where are our fasteners going in? Are they fixed in floating points respecting the expansion and contraction of the material of the substructure that's moving, okay? So designing for live buildings. Our buildings are live. Our buildings are dynamic in most cases, okay? So when we look at that and we look at the idea of having fantastic shop drawings for trades to follow so that when trades sub up, or when people get sick and leave site, it's not a bunch of guesswork. Material is not going to be the victim. We're going to be addressing things in the shop drawings, things like crossing over traditional points of deflection. How is our substructure for these lightweight, high-performance facade systems, how is it going to address these? Because this isn't stuff that's typically included in architectural drawings, and nor does it need to be if it's in great shop drawings. Okay, but we need to address these things because things like that vertical hat bar that we've got in here, holding the material up, that gives us our unobstructive active plenum, that can't cross over traditional points of deflection like a concrete slab because that's moving. And 18 gauge steel is not going to stop a superstructure from moving. So with the superstructure moving, is it going to tear our system apart? That high passive control system that we have to hopefully give us that sustainability. And if we don't do this, well, obviously, we're left with failure of a system, okay? And we've got a breach, just like we would have in a dam. We've got water leaking. In this case, we've got heat going in and out, maybe. So let's recap here for a moment. Lifespan of materials is determined by materials being quality materials, being designed in properly, and installation, and us controlling as much as we can through that process to make sure that materials are respected properly. So suitable materials, relevant design of high-performance facade systems, high-performance rain screens, installation training in shops. Are our current industry systems sufficient? I'm going to say no, they're not. So how about a quality control system? Because it needs to be a holistic approach. We need to embrace this whole thing together. We do have great standards out there. So when we look at things like CSA S478, that's a fantastic standard. It's national. And like a drop-down menu, different regions get to pick and choose whether they want to use it or not. But this is a great, and I don't have stock in this or anything. It's just a great system because it speaks to sustainability through serviceability and serviceable lifespan. Is a material that you're putting up there serviceable, and how long is it serviceable for? So great standard. Are we embracing it? We've got the tools out there. But how about a quality control system? How do we manage all of this? How would we manage all of this? Because we have challenges and we have solutions. So a pathway to sustainability through compliance, a response to the need for transparency, due diligence, which is a term that's not used enough, and proper execution of the installation of that rain screen facade. Well, if we had a certified quality control program, maybe it would include something like a contract between the architect as the client's representative, the GC, the installer, and the system provider, the person who provides the material, provides the intel on how the material needs to be treated. So software to manage installation progression, uniting everybody up there, so everybody's united in real time. Drafting and engineering would be conducted by the system provider. They should know their material best, right? Should they not oversee the drafting and engineering of this to make sure that it's respected properly? I think so. Then we would have a comprehensive review of the drafting and installation training, sitting down with the installer who's going to put this stuff up and going over these comprehensive shop drawings to make sure they understand what they're doing. And shop drawings would include icons at specific details, details of ventilation, details where membranes are tying together, etc. And we would have to have photographic evidence. And we'd have site reviews. So we'd have little icons like cameras at certain points, and we'd need to have pictures taken by the installer. And some of them are of the substructure, and some of them are of the facade when it's completed. They'd be put into the software program, just simply downloaded, and everybody would get them in real time, and everybody could review them, particularly the system provider, who could say, that's not the way my material needs to be finished in terms of ventilation gap, and we would respond to it. So another set of eyes specifically for the facade system, that primary passive control system. So if our buildings are to be sustainable, again, that thing needs to be high performance, it needs to work well. We'd have a specification that would be in section 1. So the generals would see it and it would flow down through to subtrades and they would be able to bid on it. And they would include it within their bid and it would be a system that ties everybody together, uniting the house of design with the field of construction. So when we've got something like this, we would have a facade sustainability program, and it would be a holistic endeavor, okay? So the challenge here is to build a relative resilient, high-performance, sustainable, primary passive environmental control system. I think that's fairly reasonable. Facades, as I suggested in the beginning, are the infantry of building sustainability. So we need to make sure that they're designed in and built as best as possible, and that's going to be a response to sustainability and building resilience. And you can speak to us more about that, certainly myself. So I thank you very much for your time. And let's think a little bit more about facades and sustainability. Thank you.
Okay, this is our last break. If all of the presenters from this group could please come up for a photo opportunity, please go out and recharge and have some coffee, and we'll see you in 20 minutes or so. I think there'll be a bell out. We are going to get started on the last session. Unfortunately, Joel Schwartz fell ill and we couldn't connect with him live feed either. He's just not feeling very well. So unfortunately, we won't be presenting the offshore fenestration systems. But the good news is we are back on schedule. We will finish on time. And we have 2 more presentations to go. So we've got one 15-minute one with Dr. Chengde Huang, who will do application of high-performance glass to reduce carbon emission. And then we have a very exciting panel at the end to talk about the curve. So please join me in welcoming Chengde Huang, and we'll see you in 15 minutes.
Okay. So good afternoon, everybody. I'm Chengde from China Southern Glass. Today I'll be talking about application of high-performance glass to reduce the carbon emission. Use this one?
Yes. The big button.
Big button. Okay. So my presentation will be 3 parts. First, introduction, and the second, talk about glass configuration performance. And the third part will just present you some projects we've done before. In China, have said to the common goals, we 2030 the carbon peaking, and 2060 the carbon neutrality. From the statistical data show that the carbon emission of buildings in China, like 2019, the whole cycle carbon emission of buildings accounts for about 50%, over 50% of the total emission of China, in which the production of building materials accounts for 28%, and the building construction accounts for 1%. And the building operation, the air conditioners and light, building operation accounts for 21%, close to 22%. So you can say that the lower carbon emission of buildings is crucial to the to carbon goals of China. China has implemented new code, GB 55015, called General Code for Energy Efficiency and Renewable Energy Application in your buildings in 2021. Besides the higher energy efficiency standard, the new code stipulated specific requirement on carbon emission. In 2019, China already implemented national standard called standard for building carbon emission calculation. So they have the detailed procedures to how to calculate the carbon emission of buildings. And in the standard, this is the only necessary basic data for calculation of carbon emission. And the second part, glass configuration and performance. Obviously, different high-performance glass products are needed for different climate zones for the most effective reduction of carbon emission of buildings. Like in Beijing, in northern China, in the summer it's extremely hot. Nowadays in Beijing, in summer days we could get over 40 degrees the environment temperatures. But in the winter, in Beijing, it's below zero, probably below 10 below 0 degrees centigrade. But in southern China, it's only like in Shenzhen, Guangzhou, Hong Kong, there is a hot summer, but it's a warmer winter. So it's a different climate zones. Like in Beijing in the summer, the best glass should be this 777 alloy glass, in the summer to prevent the solar heat from coming inside, to save the energy for air conditioners. But during winter times, you also need to lower the U values to for energy efficiency. But in the southern China cities like Guangzhou, Shenzhen, the 777 alarm could be to the work to prevent the solar IR radiation from coming inside. There's a typical glass configuration for like Beijing cities with a 777 alloy. This is for three different projects, different coatings, different colors. On the second surface, we apply the 777 alloy coating to prevent the solar heat from coming inside in summer days. And we apply another alloy coating on the number 4 surface called BW88 to lower the U values for winter times. Because you can see that here that the U values could be just double glazing with 2 coatings could achieve a U value around 1.1. Of course, we have some other projects need higher performance. We could, use a triple glazing. With triple glazing with 2 coatings, we could get a U values below 1.0. And then with triple glazing, we can apply 3 coatings. In that case, we can achieve a U value around 0.7, even below that, probably 0.6 U values for for higher requirement. And then when you define the new term called GIR, GIR accounts for the total solar air comes inside, because the solar air is the energy cost temporarily increase in the room during some times, summer days. So the GIR is more specific, more precisely to describe the energy glass performance against the solar heat. With the 777 alloy, you could see the GIR, all the glass, different glass could have a GIR below 3%. That means only about below 3% of solar air coming inside. So in summer days, you just need small air conditioners, just a little energy to balance the heat. And we just heard they found out there's CIR called color rendering index. That means the how clear the glass. When you install glass on the windows, you see outside, you see the trees, see the flowers, the natural colors. The higher the better. You can see the CIR we could achieve about 90%. That means very clear. And the visible transmittance could achieve a higher or lower, depending on the requirement of daylight. because different projects need different daylight. For office buildings, probably you need some medium visible transmittance. But for residents, probably need a higher visible light transmittance because the small windows need more daylight. This is a typical glass for southern cities in China, because there has a hot summer and a warmer winter, so do not need the extremely low U values. We only apply a triple silver coating on the second surface, so it's cooling enough for the energy efficiency. You can see that the already GR values just around 3%. If we use the low iron glass as substrate, we can achieve all the glass with GR below around 3%. That means only a little the solar air comes inside. That means when we install the glass, triple silver glass on the windows, even during the extremely hot days in the summer, from inside it's cool enough. Even when you stay close to the glass, you can feel it's cool because no heat comes inside. And we roughly calculated the carbon emission, just compare with the clear glass HUs for different the climate rooms. Well, here just is the data for you to have an idea about. If we just compare with the clear glass HU, to the double silver low E could reduce to about 25 to 35 kilograms carbon emission per square meters per year. Square meters of glass, not the buildings. Just we calculate for every square meters of glass. For triple silver low E, we can reduce compare with the clear glass, could reduce about 30 to 40 kilograms of carbon emission, carbon dioxide emission. So that means that you can see that the triple silver low E is the best for reduction of the carbon emission of buildings. So in China, we CSG as the leading glass manufacturer in China, we promote in China market the best performance glass for different climate zones. Triple silver low E actually is applicable for every cities in China, because in China we divide in different climate zones, but almost all the cities, even in northern cities like in Beijing, probably Shenyang, Harbin, in the summer it's still very hot. So in the summer times you need triple silver low E anywhere in China, even in northern cities. Here just some pictures of this glass. You can see our glass, different triple silver glass. It's very clear. You can see the colors, red, green, it's very clear. That means transparent. The CRI index is high enough, so you have a natural view from inside. And for the spandrel, we have tried to with the freight patterns to make a spandrel and a vision matching. In this way, we can have done many projects with perfect matching of the spandrel and the vision glass. And also, you can supply the BIPV glass for for the skylight or the spandrels, or in some projects even for the vision for windows, window glass. The patterns, they could be changed. We can use the coating technology to modify the colors, brightness, and according to the design requirement. Because it's a very short presentation, so I just show you some projects I've done before. This the double coating with triple silver low plus BW88. For this project is in Beijing. Beijing, there's a triple silver low gray color. And it's gray triple silver low plus the BW88. This is green, the triple silver low E. Outside it looks green, but inside the color is clear. We just use a coating to produce the green colors from outside. And there's a light blue, that's neutral. There's a gray, neutral again. The silver gray, silver gray means with a higher reflectivity. They're neutral again. That means you will have different colors, any kind of colors, brightness, for different project requirements. Because we supplied triple silver glass, more than 10 years ago. We start from 2009 to supply projects, triple silver glass to overseas projects. So we have over 10 years experience. We have different various options, different colors, different brightness, to meet the different projects and requirements. And another one, the team has done some jumbo size IGUs. This height of IGU over 10 meters. We have done many projects. Here, just these are some of the jumbo size IGU we had done before. You can see at least here the size, the waist, the height. And here's just a picture show you that the jumbo size IGUs we had done. This one is in Wuhan in central China. Then this one is UAE, the jumbo size projects. So that's all of my presentation because time is, I think, is just on time for that. Thank you.
Okay, thank you very much. And on to the last event of the day. We're going to close with a panel with a great topic. Anything that starts with what could go wrong is definitely compelling. So if this panel can stick around to take a photo, and if everyone wants to stay around again for a drink and social hour, we look forward to that. So I am bringing up onto the stage the moderator, Gregory of Brivia Group, Pattrick McMorrow of Arcadis IBI Group, Evan Lavelle of Front Incorporated, Lauren Ricketts of RDH Building Science, and John Douglas of Alutech. So they're here to talk about the curve, which will be very exciting. Come on up.
These are deep chairs.
Very nice. Oh, Rick's sitting with us too.
Yeah.
Wasn't sure if we had you at the podium.
Seems funny sitting here. Well, welcome everybody, and it's a pleasure to be here with our key members of our team, who I would introduce. I'll start with Pattrick McMorrow. He's with IBI. He's they're the architect of record on the project.
Central one.
Which is the pointer? Keep holding. Thanks. Hope I can remember that. And Pattrick is the lead architect on the curve. He's Passive House certified, and he's leading our team of experts. Sitting a couple of seats down from me is Lauren Ricketts with RDH. He's a director for RDH of Western Canada, and is the Passive House consultant and envelope consultant on our project. Sitting next to me is John Douglas. He's with Alutech, and he is the director for pre-construction for his company, and is the design assist contractor or consultant on our project. Evan Lavelle is a principal with Front out of the UK. He's the engineering firm that is secured by Alutech as their design engineer, and so also providing us with pre-construction services. The first question in the brochure says, why are we doing a passive house project of this size and scope? And I just wanted to maybe start off with a bit of background of how we got where we are. I guess I should first introduce myself. I'm Rick Gregory, and with Brivia, as it says in the brochure. Brivia is a developer out of Montreal who has forayed into Vancouver over the last couple of years. We have a project in West Vancouver, a 9-acre site in the middle of West Vancouver, and we have this beautiful site downtown that is at the apex of the peninsula that we're building the curve on. So in 2004, which is right about somewhere in here on this graph, my son asked me if I had seen the Keeling curve. He was at UBC. He's with us today. His name's Ryan. And I said, no, what's the Keeling curve? It's a graph of carbon dioxide that a chap named Charles Keeling had started in 1958. He had discovered 4 years earlier that he could measure carbon dioxide very accurately to within 1/100th of a part per million. And so he set up an observatory in Mauna Loa and started measuring. His first measurement came out in 1958. And by the time I saw it in 2004, it was not just increasing and going up and down each year as the planet sort of breathed in and out between the winter and the summer, but there was an arc, there was a slight curve to it, and so I knew in 1850 that we were at 280 parts per million. So I just mapped the blue line, which is just a sinusoidal exponential curve, onto the existing red data, and then kept plotting it year after year. I bet a friend in 2004 who lived in Burlington that in May of 2014, 10 years hence, we would break 400 parts per million if my graph was accurate. And I bet him a beer, and I won the beer. But I kept mapping it after 2014, and in the last 4 or 5 years, you can see the blue curve, which is a scary curve to begin with, we're actually coming off that curve. And so that's the motivation for me personally in terms of this passive house project. And I think now I'll get Pattrick just to go through and give you a bit of background on the curve itself before we start asking questions. So Pattrick?
Yeah, thanks, Rick. Do you want to flip through the slides I take that from you. Thank you. Okay. Big button. Okay, great. So we should note I'm Pattrick, and I work with IBI Group Architects, formerly IBI, and Arcadis is our name. But we have a design architect on the project, Tom Wright, from London, UK. And we've introduced the rest of the team. But for those to introduce the tower, it's downtown site adjacent to Nelson Park, and a very compact site. So one of the highest FSR densities we've seen in the city at 60 stories. And a lot of the reason that we're achieving that is because we're going above and beyond to certify to passive house standard. And so we're this project is aiming to address that Keeling curve and the idea of buildings emitting and being a concern. This is changing the paradigm for that, and buildings becoming a solution to climate and real climate action through construction to a higher standard and a blueprint for buildings in the future. So this is a site adjacent to Nelson Park. As you can see, people in the city will be familiar with the Butterfly Tower, our neighbor, and then Nelson Park adjacent. And so this is an idea of where it's sitting. And the tower itself, if we get to the architectural plan, sits central symmetrically, which is unconventional for a passive house project. Typically, we're thinking about passive house projects, orienting themselves a particular direction, but that's part of the challenge that we've seen here when you're building, market condominiums and social housing, which is what the building is made up of, 25% social housing with the remainder in market. We're looking at a product that has to be in some way symmetrical. It has to address the city at all angles. it's developed as a tower that is a 360-degree, incredible, iconic piece of architecture. And so some of those basic principles of passive house, which have developed, cannot be applied at this scale. And so we're looking at it from a different lens. We're looking at it, this giant challenge, and our solution is going to have to come from a different place to previous passive house lessons learned. So, previously, I'm going to flip through these slides. I think we're ready to talk to you, Lauren.
I can take over if you'd like.
yeah, we can keep it discussional. I was going to just maybe finish with our IBI's first passive house project in Vancouver, a 7-story passive house tower, and that was it's a high-rise building, artist studios on Pacific Street. But that was had the benefit of being able to orient itself south, east, and west, and deal with solar gains and so on in that way. And that's kind of conventional, but also window wall ratio became a huge part of that project, where we aim to keep the overall glass ratio to 20%, 25%. And in this challenge here, we've got market condominiums. That's not really a solution we can go with. So we've really been able to set a challenge. And you can get more into that, Lauren.
For sure. Pass me that down. Yep. Am I mic'd up? There we go. Is there a back button? Perfect. All right. So I think Pattrick did a great job of kind of laying the groundwork for the project, and yeah, certainly the orientation is kind of one thing that we don't have a lot of control over. So it's one of the initial challenges. We've got a few other things that make this project kind of a little different than some of the other passive house projects that we've worked on. I think one is just the nature of it being largely market condo, and so we're looking to maintain kind of those high window to wall ratios, relatively speaking. We're selling these units, and so that's something that kind of maybe initially flies in the face of passive house a little bit, and just means that we're kind of working hard to maintain that all the way throughout the project. The other part of this project that's challenging is maybe not so passive house related, but it is, it's curved, it is the curve. So it's kind of curved in all directions. And certainly from just a fabrication standpoint, a panelization standpoint, trying to come up with ways of doing that sort of efficiently, being able to sort of honor the geometry of the project, and then also hit the performance objective. That's something we've been putting a lot of thought into. It's also quite tall, obviously. And so when we're thinking about, 60-story passive house, that's not something that's really been done before. And so we're taking, these ideas of highly insulated facades, airtight facades, and really bringing them over into this world of high-rise construction. So looking at systems and ways of building that haven't necessarily had that kind of performance in the past. So that's been something we spend a lot of time working through as a design team. We're also tasked sort of with the beginning of this project with this kind of mandate, or this marching orders of looks like a curtain wall. And so the idea of this, this tower is going to stand out on the skyline of Vancouver. It needs to look good. It needs to, honor the architectural intent. And we don't want it to, sort of look, point out and say, that one's a passive house. You can tell just by looking at it. So we did really want to make sure that we were able to get a building that was going to look how it should on the skyline of the city. And then lastly, this building has balconies, has a lot of balconies actually. And so it's got balconies on every floor. And obviously that creates sort of a thermal bridging challenge. It also creates some complexity in terms of the fabrication and the installation of the panels. So that's sort of another aspect. So the combination of those things really creates a project that is pretty unique. Not a lot of other projects are going to have all of those things going on. And so sort of set the challenge for all of us to work through here.
So, Lauren, we started off looking at a unitized curtain wall system, but we didn't end up going down that route. Can you explain why?
Yeah, I think we looked at a whole bunch of different systems, as you know, Rick. Unitized curtain wall, different ways of panelizing it, and we've kind of landed, I think you'll see a little bit later, sort of on this kind of a more of a mega panel type solution.
And really the interesting thing about it was it wasn't so much about the glazed areas. The glazed areas, we're obviously looking at sort of triple glazed, extrusions with large thermal breaks in them, that kind of thing. It really came down to the opaque areas. And so when you're looking at a unitized curtain wall system, you're just quite limited by the spandrels. And so we had to look at ways of getting a lot more thermal performance out of those opaque areas. This is just kind of a simple illustration of some of the studies that we were looking at, but some of the work that we did early on was kind of working with the design team to come up with architectural solutions so that the design, the architectural intent of the building incorporated things that were going to make achieving our passive house performance easier. And so one of those was we kind of recognized right away or pretty early on that this idea of having kind of flush glass, flush opaque areas with the glass was really going to hit us pretty hard in terms of performance. And so we started doing thermal models of the different mullion conditions, the opaque to vision area transitions, and realized that if we were able to push that out a little bit and kind of build that into the architectural design of the building, then that was going to give us a lot more freedom in terms of being able to over-insulate the frames, get more exterior insulation on the building, and achieve the performance. So that's a big part of why we didn't end up with sort of just a straight unitized system and move more towards this kind of mega panel solution.
So, John, when you came on board, and you must have gone into your with your team and looked at the project and thought there's some challenges here. What would you say were your biggest challenges that you were facing?
It popped up between a conversation between myself and Evan one night after we started to look at the project. And the principle that we saw on this was we had to reduce the framing joints across all of these systems. And that's why we really pushed the mega panel idea. I mean, this essentially reduces that frame loss on your verticals massively all the way around. It has obviously a lot of challenges as well. So again, it's curved, so that you've got the very large curved mega panels, like 10.8 meters by 2.8 meters. And then you've got the interfaces where they run into a J panel as they return around the corners, which is exceptionally tricky when you're dealing with the seismic requirements on top of all of the passive house requirements. So that's the reason why we went in that direction for mega panels, yeah.
And Evan, do you want to add to that? I mean, you've got some.
Yeah, I think there's a pretty good slide here that may illustrate some of those concepts. So, I mean, just let it go. Yeah, looking at sorry about that. I don't know, conventional sort of approach, either unitized or a smaller panel approach. Yeah, it's really you end up with a lot of edge conditions and framing conditions where most of your heat loss is, and also all of your air infiltration occurs, which both work against the passive house concepts. Even a large format unitized panel still has an enormous amount of edge relative to glass, relative to opaque zones, which no matter how well you make your center panel perform, your edge is always going to fight you. And so a really fantastic approach is just to panelize as large as possible. In this case, we're using a container as the restrictive element, exactly. And filling up one container with several panels, as long as you can get them. And this does a lot of things. One, you're in the factory, your construction quality can be quite high and it's very controllable. And then two, your edge conditions on site where you're having unitization occur or your seals occur is the amount is greatly reduced, and so your air loss is reduced, your heat loss is reduced, and you can generally achieve a much higher quality product in the end, which I think for a building of this, the site, the proximity, and I think the challenges Brivia and the architect set out was kind of led us to a mega panel route, which also led RDH to, I think their initial study was a mega panel. This I think came out several years ago, and
I mean, certainly we were kind of I think thinking about a lot of the things that Evan was just touching on, and then also looking around at precedents for these kinds of buildings. And there aren't that many, but this is one that's in New York and is a passive house and isn't 60 stories tall, but is a little certainly is kind of in the high rise category, I guess. And they took a prefabrication approach. They took sort of a mega panel approach, and so kind of looking at that and saying, okay, that looks like a reasonable starting point, kind of got us down the road. And then we did also have sort of some local, maybe just hit the next button there, some local experience. This is Brock Commons. I'm sure lots of folks here will have seen and heard about Brock, but it, probably most famous for being mass timber, but it was also sort of this large format panel installed on the outside. And it's not a passive house, but we knew if we'd put, 4 or 6 inches of extra insulation on the outside, it probably could have been. And so it's sort of starting from that point, we knew that, this is something we could do here locally as well.
There's a fair amount of advanced technology in this facade, Lauren, and maybe you can talk about what that technology is and the risks that go along with it.
Sure. Yeah, we've looked at a lot of different sort of technological solutions for this project, which has definitely been pretty fun and interesting. Some of them we've heard about in the sessions today. One of the ones that we're looking at is electrochromic glazing. So looking at, particularly with the curve of the building, blinds become kind of problematic. There's ways of doing that. But we're also, trying to balance that heat gain that helps us from a passive house modeling perspective. It, reduces the heating demand, helps us to comply with the targets. But then also wanting the suites to be comfortable, desirable to be in, marketable to people who are going there and buying them. So electrochromic glazing is one of those things that we're pursuing as a way of being able to kind of balance those, right? So that we can get that heat gain when we want it, and we can also get that shading when we don't. Whenever we're looking at sort of newer technologies, there's always a sort of fair amount of due diligence. I think someone earlier said that hasn't been said enough. So that's really something that's kind of part of the process is vetting these technologies. And in certain cases, coming up with even like new testing protocols, not just sort of the ASTM standards, but things that go beyond that, just to really prove out this is going to work. It's going to work at scale. Certainly we want to make sure that this building is going to last and it's going to work for the long term. And so that's sort of, taking these new things and then, building in that due diligence as part of the process to manage the risk side.
And Pattrick, maybe you can talk about penetrations for fresh air through the facade, how we differ maybe from other buildings.
Yeah. I mean, the mechanical system for the building, because it's passive house, it has to be direct outside air ventilated into every room, and that's obviously going to be really important from the outset of how this building is going to be set up. And so we arrived upon a solution with a central air system, which is a common Swigon air handling unit. It's passive house certified, and we've seen it used in the industry in BC. But this is looking at it in a whole new scale, where you're going to ventilate across 60 stories vertically with ducting, and then bring that air. But the huge benefit and advantage there is that there's far less penetrations through the envelope. It's this facade becomes very slick, very sleek without, ventilation unit in each suite, or even grouped with suites or grouped with floors would really mean we're looking for locations to have louvers and ducting in the exterior of the building. We're looking for drops to duct that air, whereas here we're returning back to the core, and there's central vertical shafts moving the air. We've also been able to develop the solutions around how that air is delivering heating and cooling to the suites. And that kind of ties into our decision on pursuing electrochromic glass and how this building is going to perform into the future. It's really exciting to be modeling this now, but we've been working with RDH and looking at what future climate files are going to be like, and how big a benefit things like control of your solar heat gain is going to be, and how this building will be able to adapt to particular weather events, but still maintain that very low overall heating demand in the wintertime.
Thanks, Pattrick. John, the logistics of this seem like a nightmare. You've got float glass that gets manufactured in one place. You've got electrochromic glass that'll be manufactured in another. You've got potentially vacuum glass, I understand we're looking at as well. You've got to create IGUs. You've got to get them over to your facility in Doha, Qatar. You've got to get the aluminum extruded and all put together and shipped to the, like, how with so many different different manufacturers in so many different locations, logistics must be a bit of a nightmare.
Suppose we're in a very lucky position in the company that I'm in. We're fully vertically and horizontally integrated. So a lot of these processes, as in the processing of glass, the extrusion, even the smelting, it's not the smelting isn't in-house, but extrusion, painting, glass processing, that's all in-house in our company. So even on the aluminium, say the extrusion, the smelting plant is from Hydro, is 20 minutes away from our plant. So the majority of actual incoming materials are quite close to us, and all of the processing and assembly of those materials are done within a 20-minute kind of 20-minute radius of our central factories. The big challenge is the logistics of from Doha on the very large mega panels to here, and then the storage of same at an offsite area, so that they can be called off on a daily basis into the actual site. Because what you don't want to do is you don't want to clog up your site with massive panels all around the edges. So you need to be able to call them off from an actual from a yard close by, basically. So that's the challenge. It's more the from Qatar to here, and then the daily logistics, I would think, is the big challenge of the project. Yeah.
Okay, thanks, John. Evan, on the design approach that you're taking, there's a lot of sort of going ahead and coming back and forth, almost like an iterative approach. Maybe you can talk a little bit how that's been going and how you foresee that going.
Who's got the clicker? Here we go. I mean, it's very interesting, primarily because the bar is set so high, and it presents a lot of challenges because you're dealing with trying to bring in conventional construction strategies, but do it in a slightly unconventional way, but then also have a U value target that is extremely low, but then having a lot of like I think Pattrick hit on it really well, is this is a very unconventional passive house because we're not able to use a lot of the tools in the toolbook because it goes against what our market kind of condominium or apartment building needs to be. And so I think I got some slides on this. There's some interesting challenges both in the system design, how things line up, in particular how to use, in this case we're using a light gauge kind of steel construction, very conventional methodologies that are very common in North America, bringing these into Qatar, producing them there, so when they come to site and people are working on the sort of interfaces with the panel and going into the building, it's just it's what they see is a very conventional construction methodology. And so in this case, this is a panel for another project we did in Brooklyn, where it's an absolutely massive panel. This is the panel that ultimately got installed, and it's built from a extremely conventional methodologies. But this also comes into some questions with how do we wrestle U value down. There's a lot of design tweaks as we go through, requirements from the city, requirements from the architect, requirements for structural changes, depth of walls, and things like this. And so I think the key tool that we have at our disposal, it's been very useful in this, is we've built a fully parametric model of the building. And we use that as a tool to query and run analysis on. So in this case, we're doing a fully parametric full building assembly U value, where we have, I think, 28,000 conditions that we can interrogate, add the sort of run the thermal analysis on, and then it turns out spreadsheets. We can see where heat losses is, and then we can go and say, okay, we can tweak this a bit. This will give us a 10% gain if we do this. If we tweak this by 5%, we can do this. We can run scenarios on. So it allows this, we have a tool to look into the building as a whole and run scenarios on. And I think it's allowed this iterative process over the last 5 months of working on this. We've, I think collectively as this group has really, what took was a very hard task of achieving a U value of 0.44 and gotten there, and so you can get us into a passive house scenario. I think it's been wonderfully encouraging process. So,
Thanks, Evan. Just is there anybody from the city of Vancouver here in the audience? Okay, Pattrick. How has it been like dealing with the city of Vancouver on this project? Talk frankly. Nobody's here from the city of Vancouver.
Before I feel that one, just back to what Evan was saying with the process and getting to this point, and you mentioned the 0.44 U value, but the process of how we work is interesting. So I think it's worth expanding a little bit. That so we're the architect of record, and Lauren, Passive House consultant team and facade consultant. But then with Design Assist coming in, so Evan and at front and Alutech, you're running the Passive House model at RDH, and you say, this is our overall facade U value. We need to get to 0.44. And that's been really interesting to see how you've taken on that challenge, and how, you know, a facade designer can just break this down into each individual panel. I mean, the panelization even benefits the process of getting a better U value for the whole thing, because you can look at each one in individuals. And I think John mentioned, like, the J panel is a tricky one, and that's one that slots into the notch there on the north and south of the building, and it curves in like 2 dimensions as well. So it's extremely complex modeling, but by just breaking it down, and the panelization has kind of added to that a method of I think driving it to the lowest possible U value. And then the other levers and tweaks, I guess, that you're using are changing the glass specifications, the coatings on the glass, the thickness of the panel, pretty much fixed.
Yeah, and it's just sort of like trying to achieve it within the envelope that we're given, and really look at, you know, what are tools with materiality, with panelization, with how do we tweak a detail, and then running that across. You know, we have a dynamically changing building. You can't just take one panel and say this is our U value. You actually need to interrogate it across everything to see, you know, what are things you can address that have a, you know, neutral or sort of impact on the architecture, but a positive impact on the building performance. And I think that's been the challenge. And, you know, with Tom especially, design architect has been really great in this process, where he's been proactive in looking for both architectural solutions to meet, you know, a very aggressive target.
Thanks, Pattrick.
Did I answer your question? Okay, so I'll field the question on this, you know, what does certifying a passive house mean, and what does it mean to get that permits in place and approvals for that? So the project has been rezoned, and there's FSR density attached to the site now, and it's got the caveat, but you must certify to passive house standard, which has never been done before for a building this size, and it will be very extremely difficult. But it's a great challenge. And then we've also got our setbacks for the building. So very quickly, Evan and the team realized that the setbacks and the saleable area are the untouchables, and everything else had to work around that to make this U value work. So when we talked earlier about over-insulating the window frames, that's great. The more you can do that, the better that window frame installation will be, and hides the frame. You've got this beautiful detail where the metal panel returns into glass, and it's seamless. But we'd set the line of glass, we'd set the outside of the facade. That's the saleable area, that's the setback area. We can't change those. So that kind of is, these are the kind of things that add to the challenge. And so we've set the form of the building at the rezoning, and as we work through development permit process. And we've worked with the sustainability department at the city of Vancouver, who have been great allies to the project and guiding us through the process and the different kind of allowances that are within the system of for passive house. So those are things like wall exclusions for insulation. So at rezoning, that's the original mega panel concept was developed so that we could have a certifiable passive house designed that early on, which is something you'd never expect to achieve.
Yeah, and kind of committing to those kinds of things, like the wall thickness exclusion, so early in the project, when you're still, you know, quite early in the facade design process. And, you know, certainly, you know, Evan and others haven't joined the team at that point. You know, it's a bit tricky. So you're kind of developing these proof of concept systems to be able to show that, like, yeah, this is possible. and here's some ways of doing it, and we can commit to this in this sort of rezoning process. But you also know that there's a whole lot of work still to come to actually kind of flush that out.
Thanks. The other authority that we deal with is the Passivhaus Institute in Germany, who's a certifier. So Lauren, maybe you can talk a little bit about the approach with them, and maybe talk a little bit about testing of the building in situ on site.
Yeah, so I think so on this project, PHI, they're obviously they created the Passivhaus standard, but they're also the certifier for this project. And I think it's kind of a nice relationship actually for the project, because there are so many sort of new innovative pieces. We're sort of pushing the boundaries of Passivhaus in every direction. So just being able to engage with them directly and get answers on some of these questions and things that we're trying to do has been really great. Certainly one of the things that we have to do through the standard is the testing that you're talking about, Rick, and so we will be doing an air tightness test of the building, and that is one that we're sort of working through with them. I think traditionally they anticipate that you're going to test the whole thing, but testing a 60-story tower is time consuming and expensive. So we're kind of working through with them, proposing alternate ways of doing that. Sampling sections of the building, typical floors, that kind of thing. So that's one of those things maybe we haven't quite resolved yet, but we're definitely working on with PHI.
Are there any questions that anybody in the audience would like to ask?
Is it called the curve because of the Keeling curve? Was that the inspiration, like the sinusoidal, but it's not exponential as an optimistic interpretation? When
Tom Wright, the architect, first designed or came with his first design, he had taken I asked him, how did you come about with the actual mathematics behind the curve? And he says, I took a point out here and an arc like that, and then took the tangent point and put another point out here and a curve like that. And so I went home and got a similar curve. We had a 2.5 meter offset between one side and the other going up the building. And I applied a sine curve to it. And so I came in the next day and printed off both the curve with the radius and the sinusoidal curve. And I put them in front of Tom and I said, okay, Tom, look at both of these and tell me which one you like better. And he goes, nah, I don't do that. Tell me the difference. And I go, no, Tom, and I'm getting down on the desk like this, looking at them as though you're looking up from the sidewalk. And I said, look at them and tell me which one. He says, no, tell me. So I had to tell him, okay, this is this. And then he looked down, and of course the curve that you draw with circles looks lumpy when you're looking up at it on edge. So it was, at that point he agreed that the sinusoidal curve looked better. So it didn't come from the Keeling curve, but it's a sine curve is a very nice curve and look good from the sidewalk level, which we think a lot of people are going to enjoy this building from when you look up at it from below. Any other questions?
Sorry for so many questions. How did you get the seismic drift to work with such a wide panel and so many connection points?
Great question.
Great.
You want to answer?
Yeah, I'll take a stab. I mean, so the advantage of a mega panel is you can, as long as you design it, and the whole thing is designed as a giant truss, really, and you basically, for a lot of the live load that's in the building, as long as you make your dead load connections back to only where you have vertical primary structure, you remove a huge component of some of the live load from that. And then the seismic drift comes really at the corners, where you have, you've got maybe two different panels in different planes kind of going to go past each other. And so it's really about designing a joint such that in the moment where you have a seismic event and they need to slip past each other, you just design it for that. And the other bit is the vertical movement that comes, and that was always going to be a problem with the unitized facade. Is you end up with that amount of deflection doesn't change. The amount of movement doesn't change. You just end up with a really, really big joint potentially. So we kind of hide it with an overlap so you don't actually see it. So you have a really big kind of unitized joint. And by hiding it, we're also actually improving a bit of the U value because you're kind of keeping the air from, oh shoot, this is falling off. Keeping the air from kind of getting to it very easily. And by also reducing this sort of number of them, your U value is actually improved. So I think we're trying to attack it from multi-dimensional kind of.
Yeah, you're eventually ending up with a Z-like joint rather than a standard flat joint. Yeah, that's how it's dealt with.
Thanks for the presentation. Can you talk more into how do you dealt with thermal bridging between the window to wall connections?
Yeah, that's a great question. I think I'll get Pattrick to answer that, and maybe Pattrick, you can tell him of our latest issue with the column that has to catch the garage columns.
Okay, okay, you have the flipper there. So the question is specifically the window install detail, but we mentioned the over installation. Do we have a slide showing the window section?
I think it's also part the windows themselves are also a passive house window. Oh no, right? So they're already certified passive house, and then as you said, we have the wraparound of the insulation on both sides, which assists with all of that. Yeah.
Yeah.
And you have to remember, it's also a mega panel, right? So these windows are being installed in the factory into this under factory conditions, into the actual overall large panel. Yeah.
Because we have so much conductive framing, the aluminum windows, the backup framing of the mega panel. Really, the trick with all of that has just been to try and get sort of insulation outboard of that as much as we can. So around the perimeters of the windows, and then in the field of the panel as well.
The external cladding sheet is all thermally broken away from the actual frame, the structural frame as well. Yeah.
I think when we're talking about thermal bridging, the balconies are a huge thermal bridge in the project. They're the most challenging ones to deal with, and so they're envisaged right now is cast in place thermal breaks. And so that's something that's been allowed for from the beginning, but these are quite large balconies on the south side here, and those are cantilevered balconies. And then this central balcony in the notch here is also designed as a cantilevered balcony. We can pull up the plan, but so as not to connect to the building on three sides, even though it's inside the notch there, the facade will return, and there'll just be the one side where it's actually connected. And even when we use thermal breaks on these balconies, there's still a significant heat loss overall for the building. There's the floor plan, just to give you an idea of that.
Mm-hmm. The other thing I think that Evan maybe mentioned there is that, if you think about a traditional unitized system, then you're going to have a stack joint that's sort of visible from the outside and relatively exposed, often kind of a weak point thermally. But in this system, that stack joint is sort of hidden in behind some insulation and the cladding. And so sort of from a thermal perspective, it's quite protected, so we don't take as much of a hit there.
Are there any other questions?
Hi. Did you have any issues with or overheating of the building, or how did you overcome with such problems? Did you consider overheating of the building during the sunny days, or how did you?
Yeah, I think Pattrick's probably the best one to answer that question.
Yeah. So there's a number of overheating studies underway, and that had to be completed. Even just to get our DP development permit released, we have to prove that we're meeting City of Vancouver overheating standards, and then there's also in parallel to that passive house overheating requirements. But really the way we can address it here is by using electrochromic glass, which can be tinted. We've got a lot of protection. We can change the solar heat gain coefficient of the glass, so in summertime a lot less heat gain, and so we actually find the cooling demand for the building is quite a bit lower than the maximum allowed. 15 kilowatt hours per meter squared is allowed, and we're way below that when we utilize the tinted glass.
I think maybe one interesting aspect of that we've been looking at recently is just sort of that concept of overheating now versus like in the future climate. And so running that balance for overheating with the future climate file, and then also looking at what that means in terms of passive house compliance, and that balance that Pattrick's talking about in terms of, you know, how much heating versus cooling do we need. We actually find that the cooling increases by probably about 400% or something if you use a 2050 file. So, you know, in terms of the way the building's going to perform, they're sort of designing for now, but then thinking about the lifespan of it and how it's going to do with overheating in the future.
Yeah, I was quite surprised in the first iteration of the model that without electrochromic glass, we would use quite an open glass, right? The G value is 0.4,
yeah,
which seems, you know, that's going to be fantastic in the summer or in the winter time. You're going to use very little energy to heat the building, but it seems risky, you know, in summer. So we're happier with the direction we've moved. Yeah.
So with the electrochromic glass, you know, we're not in a position in our building where we have overhangs where we can, except where the balconies are, but where we don't have balconies, there's no way to prevent the sun from coming in. I mean, we sell views, so we need large windows, otherwise we can't compete with our competitors. And so by using electrochromic glass, it cuts down our cooling loads by about 1/4 to 1/5 of what it would normally take. Which means we can, you know, downsize heat pumps on the roof, which is where our cooling is, you know, the energy for cooling comes from. And it just means a reduction in the amount of mechanical systems within the suites themselves. Well, I want to thank the panel here for joining me, and thank you all for coming. I'm going to pass over the microphone. Our host.
Up and running. I just want to say thank you again to the panel, to our hosts, Zak and Ahmed and Susan and the whole Zak team. This was a great event. Obviously, thank you to the venue and service staff. 500 people is a lot of people. The food was excellent and the service was incredible, so very well done. Obviously, thanks to the partners and sponsors. These events are not possible without them. So I hope you got time to meet with them at their booths or in the expo hall. And obviously, thank you to the presenters. A lot of work goes into these decks and preparing for events like these on top of everyday business, which just keeps growing. So thank you to the audience and for making this a great success. With 30 shows a year, I hope you'll consider visiting another city to catch a Zak conference and learn about what's going on there. And I think the last thing I want to say is that we need more people in the industry. So if you have kids or nieces or nephews and any of them are interested in this, get them to a job site, get to them before the apps do, or maybe build gaming apps to build facades. I don't know. That's, I guess, a different crowd. But I'm looking forward to working with you and learning from you in the future. Thank you very much. Have a good night.
Thank you, Heather. I think a round of applause for Heather. She was excellent. She curated today's event. Thank you so much. So as I mentioned in the morning, we've recorded today's event. We'll share the YouTube link with you along with the feedback link next week. Should be there with you by next Thursday. I'd like to thank our event sponsors, Rainers and others for supporting this first edition of the Zak World of Façades conference here in Vancouver. And next one in Canada is in Montreal on the 19th of October. Of course, we've got San Francisco next week, DC next month, and New York in October. So those who are willing to attend those events, please do drop by. We'll be happy to host you again. So thank you all.